Hi everyone and welcome back to another marathon of power system. So in this marathon we will be studying about unsymmetrical faults. First of all, we will be discussing about sequence networks. Okay, like I hope you know. If you don't know, then you learn that in unsymmetrical faults, all the three phases, right, will not have balanced current. If the currents are not balanced, then we break down our components like unsymmetrical components into symmetrical components: zero sequence, positive sequence, and negative sequence components. So each network will have different kinds of components. Okay, so how the network behaves, so those things we'll learn. So like you can see from, like, I have taught everything from basics, like how can we draw the zero sequence network of a transformer, right? In every other place, what you will see is they will just tell you to memorize, mug it up, but I have told you conceptually how you can understand. Everywhere else they will draw a diagram of 4 switches, and then they will tell you this switch will be off, this switch will be off, switch will be on during if neutral is grounded, if neutral is not grounded, right? They will tell you to mug up, but I have not done that. I have told you conceptually why this will be open circuit, why this will be closed, right? Why this parallel path will be closed. All those things I have taught. Okay, you can watch the marathon with this. So if you haven't already, make sure you start from the marathon 1. We are building our fundamentals from the basics. Okay, then this is the marathon 3, and if you are enjoying this marathon series, right, make sure to like the video. Okay, comment down below if you have understood the concept clearly, so that I can get a feedback of the video. Okay, so yeah, these are the level of questions that we are solving, right? You can try to solve. If someone has already studied fault analysis power system, they can try to solve it. Okay, these are the levels I wanted to show, because I wanted to know that what level are we teaching. Okay, this is the level that we are teaching. So these are the questions. And another announcement is that currently huge discount is running on all our courses. If you apply the code fusion, FUSION, you will get maximum discount on all our courses. So yeah, with that, I hope you enjoy the marathon, and I will see you in the next video. Until then, happy learning. Hi everyone and welcome back to PrepFusion. So today we will be starting the unsymmetrical faults. So before learning unsymmetrical faults, we have to learn a new concept, that is symmetrical components. So we will understand what is symmetrical components by understanding the difference between balanced and unbalanced system. So briefly we had discussed about balanced and unbalanced system previously. So now we will discuss. So here I have two systems, right? And can you in first glance say which of the system is balanced and which of them is unbalanced? So you are correct. Yes, option A is the system which is balanced, right? So A is the system that is balanced, and B, if you see, although the supply is balanced but the load is unbalanced. If the load is unbalanced, then what happens? The current will not be symmetrical. What do I mean by symmetrical currents? So they will not follow any symmetricity. So voltages and currents will not follow any symmetricity. Unbalanced basically means voltages or currents do not follow symmetry. Now one thing you have to keep in mind, symmetry does not mean balance, does not mean that it has to be balanced in terms of three-phase system. So for a three-phase system, we know that I have three phases A, B, C, and three of them, right? Basically this one, B will lag A by 120 degrees and C will lag B by 120 degrees, and their magnitudes of A, magnitudes of B, magnitude of C will be same, right? But it's not always like if the system is balanced that this condition has to be satisfied. We can say a system is balanced if it follows symmetry. What do I mean by this? I will explain when I will discuss symmetrical components. So I will break my unbalanced system into three balanced system which follow some sort of symmetry. Okay, so for now let's solve this question. We have to find out the line currents of circuit A and B. Line currents means these currents, right? These currents. For circuit A, it is very easy to do the analysis. Why? Because I can do the per phase analysis. Because if the system is balanced, I don't need to analyze the circuit in three-phase domain. I can analyze the circuit in per phase, single phase domain. Okay, so you can cross verify this. This will work. So what do I mean by this? So here, if the neutral is connected to ground, right? So here, if the system is balanced,
this neutral also will be automatically ground. Can I prove it to you? Yes, I can. So we know if I apply KCL at this node, what will be the KCL at this node? So I should also have provided the dot polarity. This is dot, this is dot, this dot. This I forgot to. This I forgot to provide. Instantaneous polarity I should have provided. My bad. So let's assume that it is not ground. You are saying it is not ground. So let's assume a potential here Vn. So I can, if I apply a KCL at this node, what will be the KCL at this node? It will be Vn minus Va divided by, what is the total impedance? It is 1 ohm plus J. So 1 plus J. Similarly it will be Vn minus Vb divided by 1 plus J. Plus Vn minus Vc divided by 1 plus J. Like here it is open ended, so I will say the current here is 0. So now if I equate, if I multiply by 1 plus J on both sides, and if I take all these 3 on the right hand side, so my Vn is actually equals to Va plus Vb plus Vc. Do you know what is the sum of the 3 phase voltages? It is 0, right? Because it is a balanced system, so sum of the 3 phase voltages will be 0. Okay, or you can draw in the phasor diagram. So one of them will be here, other one will be here, and the third one will be here. So basically the addition of these 3 phasor components will be 0. We know this, right? Va plus Vb plus Vc is 0. You can do it, you can do it as well. If you are unsure, you can solve it. So this will be V angle 0 degree plus V angle minus 120 degree plus V angle plus 120 degree. Okay, so this will be equals to 0. This will be equals to 0, right? So yeah, that is the case over here. So Vn comes out to be 0, even though I told you that Vn will be 0 because the system is balanced. I have proven to you that Vn will be 0. If Vn is 0, I can simply do the per phase analysis. So this voltage is there connected to ground, and this J plus 1 is there, right? So I can simply convert this whole circuit into per phase analysis. So per phase analysis will be something like this, that here I will have, because all the 3 phases are symmetrical, just it is phase shifted by 120 degrees. So I can find out the per phase analysis. I can do the per phase analysis. So I will have a voltage source connected, that is, let's take this voltage source Va, right? Va is connected. Have they given us the, okay, Va value is Vm angle this, right? So these values are given actually. So it is in terms of Vm, so we have to find out the current in terms of Vm, right? So this will be Va, then there will be there will be this reactance J. Okay, reactance J will be there in per phase. Then there will be this resistance 1 ohm. Okay, so yeah, that is the case over here. So this will be so I can find out the current, because they have asked the current. So current in phase A or line A will be VA angle 0 divided by 1 plus J. So this is basically VA by root 2 angle will be minus 45. So your current, right, in sinusoidal, so what will be your IB? As the system is balanced, I can directly say your IB will have same magnitude, but phase will be shifted by minus 120 because the voltage also was shifted by minus 120, right? If it is a balanced system, then everything will be balanced. So I don't need to do the calculation again for IB. So it will be magnitude will be same, VA by root 2. Anyways, we know magnitude of VA, magnitude of VB and magnitude of VC all are same, right? Angle, this will be minus 45. Okay, minus 45 minus 120. So this will be minus 165. Okay, and my IC will be, you can calculate the values, you will get the same value. VA angle root 2 this will not be minus, this will be plus 120, right? Plus 120 from IA. So this will be if I add 120, so this is minus 80 plus 75, so it will be 75, right? 120 minus 45, it will be 75. So this will be plus 75. Okay, so this will be Vm by root 2 sine omega t minus 45 degrees. Okay, and this will be equals to Vm by root 2 sine omega t minus 165 degrees, and this will be Vm by root 2 sine omega t plus 75 degrees. Okay, so these will be the line currents for the circuit A. Now for the circuit B, will this be this much simpler? No, it will not be this simple. We have to use KCL. I cannot do this kind of thing that okay, this is ground, I will do the per phase analysis. So per phase analysis is not possible for unbalanced system. So I will write here per phase analysis. Why is it unbalanced? Because the load you see is unbalanced, right? So that's why it is unbalanced. So there can be two things, either the source is unbalanced or the load is unbalanced, or both of them are unbalanced. In both cases it will be a unbalanced system. In all the three cases it will be a unbalanced system, that I will discuss in the next few slides. So let me first find out the currents. How will I find out the currents? For that, first of all, I have to apply a KCL in this neutral node Vn. So this time Vn will not be 0 because the system is unbalanced. So from here I will be able to find out my Vn. So Vn minus Va divided by 1 plus J plus Vn minus Vb divided by 1 plus J plus Vn minus Vc divided by 1 plus J equal to 0. So 1 plus J, will it go away? Okay, no, sorry, this will not be this, right? 1 plus J, because here this is 1 plus J, but this is 2 plus J, because this, sorry, this is C, this is B, right? Yeah, 2 plus J, because the resistance is here is 2, so it will not simply get cancelled. Here the resistance is 3. If you see here, the resistance is 3, right? So that's why the unbalancing comes. So I have to solve this now. So this will be a bit difficult for me to solve. So Vn will be here and I will have 1 plus j plus 2 plus j plus 3 plus j. This will be equals to here VA. So this will be very, very difficult to calculate, right? Very, very difficult. You can calculate this. So VA will be V angle 0 basically. So V angle 0 divided by 1 plus j. Okay. This will be VB. So V angle minus 120 divided by 2 plus j plus V angle plus 120 divided by 1 plus j, 3 plus j, right? So it's very difficult for us to calculate, right? Very difficult. You can calculate, but I will not calculate because I have to cover other things as well. So we will stop here. So that's why a thing came that is known as symmetrical components. So we will break down our unbalanced system into symmetrical components, 3 symmetrical components to be precise. I will discuss about that. So few things you have to keep in mind, that if like this, I think I have discussed later as well, that if my system, that is supply source, is balanced, right, but my load is unbalanced, then also my overall system will be unbalanced. If my source is unbalanced but my load is balanced, then also my system will be unbalanced. And if both are unbalanced, then anyways my system will be unbalanced only. If both of them are balanced, then only the system will be balanced. Otherwise, the system will be always unbalanced. So, for a system to be balanced, the both the source and load should be balanced. Okay, both the load and source should be balanced. So we will discuss few things. So what are symmetrical components? It is basically a method of analyzing the unbalanced systems. So we know in pre-fault condition, in pre-fault, the system for a, what is the characteristics of a unsymmetrical fault? Pre-fault condition system will be balanced, right? Voltage and currents all will be in phase, all will have equal magnitude. But post-fault, what will happen? Due to symmetrical faults, the system still remains balanced, but due to unsymmetrical faults, the system will become unbalanced, like LG fault, like LL fault, like LLG fault. So all these faults are there. Due to these, the system will become unbalanced. So here per phase analysis is not valid. So what we will do, we will break the system into symmetrical components, and individually I will do the per phase analysis of those 3 symmetrical components, because we love per phase analysis because that is the easier way. So individually do the analysis, per phase analysis of symmetrical components. Okay, so I think we have already discussed. So whatever we have studied till now, can you identify whether the three circuits or systems are balanced or unbalanced, right? Whether the following systems are balanced or unbalanced. So I have already given you enough hints what needs to be taken care, right? So here in circuit A, what do I see? I see the load is balanced. I see the source also is balanced, right? Here all of the series reactants are same and the voltages magnitude are same and they are phase shifted by 120 degrees. So it's a balanced system. So circuit A is a balanced system. Circuit B, if I see circuit B, right? In circuit B, what am I observing? The load is unbalanced, but the source is balanced. So load is unbalanced. Then what kind of system is this? It is a unbalanced system. It is a unbalanced system. Okay. Now coming to C. So if I come to C, what do you see? Load is balanced. Is the source balanced? I see magnitudes are same, but phase difference here is minus 100, here it is plus 100, but it should be for a three-phase system. For the system to be balanced, the phase difference should be 120, right? But here it is minus 100, here it is 100 between these two, and here it is 200. So it is not balanced. So again it is unbalanced, right? So for unbalanced system, we have to do the symmetrical component analysis. So as I have told you previously as well, that a balanced system means where the load and source both are balanced. Even if one of them is unbalanced, then the system becomes unbalanced. That is, if the load becomes unbalanced, system will be unbalanced. If the source becomes unbalanced, system will be unbalanced. If both of them become unbalanced, system will be anyways unbalanced. Okay. Okay. Yeah. Now understanding the symmetrical components. The symmetrical component method was proposed by Charles L. Fortescue in 1980. Okay. It provides a mathematical framework to transform an unbalanced set of phasors into a combination of balanced sets. Right. So what we will do? We will convert our unbalanced system into combination of balanced set, mainly three sets. One will be called as the positive sequence component, second will be called as the negative sequence component, third will be called as the zero sequence component. So one by one we will understand what does positive sequence components mean, negative sequence component mean, and zero sequence component mean. So positive sequence component is same as your original system. So if your original system was supposed to be balanced with phase sequence ABC, then your positive sequence component of the unbalanced system also will follow phase sequence of ABC, and all of those voltages magnitudes will be same and they will be phase shifted by 120. Phase sequence will be ABC. Negative sequence component will be just opposite, like everything will be same, the phase sequence will reverse. So if the original system had a phase sequence of ABC, negative sequence will have a phase sequence of ACB as it is written over here. What is zero sequence component? So zero sequence component will be those components whose magnitudes will be phase and the phase difference between them will be 0. Magnitudes will be same and the phase difference between them will be simply 0. Okay, those are my zero sequence components. Okay, I hope you have understood that point. So yeah, so basically I can write my phase unbalanced voltage VA as the sum of a zero sequence component, that is this one VAO. This will be actually VAO, right? Zero sequence component VAO, VBO, and VCO. This will be VB2, like we write negative sequence as 2, VA2, VC. Let me write this in bottom, right? This will be 1, this is 1. What I'm doing. Okay, so yeah, so I can write my VA as the sum of 0 sequence component and its own negative sequence component VA2 and its positive sequence component VA1. So these three are individually balanced, but if I'm adding these three components, automatically the system will become unbalanced. That is fine, but I will analyze 0 sequence component separately, I will analyze positive sequence component separately and negative sequence component separately. That will make the analysis much simpler. Otherwise, if you try to solve this equation, it will be very hectic for you. It will be very hectic for you, right? So yeah, that is what my symmetrical components are. Don't worry, I will get into this each of them slowly. So it is only, remember, limitations of symmetrical components, it is only applicable to phasor quantities, because phasor quantities are those quantities which are rotating in nature, right, which are sinusoidal in nature. So those quantities can be applied, the symmetrical component method can be applied. It cannot be applied to power, because power is not a phasor, it is a scalar. Right? Impedance also is not a phasor basically, it's a complex number. Impedance is a complex number, it's not, it is a static value, it's not rotating, right? So this can be only applied to voltages and current. So how can I apply it to voltage? So VA can be written as VAO plus VA1 plus VA2. VB can be written as VBO, VB1, VB2. VC can be written as VCO, VC1 plus VC2. Okay. So this is what my voltages. This is how I can write my voltages. Okay. Then what about currents? Currents also will follow the same thing. So if I copy and paste, currents also will follow the same pattern. I can write my unsymmetrical currents as the sum of three symmetrical components. Okay, so IA, this will be IA, IB, IC, VAO, VBO, VCO, VA1, VB1, VC1, VIC2. Okay, so these are my currents basically. I hope you have understood this point. Now I told you, right? So basically for positive sequence component, the clockwise movement, first I will get A, then B, then C, because it is following the actual phase. Because it is following the actual phase sequence. So how can I write my VB1? So VA1, let's assume VA1 is, let's say, V1 angle of 0 degree. So what will be my VB1? VB1 will be V1 angle of minus 120, because I'm going in the clockwise direction and I have to rotate my 120 degrees. So clockwise, that's why negative, and rotating 120, that's why it is minus 120, right? Then VC1, V1 angle plus 120, okay, because I am rotating in the anti-clockwise direction 120 degrees, right? So what about these components? So these components also will be same, but just the phase sequence has changed. So if I rotate in the clockwise direction by 120 degrees from VA1, now I am reaching VC2, not VB2. Previously I was reaching the phase B voltage, right? So that's why the name negative phase sequence. The phase sequence is just opposite. So if I copy these values over here, so this will be VA2, VC2, and so now what will be, so this magnitude also will change because these are not same anymore. This will be V2, 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 but this time, as it is, if I move in the clockwise, I am reaching VC2. So that means VC2 will be minus 120 degrees from V2. So that's then this will be negative 120, not plus. Similarly, if I move in the anti-clockwise direction by 120 degrees, it becomes plus 120, right? So this is plus 120. So the phase sequence has just reversed. That's why the name negative phase sequence, negative symmetrical components, right? Negative sequence components. Okay, and what about VAO and VBO and VCO? These zero sequence components will have equal magnitude and their phase shift also will be zero. So basically, VAO will be equals to VB0 will be equals to VC0. So magnitude same and 0 degree phase shift, right? Phase shift also will be same. Okay, that is what my zero sequence components are. So one thing I notice that I see multiple times this, like what is this? This V1 is basically, VC1 is basically V1 into 1 angle plus 120, right? So I'm observing one thing, that this 1 angle plus 120 here also it is coming. So in symmetrical components we give this a name. What is the name? Name is the alpha operator. Okay, the name is the alpha operator. What is the alpha operator? Alpha operator is also called as the transformation operator, right? It is also called as the transformation operator. Okay, so what is transformation operator basically? So transformation operator is nothing. If I have B here and if I multiply the alpha is 1 angle 120, right? So if I multiply alpha with V, I will just rotate in the anti-clockwise direction by 120 degrees. So this will be, alpha is what? Alpha is 1 angle 120. So if I multiply with V, it will not change the magnitude because its magnitude is 1. It will change the phase by 120. It will shift the phasor V by 120 plus 120, right? So this will become 1 angle plus 120 degrees. Okay, so into V, that's why we shift. If I'm multiplying anything by alpha, it will just shift the phasor by plus 120 degrees. Okay, so this alpha is something familiar if you remember cube root of unity. So cube root of unity, if you remember, it was equals to minus half plus j root 2 by 2 plus minus j root 2 by 2 was there. So it is also called as cube root of unity, because if you remember this value used to come in cube root of unity, right? So that's why it is also called as cube root of unity. So all the properties of cube root of unity will be followed here. Whatever were the properties of cube root of unity will be followed here. So I will explain you what are the properties of cube root of unity. So like I will give you another example. This was my reference, right? So it got rotated by 120 degrees. So now the value, this value is basically V angle plus 120. So let's say I had a phasor that was V and it had magnitude of V1 angle minus 45, right? So if I multiply the alpha operator, can you tell me what will happen? If I multiply alpha into V, or let's say V1, right? Alpha into V1. This will be basically if I multiply alpha into V1, that means 1 angle 120 I am multiplying, magnitude will not change. This will be magnitude of V1, but the angle will change, right? It will be shifted by plus 120. So 120 minus 45 will be what? 75. So it will be plus 75. So pictorially what will happen? Pictorially I will just shift it in the clockwise direction by 120. So this is my reference, right? And I will have a phasor here, that is minus 45 degrees. Okay, so if I shift it by plus 120, it will become 75. So 75 will be somewhere here. Somewhere here. Okay, so this like magnitude will not change. Sorry, magnitude will not change. Okay, so this will be plus 75 from the reference, but overall it has shifted by 120 in the clockwise direction. So this is my alpha into V1. So I hope now it is clear like what is alpha into V1. So you can choose any magnitude. This magnitude can be anything, right? 1, 2, 3, 4, 5, 6, anything. It does not matter. It will not change the magnitude. Here it has told us that the operator rotates any phasor by 120 degree in the counterclockwise direction without changing its magnitude. Okay, I will not change its magnitude. So there are few key properties that you should keep in mind in case of alpha, right? That is cube root of unity. We know it is cube root of unity. So if I cube it, I will get 1. If you remember, there was one more property like in your JE days, 1 plus omega square was equal to 0. So same thing is here because it's a cube root of unity. So I can simply apply this property, right? One more thing we can do is I know alpha cube is equals to 1. If alpha cube is equals to 1, if I multiply by alpha inverse on both sides, what will I get? So this will be alpha square, that is equals to alpha inverse. What I've done, I have just multiplied by alpha inverse on both sides. Okay, I have just multiplied alpha inverse on both sides. Okay, and these are more additional properties. We know alpha is equals to 1 angle 120, which is minus half plus j root 3 by 2. So alpha square will be what? It is 1 angle 240. If you break it down into rectangular coordinates, so this will be minus half, this will become minus. So this is the other cube root of unity. This is one of the cube root of unity. This is the other cube root of unity. And of course alpha cube is 1. So one of the solution will be 1. So that is the third cube root of unity. So this property I can again extend that what is 1 plus alpha square. So if I take the alpha on that side, 1 plus alpha square will be minus alpha. This will be used. This will be used in lot of places. Okay, this will be used in lot of places. So what is 1 plus alpha square basically if in phasor? So 1 plus alpha square is 1 angle 0 plus 1 angle alpha square is 240. Basically if I am squaring this, right, the angle will be doubled, right? So this will be 240 is equals to minus of alpha. So minus 1 angle 120, or I can write this in terms of if I subtract 360, because adding and subtracting 360 from an angle does not make any difference. So 1 angle 0 plus 1 angle minus 120, and here it is minus 1. Minus 1 basically means plus 180 or minus 180 in angle terms, right? So this will be minus, if I do minus 180, this will be minus 60 degrees. So I got information that if I am adding two vectors which are 120 degrees apart, right, like I have a vector here and I have a vector here which are 120 degrees apart. Okay, so then 1 angle minus 60 is what? 1 angle minus 60 is the resultant. If I add these two values, right, if I am adding these two, so the resultant will come somewhere around here, correct? So this will be here, right, which we know magnitude will be same, but it will be minus 60. That's it. Basically it will be a bisector, it will be just a bisector. Magnitude will be same, but it will be bisector. So this is also another handy thing to keep in mind, right? This can help you in complex calculations. So these are handy things to keep in mind. Okay, now one more thing is that what is my alpha conjugate? So alpha conjugate is nothing but alpha is what? Alpha is 1 angle 120. Conjugate will be just the negative, right? Alpha conjugate will be 1 angle minus 120. So what is 1 angle minus 120 actually? 1 angle minus 120 is same as alpha square. Why? Because alpha square is 240. If I subtract 360, because adding and subtracting 360 does not make any difference to an angle, this will be basically this will become 1 angle minus 120. So alpha square is actually equals to 1 angle minus 120, which is equals to alpha conjugate. So that's why I have written here alpha conjugate is equals to alpha square. And what is alpha square equals to? Alpha square is equals to alpha inverse, right? So that's why these are the few properties that can be utilized later on. Okay, I'm just providing you all this. These are the few properties that we will be using. Okay, one more thing, one more key point that I want to explain over here is that please keep this in mind that in some books or in exam your alpha operator can be equals to 1 angle minus 120, right? So be careful, be careful. Okay, if you are not careful, then something like you will go wrong, because all these properties won't be valid here, right? Properties will change basically, then the above results will change. So make sure you are checking okay, make sure you are checking, right? So yeah, now like you must check in the exam if alpha is equals to 1 angle plus 120 or 1 angle minus 120, right? So few more key points we can do. One of those key points is that alpha conjugate is this, right? Do we have any other? Yeah, one more thing we can do. I can take the conjugate of this, right? If I take the conjugate, what will happen? Alpha conjugate is equals to alpha square conjugate is equals to alpha inverse conjugate, right? Whatever you want to write. So basically from here you can directly say that your alpha is equals to alpha square conjugate. Okay, alpha is equals to alpha square conjugate. This property also can be applied. One more thing, as it is a cube root of unity, you can break it down in terms of cube, right? So let's say I have to find out alpha raised to power 28. What will you do? You will do alpha cube whole raised to power, basically you will divide 28, right? So if I divide 28, what do I get? If I divide 28, I will multiply it by 7, not 7, sorry, 9. This will be 27 and 1, right? So 1 is the remainder. So what I can write is this 1 will be here, alpha raised to power 1, and this will be 9 into 3. So alpha raised to power 3 raised to power 9. So this will cover the 27 and an additional 1 will be here. So overall, this will be equals to 1 raised to power 9. 1 raised to power 9 is simply 1. So this is only equals to alpha, right? So that's how you can simplify. This is also another way to simplify the things. Now one more thing that can be asked is 1 minus alpha. This also will be used very well, right? What is 1 minus alpha? Okay, 1 minus alpha. What is 1 minus alpha? So 1 minus alpha, I actually know what is the value of 1 minus alpha. So here, right, what is 1? What is alpha? 1 is 1. What is alpha? Alpha is minus half plus j root 3 by 2. So it is basically 1 minus half plus j root 3 by 2, which is equals to 3 by 2 plus j root 3 by 2. If I take common here root 3, what will I get? So if I take common here root 3, if I take common, this will be, or can I take something else? Root 3 by 2, can I take common? I'm thinking root 3 by 2, yes, root 3 by 2 also I can take common, right? So this will be root 3 plus j. Will it be helpful to me? Yeah, so kind of this will be basically root 3 angle plus 60. Why? Not plus 60, sorry, tan inverse y upon x, sorry, this will not be plus 60, tan inverse 1 by root 3, this will be 30 plus 30. Okay, so you can do this, right? So basically it is magnitude will be square, this square plus this square under root. So 3 plus 1 under root, that is 4 under root, that is 2. Okay, 2 times root 3 by 2 will be root 3 only, and angle will be tan inverse 1 upon root 3, that is 30, right? So that is 30. So this will be equals to plus 30, right? So this will be root 3 into plus 30. Okay, so now this becomes, so 1 minus alpha becomes plus 30. Am I correct? Sorry, this is negative, right? Sorry, this is negative. This should be negative. So this will be actually negative. Now intuitively, can I answer it? Yes. So I have to subtract 1. I have to subtract alpha from 1, right? So 1 is here. One is here, that is 1 angle 0. Okay, what is alpha? Alpha, I know alpha is actually 1 angle 120, but it is minus alpha, so it will be here, right? So my alpha is here, but I have to subtract, right? Subtract means negative of the vector. So this is alpha basically, this is 120, but I have to subtract. So subtraction means it will be here, right? And these two vectors I have to add. So it is basically 1 plus of minus alpha. So what is the angle here? So this whole angle is 180, this whole angle is 120, so this much angle will be 60. So this much angle will be 60 degrees. Okay, this much angle is 60, and this is minus of alpha, right? Minus of alpha. So have I told you something like this? What is the magnitude of this vector? Magnitude of this vector is again 1. What is the angle? Angle is minus 60 degrees, right? Have I told you something like this, that if I have two phasors whose magnitude are same and they are phase shifted by 60 degrees, then the resultant will be the angle bisector, and its magnitude will become root 3 times the previous magnitude. So root 3 and resultant will be angle bisector, so it will be minus 30. So we got two results. One is if I have two phasors which are phase shifted by 120 degrees, the resultant will be the angle bisector with the magnitude same as the previous magnitudes. If I have two vectors which are phase shifted by 60 degrees, then the resultant will be the angle bisector and their magnitude will be root 3 times the previous one. Okay, these are a few important points which will be used later on. Okay, which will be used later on. Okay, so what I know, what is 1 minus alpha? What about what is 1 minus alpha square? So all this will be used later on, right? So I'm just telling you how to calculate mathematically, how to calculate in phases. So it's not like you have to remember the result. No, you have been given the expression, you draw the phasor and then you solve, because with pictures we are easily able to remember. So these things you can put in short notes. So this will be 1 minus alpha square equals to, what is alpha square? Alpha square is minus half, and the it will be minus 1 by minus 1 by 2, right? So minus root 3 by 2, minus j root 3 by 2. So minus one by 2 minus j root 3 by 2. Okay, so this will be equals to root 3 by 2 plus j root 3 by 2. Okay, so so this, right, what will be the value? Again, if I take common root 3 by 2, this will be root 3 this time plus j. So this will be root 3 angle plus 30. Okay, so let us check vectorically, is it true in phasor diagrams? So again I will add, so alpha square will be basically minus 120 here, right? So I have this one angle 0, and this is my alpha square here. So my minus of alpha square will be here. What is the angle? 60. Again the same trend we will follow, right? So this will be minus of alpha square. I will add these two. So the resultant will be in the bisector. Its magnitude will be root 3 times the previous one. Its angle will be the bisector, that is plus 30. Now it is in the clockwise direction. So it is plus 30 degrees. Okay. So I hope it is clear what are the angles and the magnitudes. Okay, so these are the few results you should remember. Okay, so remember this thing, that we will get these many equations. So I have these so these equations we have to solve. We will see how can I solve these equations. Okay, I hope it is clear. One more last property I want to say. If I subtract these two values, sorry, if I add these two values, what will I get? Or if I subtract this from this, why I want to do that, I will explain. So if I subtract this from this one, so 1 minus alpha square minus 1 minus alpha will be equals to what? I already know the result. This is basically root 3 by 2. This is 3 by 2 minus j root 3 by 2. This is plus 3 by 2 plus j root 3 by 2, right? 3 by 2, 3 by 2 minus plus. So automatically the imaginary component will be added because I am subtracting. The similar terms will be cancelled. The imaginary components will be added. So this will become plus j root 3, right? So basically what we get is my alpha minus alpha square is equals to j root 3, right? Is this correct intuitively? So intuitively, if I say alpha will be somewhere here, alpha square will be somewhere here. Okay, so what will be the resultant? Sorry, I'm not adding, actually I'm subtracting, right? So alpha is here, I'm subtracting alpha square will be somewhere here. So again some symmetry is there, right? So what is this angle? This also will be 120 only, so this angle will be 60. this will be 60, right? So the resultant will be bisector exactly at the center, right? So this much angle from the reference, this much angle from the reference is 120. I know it is half. So what will be this angle? This is 120. This much is 30, right? So what will be this total angle? And this much is 60, right? So this is whole 120 and this is 30. So this whole angle will be 90. This much is 30. This whole angle is 120. So this much angle will be 90. So that's why this angle will be 90. Okay. So it's not like I'm telling you to mug up the results, right? No. Don't mug up. Understand, like I'm telling you, I'm writing this mathematically to prove it to you that whatever I'm drawing, that is correct. So in the exam hall, you will draw the phasors. With the phasors, you will solve it. In the exam hall, with the use of phasors, you will solve it. Okay. So I hope that is clear by you. Okay. So these are few properties. Now we will discuss about the positive sequence, negative sequence, and zero sequence components. Right. So what are positive sequence components? Positive sequence components are three phasors which will follow the same phase sequence as the normal phase sequence, as the original phase sequence of the system. So it follows the original phase sequence of the system. The vectors, the phasors will be equal in magnitude and they will be phase shifted by 120 degrees. Phase sequence will be followed as the original phase sequence. So if the original phase sequence was ABC, then this also will be ABC. So first A will come, then if I move in the clockwise, B comes, then again C comes, right? So this is VA1, VC1 and VB1. Okay, that's it. So can I write this in terms of my alpha operator? So VA1 is V angle 0. What is VB1? It is V angle minus 120. So I'm shifting by minus 120. So that is basically what? Alpha square into VA1, right? So I can write my VB1 shifting by minus 120 means alpha square, right? So it will be alpha square into VA1. And what about VC1? So VC1 is V angle 120. So I'm shifting by, I'm not changing the magnitude, I'm just shifting by plus 120. So VC1 is alpha V A1. Okay, so it will be alpha times V1 and alpha square times VV1 will be alpha square into VA1. Okay, so yeah, that is what my VC1 VA1 is for positive phase sequence. For negative phase sequence, already defined that again magnitudes will be equal, phase difference will be 120, but it will follow the reverse phase sequence. So if the original phase sequence was ABC, so I will write here what is the original phase sequence. So I will write here original phase sequence. So original phase sequence is ABC, right? If the original phase sequence is ABC, then the positive sequence components will follow the original phase sequence, but the negative sequence components will reverse. It will be ACB. Now if you see, okay, this has to be changed. Actually, I have not changed it. My bad. This has to be changed. So let me color this blue. Let me color this in yellow. Sorry. Oh, I had changed the color, but I forgot to change the names. Okay, my bad. So color was correct. VC, this will be VB. VB2, this will be VC2, this will be VA2. Okay. So if you see now, if I move in the clockwise direction, now I'm encountering VC2. Previously I was encountering here, if you see, previously I was encountering VB1, right? Okay. If I move in the clockwise direction, now I'm encountering VC2 because it is negative phase sequence. So it will be negative phase sequence. So these components arise due to the unbalanced fault. So unbalanced nature brings this component. So if my system is purely balanced, we will do one numerical as well. You will see that only positive phase sequence components exist. Other components will not exist. So if in a system only positive phase sequence components exist, I can say that the system is balanced. If other components exist, then the system is like not balanced. Okay, then the system is not balanced. Okay, so that is the case over here. and it can damage the system because due to harmonics, right? This negative sequence components, basically the phase sequence is different, so it tries to rotate the machine in the opposite direction. So in either in the counterclockwise direction or in the opposite direction, opposite to original rotation. Okay, so that's why they're dangerous, because I am trying to, let's say the original direction of rotation is clockwise direction, but it is trying to change, right, in the opposite direction. So it is opposite to the original direction, so it will be in the negative phase sequence. That is the problem, right? Okay, so I hope that is clear now. So these components arise due to unbalanced faults. So can I write, so VA2 will be V angle 0, this time VC2 will be minus, like V angle minus 120. Previously VB1 was V angle minus 120. Now VC2 will be V angle minus 120 because the phase sequence has changed. So here as well, one more thing, one more key point, the magnitude of VA1 will be equals to magnitude of VB1 will be equals to magnitude of VC1, just the phase is different. That's how I have shown it over here, right? And here again the magnitude, now these magnitudes are not same, so I will say magnitude of VA2 equals to magnitude of VB2 equals to magnitude of VC2, right? Now these magnitudes actually are not same, right? These magnitudes are not same because they are different components, but VA2, VB2, VC2 all will be same, VA1, VB1, VC1 all will be same. Okay, that is the important part that you have to understand. Okay, so I hope it is clear. Now can I write my, now if you see VC2 is minus 120, so I can write my VC2 again in terms of alpha operator. So VC2 will be equals to V angle minus 120, that is I can write it is V angle, it is VA2 into alpha square, so alpha square into VA2, and my VB2 will be alpha into VA2. So let's now move on to zero sequence component. So what are zero sequence component? So this is my zero sequence component, VA0, VB0 and VC0. Okay, so zero sequence component will have same magnitudes and all will be in phase with each other. There will not be any phase difference. It's not like zero sequence component will always be constant. No, they can be like, it will not be like zero sequence component will always be like 1. It can be J as well, like, but if one of the zero sequence component is J, all the other will be in J. So you will say, sir, is this system balanced? Yes, this system is balanced with respect to itself, right? It is symmetric, right? Because here all the values are same and phases also are same. So in its own set it is symmetric. This system in its own set it is symmetric. This system in its own set it is symmetric. So I can break down my unsymmetrical components into three symmetrical components, three different symmetrical components. Okay, so for zero sequence component, my VAO will be equals to VBO will be equals to VCO. We don't need any alpha operator here. Okay, we don't need any alpha operator. So these are the equations basically. So VA I can write as VAO plus VA1 plus VA2. VB I can write VAO because I have just told you that the zero sequence component of all of them will be same, plus alpha square VA1. So what is my VB actually? VB is equals to VBO plus VB1. Now what is VB1? Remember, it is the positive sequence components, right? Positive sequence component. So I know if it is the positive sequence component, it will lag the VA1 by 120. So alpha is plus 120. I need minus 120 because it is lagging. So I need to multiply alpha square. That's why alpha square is here. That's why alpha square is here. And then it is equals to plus VB2. So VB2 is the negative sequence component. Now it follows the opposite phase sequence of AVC. So it will lead the A phase, right? It will lead the A phase by 120. So I have to multiply alpha. So I have to multiply here alpha. So 1 angle plus 120. So I have to multiply here alpha. I hope that is clear. What is VC? VC is equals to VAO plus alpha VA1 plus alpha square VA2. Okay. So now how do I write it? So this is equals to VC is equals to VCO plus VC1 plus VC2. Okay, so VC0 is what? VC0 is same as VB0, right? Which is same as VA0. So that's why VA0 is here. What is VC1? Again, it is the positive sequence components, and in positive sequence I know it leads the VA1 by 120. So I have to multiply here alpha. That's why alpha will come. And VC2 will lag the negative, it is the negative sequence component, so it will lag the VA2 by minus 120 by 120. So here alpha square will come. So basically what you have to remember, if alpha square is coming here, then alpha square will come here. If alpha is coming here, then alpha will come. So this thing you must remember, right? This will be helpful in few other derivations which we will do, right? If alpha square is coming here, then alpha square will come here. If alpha is coming here, then alpha will come here. Okay, that's it. So what we can do, we can write this in a matrix format. VABC will be equals to, it's basically VA0 plus VA1 plus VA2, the first row. Second row will be VA0 plus alpha square VA1 plus alpha into VA2, right? Then VC is equals to VA0 alpha into VA1 alpha square VA2, right? VA0 alpha into VA1 alpha square VA2. Okay, so we have just written this in the matrix format. Why? Because I want to find out the VA0 VA1 VA2. So how will I find out VA0 VA1 VA2? So this is called as the symmetrical component matrix, right? And this is called as the phase voltage matrix, and this is called as the sequence voltage matrix. Okay, ultimately I still don't know how to find out VA2 VA1 and VA0. I do know that VABC, I don't know this, because these are the unbalanced voltage that is given to me, right? These are the unbalanced voltage that is given to me. So what I can do, I need to find out this value VA0 VA1 VA2, because I don't know this, these are unknown. So I can take the inverse of this matrix and multiply on both sides. I will be able to get my VA0 VA1 VA2. So exactly that is what I will do. I will take the inverse and multiply on both sides. Okay, so what I will do, I will take the inverse, right? So this is also called as the matrix A. This is also called as a matrix A. So if I take the inverse, this will be VA0 VA1 VA2. Okay, this will be equals to, now in what will be the inverse of this? What will be the inverse of this? So there is a neat trick to remember the inverse, right? Or you can, like, of course it's a 3x3 matrix, you can always calculate the inverse, no problem, right? You can always calculate the inverse, but if you remember the inverse, that will be really helpful to you. If you are able to remember the inverse, that will be really helpful, right? So your inverse of this matrix will be, basically what will happen, your alpha and alpha square will just swap their places. Alpha and alpha square will just swap their places. So this thing what you have to remember. So alpha will come here, alpha square will come here, alpha square will come here, alpha will come here. That's it. That's it. Okay. So A inverse will be equals to 1 by 3, right? A 3 extra term will come. This you have to remember, that a 3 will come. Okay. Additional 3 will come because I'm taking the inverse, so some magnitude has to be divided. So 1 by 3 will come, right? Then basically you replace alpha with alpha square, everything else remains same, right? So your inverse will be 1 1 1. If you don't remember this inverse, it will be very difficult. Okay, you have to remember, because you will not, in the exam hall you will not be able to solve it, because these are complex numbers. This is a complex number, right? It's not that simple. It's not a scalar, it's a complex number. So calculation is not that cakewalk. Okay, so 1 1 1 will be here, alpha will be replaced with alpha square. So alpha will be here, alpha square will be here, alpha square will be here, and alpha will be here. Okay, so yeah, 1 by 3, this value is there. Okay, so this is my inverse basically. So from here I can easily find out what is my VA1 0, VA1, VA2. So this will be 1 by 3, 1 by 3, 1 by 3, this 1 1 1 1 alpha alpha square, so 1 1 1 1 1. Now this time alpha will come, alpha square will come here. So how do you remember it? So this was the position for VB1, and VB1, it lacks the VA1 by 120, so minus 120. So alpha square should come, but it's inverse relation, so that's why alpha comes. So that's how you remember this, right? So you just remember this one, right? This first one, everything else will be sorted. How to remember? I have already explained through this equation. So only this part you have to remember, that alpha will be replaced with alpha square, and there will be 1 by 3. Okay, only this part you have to remember. So this will be alpha square alpha into this VA, VB, VC. Okay, so VA, BC, this is my VA0, VA1, VA2, and these are my components. So this is you will solve this. You have to basically solve this equation. So what will be your VA0? From this I get a equation. What is my VA0? VA0 will be VA plus VB plus VC by 3. This is what my VA0 is equals to. What is my VA1? So VA1 will be equals to 1 by 3 will be there into VA plus alpha into VB plus alpha square into VC. So do I recommend you remembering this formula, all these things? You can, like if you are very good in remembering things, you can, but it's fine even if you are not able to remember, you still can solve it. Okay, you still can solve it. There is no problem at all. There is no problem at all. Okay, basically what you have to do, you have to remember this equation, and you have to remember this matrix, right? First you write down this matrix, then from this you write down this matrix, and then you divide by 3, and then you write down this equation, right? So this thing you have to do if you are not able to remember it, right? So that is the alternative way. If you are not able to remember, that's how you can remember. Okay, now what will be VA2? VA2 will be equals to 1 by 3 VA plus alpha square VB plus alpha into VC. Okay, this will be my negative sequence component of VA2. Now if I know VA2, VA0, VA1, VA2, I will be easily able to find out all the other components. What is VB1? It will be alpha into VA1. Okay, what will be VB2? It will be alpha square into VA2. So all the other components I will be easily able to find out if I know VA0, VA1 and VA2. Basically all the other unbalanced components I will be able to find out, because individually they are balanced. So this VA0 is equals to simply what? VB0 is equals to VC0, and this is equals to basically alpha into VA1, right? Sorry, my VB1 will be equals to alpha into VB1. Okay, so alpha into VA1, right? And your VC1 will be alpha square into VC1. This we already know, so I hope I am not writing it over again. Basically the point is, if you are able to find out one, like full components of the one of the phase, you will be easily able to find out the other two other phase unbalanced components. Okay, now one more thing can be there, one more short point can be there, that what if you want to find out VB0, VA1 and VB0, VB1 and VB2 directly. You don't want to find out A phase, you want to find out the B phase. How will you find out the B phase, right? So then what will happen to the matrix? because you want to find in terms of VB, not in terms of A. So that can also happen, right? That can also happen. What do I mean? So you will write, I have my VA phase voltage, VB phase voltage and VC. So I will write my VB phase voltage first. So VB will be VB0 plus VB1 plus VC1, VB2. Okay. Now what will be VA? VA will be VA0, which is same as VB0. What will be VA1? So VA1, I know if it's a positive sequence, I know VB will lag, right? VB will lag, VB1 will lag. So what I have to multiply with VB1 to reach VA1? What do I have to multiply with VB1 to reach VA1? So I am rotating 120 degrees in the clockwise direction. What is that operator? Alpha. So this will be plus alpha into VB1 plus. Now what about VA2? So we know VA2 is here, right? And VB2 lags VA2, sorry, leads VA2, right? So it will be here, leads by 120, right? It is negative sequence component. So what do I have to multiply with VB2 so that I reach VA2? It is minus 120, right? So this will be minus 120. So that's why I have to multiply alpha square. VB2. Okay. So I have to multiply alpha square with VB2. Now VC2, VC. So VC will be, this will be B0. Obviously 0 sequence component is same, plus now VB1 is here, right? VC1 will be here, correct? So what do I have to multiply with VB1 to reach VC1? Minus 120, because I'm going in the clockwise direction. So minus 120 is alpha square. So here alpha square will come. This will be VB1. Now it will be just opposite, right? I hope you get the point. This will be alpha into VB2. So now if I put this in the matrix equation, VA, VB, VC, this will be 1, 1, 1. This will not be 1 anymore. This will be alpha square. This will be 1, 1, and this will be alpha square alpha. Now I will give you some task, okay, and please prove it to me. So this will be VB0, VB1, VB2. Okay. So VB0, VB1, VB2. Now the thing is, important point is, tell me what is the inverse. So go and please, this is the task for you. The task is to find out the inverse of this matrix. Okay. And tell me, is it the same as this one? Is it similar to this one? Basically this will be swapped. Okay. This thing will be swapped. Is it the same? If I just swap this, is it same here? Same will work here. I will just replace alpha with alpha square and job will be done. So your job is find out the actually the inverse 3 cross 3 matrix. These are complex numbers, so not that simple. So find out the inverse and check whether this trick is working. Alpha will be replaced with alpha square and you will multiply by 1 by 3. Okay, this is the homework task for you. So this will be the homework task for you. Okay, now let's like do the same for, like, this is also one way to analyze. So one day GATE examiners actually they will give you these components, right? They might give you VB0, VB1, VB2. Okay, either what you can do, either you can convert this VB0, VB1, VB2 into VA1, VA2 and VA1. So that is one method, or this is another method, right, which you can solve, right? So that is the best method actually, because only you need to remember this formula. So in most cases this actually will not be required, but I'm telling you, just in case, if you have to write in terms of VB0, VB1, you can write this, right? I'm just giving you more options, but most cases you will be required to find VA0, VA1, VA2. If you are able to find out VA0, VA1, VA2, you will be able to find out all the other values, because you can convert back, right? So VA0 will be equals to VB0 will be equals to VC0. VB1 will be alpha square VA1. VC1 will be alpha into VA1, right? So these values will be there. Okay. So I hope it is clear. So for currents as well, you will do the same thing for currents as well. Same thing will be followed, that if phase current is equal to this value, then I can find out the, if the phase currents are unsymmetrical, I can find out the symmetrical components with the help of the same matrix A inverse, right? That's it. So same procedure will be followed for currents. So now let's solve few questions to understand these concepts even better. So the line currents in a three-phase system are given, okay? And of course, from the first glance, of course, it seems that they are not symmetrical, they are not balanced. Why? Because if I find out the magnitude here, it is 3 square plus 5 square 25, so 9 plus 25 34. So under root 34, right? This is what? Under root 8. So of course the magnitudes are different. So of course these all three currents are unsymmetrical or unbalanced. So they want me to find out the positive sequence, negative sequence and zero sequence. Okay, positive sequence, negative sequence and zero sequence. So basically what will be the zero sequence? So for zero sequence you don't need to use any matrix, but still you can use. So it's good if you are able to remember the matrix. If you are not able to remember the matrix, how to write from scratch, I will explain here. After this I will always directly use the formula, right? So I know that my IA will be equals to IA0 plus IA1 plus IA2. What will be my IB? IB will be equals to IB0, that is IA0 plus alpha square into IB1. Why? Alpha square into IA1. Why? I will not explain, right? So alpha square into IA1 plus alpha into IA2. Okay, and your IC is equals to IA0 plus this will be alpha into IA1 because it is leading, right? It is leading, so it will be alpha into IA1 plus alpha square into IA2. So if you are able to write down this second equation, the third equation is just dual, right? It is just dual, it is just opposite. Okay, here alpha square is here, here there is alpha, here there is alpha, this is alpha square. Okay, so you can directly say basically yeah, so what will be the basically matrix? So matrix I can write, this will be 1 1 1 1 1, this will be alpha square, this will be alpha. I could have directly written this matrix as well, this will be alpha, this will be alpha square. I could have directly written this matrix, right? Because I know their phase, here the phase B current will be there, phase C current will be there. Okay, I got directly written this. Now what is the inverse? Inverse will be 1 by 3 into 1 1 1 1 1 1. Alpha will be here, alpha square will be here, alpha square will be here, alpha will be here, right? And this will be VA, not VA, sorry, IA, IB, IC. Same equation will be followed for both voltage and current, and this will be IA0, IA1, IA2. Okay, so from here I can easily find out what is my IA0. IA0 will be, or IA0, the zero sequence current will be basically 1 by 3 1 by 3 into IA0 plus IA1 plus IA2. Okay, sorry, IR plus IY plus IB, right? Actually it is RYB current, so it does not matter. You can write here RYB, it's the same thing, right? I hope you understand. So I will add all these three. So if I add all these three, C plus J5, so this will be 5 plus J7, or this will get cancelled. This will be basically 5 plus J6. So 5 plus J6 is your zero sequence current. Okay, so zero sequence current. Am I correct here? Yes, 5 plus J6 is your zero sequence current. Okay, so I hope it is clear. What is your zero sequence current? What about your IA1? Okay, what is your IA1? What will be your IA1? IA1 will be 1 by 3 IA plus alpha into IB, right? Alpha into IB. So what is IB? That is this value, right? Alpha into IB plus alpha square into IC. Okay, So this will be 1 by 3 into IA. So IA is this value 3 plus J5 3 plus J5, okay, alpha into IB. So what is alpha? Remember, IB is written here as a like rectangular component. So I should write my alpha also in rectangular components. Do you remember what is alpha? So alpha is actually 1 angle 120. So it is roughly on the which quadrant? On the second quadrant, right? Second quadrant, x is negative. So it will be minus half. So that's why this will be minus half, because the real part is negative. Y has to be positive because it is in top. So this will be plus j root 3 by 2. Right? This you have to remember, right? What is alpha? How do you remember? I have explained. In the second quadrant, so in the second quadrant, real part will be negative, imaginary part will be positive. Okay. So this will be plus minus 1 by 2 plus j root 3 by 2 into IB. What is IB? IB current is given to me as 2 plus J2, right? So 2 plus J2, I can directly, okay, let me put it like this, 2 plus J2. So let me put it below here. Plus alpha square. Alpha square will be what? Alpha square is 1 angle minus 120 actually. So this is in which quadrant? So this was in second quadrant, right? This in which quadrant? This is in the third quadrant. In third quadrant, x will be negative, real part will be negative, y will be negative also. So this will be minus j root 3 by 2. Okay, so this will be minus j root 3 by 2, and what will be the current? The current is minus 2 minus j. So minus 2 minus j. So this will be equals to 1 by 3 3 plus j5. Now what will, I will take the 2 common. So if I take the 2 common, this half and this will get cancelled. So basically this will be minus 1 plus j root 3 into 1 plus j. And here, right, I cannot take the 2 common, so I have to directly multiply. So this will be minus half into minus 2, which will be plus 1, minus half into minus j, which will be plus j by 2. Okay, minus half, minus j root 3 by 2 into this, which will be plus j root 3. Okay, both are negative actually. I could have taken the negative sign outside. Negative anyways would have become positive. Okay, yeah, this will be minus will become 1, j square will become minus 1. So this will be basically minus root 3 divided by 2. So this will be overall 1 by 3. Okay, what is this? 3 plus 1 minus root 3 by 2. So this is actually 4 minus root 3 by 2. Okay, so 4 minus root 3 by 2, then j5, and yeah, j5 this is j by 2, so this will be j 11 by 2, and root 3 is also there, so plus j 11 by 2 plus j root 3. Okay, then this will be plus minus 1 into 1, so minus 1, then this will be plus j root 3. Okay, plus j root 3, right, then this will be minus j, and this will be j square root 3, so minus root 3. Okay, okay, so this is like a bit complex, but I hope you guys will be able to solve it, right? So this will be equals to 1 by 3, okay, 4 and minus 1 is there, so this becomes 3, and this is minus root 3 by 2 minus root 3, so this becomes minus 3 root 3 by 2. Okay, minus 3 root 3 by 2, we get this value. And what else do we get? So this will be plus, okay, now I will take the, so real components I have taken, I will take the imaginary components. So j 11 by 2 minus j is there, so minus sorry, plus 9j by 2 will be there, right? So plus j root 3 is there, plus j root 3 is there, so this will become plus j 2 root 3. Okay, this will be the like imaginary component. And now if I divide this, right, if I divide this, what will I get? So I will divide this by 3, right? So 3 I can take common, except this one, I can take 3 common, so this value will come out to be like 1 minus root 3 by 2 plus j 3 by 2 plus j2 divided by root 3. Okay, so I will find the values, basically find the values of this component. Okay, let me find out the values. Okay, so this will be root 3 divided by 2, this is negative, right? Am I correct here? This is minus 1, so 3 is here. Is this negative is correct? Huh? Negative 1, yeah, this should be negative only, this should not be plus. Yes, so this comes out to be this plus 1, so this comes out to be 0 0.133134. What about the imaginary component? So imaginary component is 3 divided by 2 plus 2 divided by root 3. Okay, so this comes out to be j 2.654. Okay, so this part is correct. I'm just checking whether this component, right, I have added this correctly or not. Minus 2 minus j, yeah, minus 2 minus j is there, yeah, minus 2 minus j irYB, yeah, minus 2 minus j is there, minus 2 minus j, this will become plus 1 j square, right? J square is minus 1, so minus root 3 by 2, yes, correct, minus root 3 by 2 plus j root 3, then j by 2, then plus 1. Okay, so yeah, this will be the IA1. So if I calculate this in like a polar format, this whole square plus 0.134 whole square whole under root, so this comes out to be 2.658 angle 2.654 divided by 0.134 tan inverse, so it comes out to be 87.11 degrees. Okay, 87.11 degrees. This is my IA1, what about IA2? So IA2 will be again, it will be 1 by 3. The calculation will be difficult now. Okay, so 1 by 3, and it will be IA plus alpha square into IB. So IA, is there any lag here? No. IA plus alpha square into IB plus alpha into IC. So which will be equals to 1 by 3. IA is, okay, let me copy the currents actually, because I will not go back here right again. So that's why symmetrical components is a lengthy one, because it's an unbalanced system, right? So it becomes bit lengthy. So 3 plus J5 plus alpha square. So alpha square again, it is in the third quadrant. So this will be minus half minus J root 3 by 2. Okay. Okay. And this will be IB. So IB is this fellow, right? This fellow. So 2 plus J2 plus alpha, that is minus half plus J root 3 by 2 minus 2 minus J, right? Okay. So this will be equals to 1 by 3 3 plus J5. So 2 will get multiplied, so this will be minus 1 plus J root 3 into 1 plus J. Okay, plus okay, so this will be basically, if I just like simplify this, minus I can take common, right? No, minus, this time I cannot take minus common. So this will be half minus half into minus 2, so this will be 1 minus half into minus J, so this will be plus J by 2. Okay, this will be minus J root 3, wait, plus J by 2, and this will be plus root 3 by 2. Okay, so this will be 1 by 3. So here it is 1 plus root 3 by 2, so this will be 4 plus root 3 by 2, so 4 plus root 3 by 2 and plus 11 by 2J minus J root 3, and this will be what? This will be minus 1 and J root, right? So this will be minus 1, so minus 1 minus J plus J root 3 minus root 3. Okay, so this will be equals to 4 minus root 3 by 2. Okay, also there is minus 1, so this will be 3, right? This 4 minus 1 is 3 minus root 3 by 2. 3 minus this is root 3 by 2 and I am subtracting root 3. So 3 minus root 3 by 2 plus, I have a minus 1 here, so this will be plus 9 by 2. Sorry, oh sorry, minus 1 is not there, sorry, minus j is there, right? So this will be plus j plus j 9 by 2 and minus j root 3 plus j root 3 will get cancelled, so only this will be left, right? So from here the value will be 1 minus 1 by 2 root 3 plus j 3 by 2, okay, j 3 by 2. Okay, so this value will come out to be, if I calculate this value, okay, I am dividing by 3, I have divided by 3, it is correct only. So j root 3 minus j root 3 cancels out. So 1 minus, so 1 divided by 2 divided by root 3 minus 1. So this is 0.711 plus j 1.5, right? So now you will calculate the polar format. So whole square plus 1.5 whole square whole under root. So it is actually 1.66 angle. So 1.5 divided by 0.711 tan inverse 64.64 degrees. Okay, so it's long, it went long. So this is my IA2. So these are the components, basically these are the sequence components, and from this you can find out the other components, right? Other components you will be able to find out. So I have found out IA0, IA1, IA2. Okay, I hope it is clear, like how to find and solve for it, right? So now let's like this is one of the ways, like this is one of the like this will not be asked in gate, right? But it's good to know how to find out and do the calculation. So if you do more practice, right, this complex calculations, there will be less chances of errors happening. Okay, so let's see one, like what kind of questions gate examinations, like gate examiner ask, right? So we have a system, unbalanced three-phase system that they're telling me, whose phase current is IA is this, negative sequence currents IB2 is given, zero sequence current IC0 is given. The magnitude of the phase current IB will be what? So what is my IB equals to? So IB is equals to IB0 plus IB1 plus IB2, right? Now they've given me the phase current IA. Okay, the phase current IA is given to me. So actually this is not that simple if you think, right? So basically the phase current IA is given to me. So if phase current IA is given, what is IA is equals to? IA will be equals to also IA0 plus IA1 plus IA2. IB2 is given to me, right? IB2 is this. So what will be IE2? So I know IB2 is the negative sequence current. So if it is the negative sequence current, I know A will be here and B will be here. So if I have to go to A from B, what will I multiply? I will multiply alpha square, because I have to go clockwise direction 120 degrees. So I will multiply alpha square. So IA2 will be equals to alpha square into IB2. IA2 will be equals to alpha square into IB2. Okay. So it will be alpha square. So I have to basically go in the clockwise, subtract 120, right? So it is alpha square is what? 1 angle minus 120, correct? So IA2 will be 4, magnitude will not change, this will become minus 270 degrees. So minus 270 degrees is, if I add 360, it will be 4 angle plus 90, right? Which is basically J4, right? And this is what? This is basically minus J. It is basically minus J, right? Minus 90 is there. IC0 is given. Okay, IB2 I am able to find out. IC0 is given as 3. So they will give easy calculations. They will actually give very easy calculations. So IC0 will be equals to IA0, that will be J3. Okay, so that will be J3. Now will I be able to find out IA1, right? Because ultimately I have to find out IB. For IB I need IB naught, IB1, IB2. So I know what is my IB naught, that is this one only. I will be able to find out IB2 because that is given. I just need IB1. For IB1 I will find out IA1 with this equation, and then I will use the operator, alpha operator, right? So here if I put the values, IA is given to me as minus of J, IA is given to me as minus of J, IA naught is given to me as J3, IA1 is the unknown that I need to find out, IA2 will be plus J4, right, as I have found it out over here. So your IA1 will be equals to IA1 will be equals to so minus of J8, it will be minus of J8. So I will what will be my IB1? So it's a positive sequence current, right? So B will lag the A. So if my A is here, B will be here for the positive sequence. So I have to multiply just a alpha with IA1. So if I multiply alpha, that is 1 angle 120, right? So this will be 8 angle minus 90 plus 120. So it will be 8 angle minus, sorry, plus 30. It will be 8 angle plus 30. Okay, that is what your IB1 will be equals to. That is what your IB1 will be equals to. So which I will replace in this equation. So IB I will be able to find out. So they are asking me what? They are asking me a magnitude of the phase current, right? IB. IB will be this IB0. IB0 is same as IC0, that is J3. This will be J3 plus IB1 that I have just computed, that is 8 angle 30 plus IB2. IB2 is given to me, that is this value, right? IB2 is given in the question. Sorry, IB2 is given in the question here. 4 angle minus 150. 4 angle minus 150. 4 angle minus 150. So this, right, we have to actually add. Do we have any solution here? Yes, one kind of solution is there, but these magnitudes are different. So no, there is no solution. We have to simply use the phasors. That is the only solution. Not phasors, so simply convert it into rectangular format. So this will be J3 plus cos 30 into 8, 6.9 3. Okay, cos 30, 8 into 6.93 plus J, so sin 30 into 8, so this is J4. Of cos 150, right? Cos 150, that is it is minus 150, so minus 150 won't matter actually, it will be same only. So this is root 3 minus root 3 by 2. This will be minus 150 sine, which will be minus half G. Okay, so this will be 6.93 plus J7 minus 2 root 3 minus J2 is equals to, so this will be, so 6.93 minus 2 into root 3, so this is 3.466 plus J, so this will be J5 plus J5, right? So what will be the magnitude? 5 square plus 3.466 whole square whole under root. Okay, somewhere I've messed up because the answer is not correct, right? Okay, minus 2 root 3, okay, negative IB2 is given to me, right? Yeah, this is my IB2, correct. Okay, IB1 I've just found out. IB1 will be, oh, sorry. I'm really sorry. What have I done? Sorry. What have I done? No, IA2 is correct. This is also wrong, right? So I from IA1 I have to go. Okay, no, this is correct only, right? Because I have to move in the clockwise direction. No, this is correct only. It's correct only. Oh, sorry, this will be minus 120, right? If I'm moving in the clockwise direction, so this will be alpha square. Sorry, I'm moving in the clockwise, right? What am I doing? Yeah, this will be alpha square. Sorry. This will be alpha square. I'm moving in the clockwise direction, right? Here also I was moving in the clockwise direction. That's why I multiplied alpha square. If I was moving in the anti-clockwise, then I have to multiply by alpha. This will be alpha square actually. So this will be minus 120. So this will be actually this will be minus 210. Okay, or this will be 150. You can write 8 angle 150. That also will work. Okay, I'm sorry for that. So this will be 8. Okay, this will be 8 angle 150. Will that help any way, shape, or form? Actually, this minus 210 is fine. Minus 210 is fine. Why is it fine? I will explain just in a second. Okay. So this is minus 210, right? So I can break this down into two components. This will be J3 this will be J3 plus 4 angle minus 210. What is 210? 210 is also plus 150, right? I'm just adding 150. 210 is also plus 150. So this I can write as plus 150 because adding 360, subtracting 360 with angle does not make any difference. So this I can break it down into two components. One will be 4 angle plus 150. This is 3 angle 90. Why am I doing this? I will explain. This will be 4 angle minus 210. So what I have done? So this 8 angle minus 210 will be 4 angle minus 210 plus 4 angle minus 210. So one of the component I have written as plus 150, other component I have kept as minus 210. Now I will add here 4 angle minus 150 degrees. Okay. Now will I be able to simplify this further? So I know this, that this will be what? These are two vectors whose difference of phase is 60 degrees and whose magnitude are same. Then what will be the overall magnitude? Overall magnitude of this will come out to be root 4 root 3 and whose angle will be the bisector. So it will be minus 180. That's it. Okay. Plus now here these two magnitudes are actually not same. These two magnitudes are actually not same. So I can make them same, right? So what I can do, I can again further break this into two components. One will be 3 plus 150. Another one will be plus 1 angle 150. Okay. So 1 angle 150 I will keep as it is. And the other component will be, so here again if I see there is a phase difference of 60 and both of them have same magnitude. So this will be 3 root 3 angle 120. Okay. Now does this help me? No, after this it will not help me. I was thinking maybe I will be able to simplify, but it seems our luck has ran out. Okay, we will not be able to simplify this further, so we will we'll have to solve it just like normal guys. Okay, so 120 cos will be basically minus half, so this is 3 by root 3 minus, okay, and sine of 120 is root 3 by 2 minus sine of 120, right? So minus root 3 by 2. So this is not minus, plus 128. Sorry, plus only. So this will be plus j 9 by 2. Okay. So yeah, what will be this value? This will be 150 cos So minus root 3 by 2, 150 sine plus j by 2. And this is simply minus 4 root 3, right? This is minus 180. So this is simply minus 4 root 3. Okay. Okay. So here I have root 3 by 2. Right here I have 3 minus 3 root 3 by 2. So actually this becomes minus 4 root 3 by 2. So minus 2 root 3. Minus 4 root 3 is here already. So this becomes minus 6 root 3. Okay. And this is plus j by 2 plus 9 by 2. So which is actually j5. So this will come out to be 5 square plus 6 into root 3. 6 into root 3 whole square plus 5 square whole under root, which comes out to be 11.53. I was thinking that I will do some trick, right? But gate did not allow. Right? So there is bit of calculation involved. So you have to be good in complex calculation. What is the angle? They have anyways asked the magnitude, so you have got your answer. This is the answer, right? But I want to calculate the magnitude as well. So magnitude will be 5 divided by 6 into root 3 into 5 into tan inverse 25.69. And remember, your x is negative, y is positive. It is in the second quadrant, right? So if it's in the second quadrant, it will be 180 minus theta. Okay, 180 minus theta. 180 minus theta. So this will be plus 180. So angle will be 154. 154.3 degrees. Okay, this will be your answer basically for this question. 11.53. Okay, let's now solve this one. So with this question, we will like understand a very critical point, that they are asking me to find out the positive, negative, zero sequence components of the current, right? Don't worry, this will be not lengthy, this will be easy. This will be actually easy. So now I will directly write the matrix. So first of all, 1 by 3 will be there. I know for B, so this 1 1 1 1 1 1 will be here. Okay, that will be there. I know for B, my B component IB1 is supposed to lag the IE1, right? So it is alpha square, but this is the other matrix, so alpha square gets replaced with alpha, so we write here alpha. So next is easy, right? So here alpha square will come, here alpha square will come, here alpha will come. So only this element you have to remember, others automatically is done, right? So only one element you have to remember. Okay, so this here I will have IA0, IA1, IA2. Sorry, this is wrong, right? So this will be IA, IB, IC, and here IA0, I1, I2. Okay. What will be your IA0? IA0 is always easy, right? It is just the sum of the all three components divided by 3. So it will be IA plus IB, all the phase currents divided by 3, IC. So this will be equals to 1 by 3. If I add all these three, what are you able to notice one thing? Are you able to notice one thing? So here I am able to notice that all the magnitudes of IR are same. All the currents magnitude are same. Also, I know if my R is here, my Y will be here, right? Y will be here. It lags the, so R is here somewhat plus 30, right? So Y is somewhere here, okay, and B is somewhere here. So it is basically a balanced system, right? So I know the addition will always be 0, right? Addition of the three balanced components will always be 0. So this will come out to be 0 only. I don't have to solve, this will be 0. What about the other components? What about IA1? So IA1 will be equals to 1 by 3 IA plus alpha into IB plus alpha square into IC. So IA is IR, that is 5 angle 30 plus alpha into IB, alpha into IB. So alpha into IB, so alpha is 1 angle 120. If I multiply it, this will become 5 angle 30 basically. Alpha square into IC, alpha square is minus 120 into this, so it is 30 again. Magnitude does not change, so this will be plus 5 30. So do you notice anything? So it is basically equals to 5 angle 30. So your positive sequence current is actually equals to the IR itself. What about IA2? IA2 will be 1 by 3. IA, this time it will be alpha square into IB plus alpha into IC. Now I know you will say, sir, this is RYB, why are you writing IABC? So I hope that is understood, right? I will not change all this. This is like very basic thing. इसमें कंफ्यूज मत होना यार, इसमें बोलना कि पता है यार, ये पता है, ये दिस इज RYB. Okay, इसमें कंफ्यूज प्लीज मत होना. Okay, don't get confused in this, that whether this is ABC or RYB. This is like, it's understandable, right? This is RYB. I'm writing this as because I'm accustomed to write ABC, but that is understandable that RYB and ABC are interchangeable. Okay, so this will be equals to 1 by 3 IA is 5 angle 30. Now alpha square IB, what will be alpha square IB? So alpha square will be minus 120 times this. Minus 120 will be, this will be 110 minus 210. Okay, minus 210. So this will be 5 angle minus 210 plus 5 angle 150. So it is like, it is alpha into IC, that is plus 120. Plus 120 is 270, right? Plus 120 is 270. Okay, so yeah, so now how will I add it basically? So one thing you notice, do I notice anything? Okay, if I subtract here 360, what will I get? This will be, if I subtract 360 and add 360, so let me see if I can bring something. So this is 5 angle 30 will be staying here. I will add 360. This is not looking good, so I will add 360. So this will be 5 angle 150, and this will be, I will subtract 360 with this, right? If I subtract 360, this will be 5 angle minus 90. So are you observing anything? So here there is a phase difference of 120. Here there is a phase difference. Is there a phase? Okay, no. Here there is a phase difference of 120, right? And between these two, they have a phase difference of 240, right? Is it 240? If I subtract, yeah, if I subtract 120, it will be 30. Another 120 I have to subtract. So 20, 100, yes, correct. So basically it is a balance. It is forming a balance addition, right? I know the balance addition will always be equals to 0, right? So this will be equals to 0 simply. So conclusion is that my sequence components will be 0 if the system only consists of balanced currents, right? So if system is balanced, then only positive sequence components will exist. Okay, only positive sequence components will exist. So that is the case. So other components, so basically the conclusion is negative sequence components and zero sequence components will be equals to 0. Okay, so I hope this conclusion is done. So one more conclusion I want to one more key observation I want to say, that we know that our zero sequence component, right, IA0, IC0, all of them are same only. IA0, zero sequence current is actually 1 by 3 of sum IA plus IB plus IC. Okay, yeah, that is the thing over here. Okay, so yeah, okay, next we know this, right? So basically for a balanced system, this IA plus IB plus IC will be 0, right? So there will not be any neutral current. But basically if I see a star connection at this node, if the system is balanced, then there will not be any neutral current. So this is similar, it is similar, this is the basically the neutral current, right, IN. So what do I mean? So if I don't provide, if I keep the neutral open, so if neutral is open, that means my IN is 0, it is open circuit, no current will flow. If IN is 0, that means my zero sequence current has to be 0. So there is no path for zero sequence current to flow. Right? So if neutral is not grounded, zero sequence current won't exist. Okay, so important point, I am talking about currents over here, right? So if neutral is grounded, zero sequence current won't exist. Okay, sorry, if neutral is not grounded. Do you remember any similarities? So the behavior, if you remember, is similar to third harmonics. So third harmonics also, all the phase currents were equal in third harmonics because the phase difference was 360. Remember, right? So the behavior, another key observation, but they are not same. Zero sequence current and of course third harmonics are different. But one more key point, behavior of third harmonic currents and zero sequence currents are almost are similar, not almost similar. So if there is no path for the current to flow, then where did it go? What is it? This should be where actually. I think this came by mistake, right? This will not be here. Oh, sorry, this is IA. If behavior of third harmonic currents is similar to zero sequence current. Okay. So I hope it is clear that behavior of third harmonic currents is similar to zero sequence current. Okay. One more thing about delta. So for delta, we can talk about zero sequence voltage in line. So what is the okay, yeah, what about one more thing, one more key observation for star only we can discuss. One more key observation, this was about the current. Now let's discuss about the voltage. Let me copy this. Okay, this was about the voltage. So what is the line voltage here? VEB. So VEB will be equals to VA minus VB. So if I assume that the line voltage that the phase voltage has zero sequence component, if I assume that, right? So if I assume phase voltage has zero sequence component, right? So VA is equals to VA0 plus VV0, sorry, VA1 plus VA2. Similarly, VB also will be equals to A0 plus VB1 plus VB2. I'm not writing here alpha, all those things. Okay, not interested in that. So what will be VAB? So VAB will be equals to VA minus VB. So VA0 automatically will get cancelled. VA1 minus VB1 will be there. VA1 minus VB1 plus VB2 minus VA2 minus VB2. So what is the key point? Key point is there is no zero sequence component, right? This is the positive sequence component, like whatever I will subtract and add, this will be the positive sequence component, this will be the negative sequence component. So there cannot be any zero sequence component for voltage. So line voltage in star, right? In star, line voltage in star, zero sequence component, zero sequence component cannot exist. Cannot exist in line voltage. Okay, so this is also another key important point about the star connection. So in line voltage, 0 seconds component will not exist. What about the current? So neutral current, if neutral is not grounded, 0 seconds component of current cannot exist. Neutral has to be grounded for 0 seconds component to exist. Otherwise, where will the current flow, right? 0 seconds component, where will the current flow? It needs a path. So neutral must be grounded. It does not matter whether it is solidly grounded, grounded through a resistor or something. It does not matter, but it must be grounded. Okay. So here as well. Now for delta, I can just do the opposite analysis for currents. So what is the line current, phase current here, right? I A phase, right? What will be the phase current? So phase current will be basically equals to, sorry, what will be IA current? So IA current will be equals to IAP plus, here let's say this is the current, this current is incoming, IBP. So my IA will be equals to what? IA will be equals to IAP minus IBP. So IA will be equals to IAP minus IBP. Okay, IA will be equals to IAP minus IBP. Same analysis, same ditto analysis. If you assume that phase current has 0 sequence component, so same analysis like the previous one, because here there is subtraction. So I will directly write the observation that if phase currents have, so in I will write in delta, if phase currents have like basically the crux is, sorry, in delta, 0 sequence component, 0 sequence component of current won't exist zero sequence component of current won't exist, right, in line currents. The reasoning same as the previous one. Okay, what about the, like, so if zero sequence component exists in the phase and it does not exist in the line, where will the zero sequence component current flow? So I know in case of zero sequence component, I know this thing, that like this is the direction of IAP, this is the direction of IBP, and this will be the direction of ICP, right? And I know all of these components will have a zero sequence. So IAP will be equals to IA0, like there will be a zero sequence component of IAP, that will be equals to the zero sequence component of IBP, that will be equals to the zero sequence component of ICP, right? So here I observe the zero sequence component of IBP will flow in this direction, the zero sequence component of ICP will flow in this direction. So basically what, and I know these are equal, so whatever current is coming here, same current will go here. So basically what is happening, there is a circulating current that is flowing in this loop, that is known as IC. So the zero sequence current will flow through the loop, it will flow through the loop, it will never enter the line. So from this, so basically if in delta, 0 sequence component, zero sequence current flows in a loop through the phase through the phase called circulating current. Hence, do not enter the line. Okay, so they do not enter zero sequence current, do not enter the lines of delta. Okay, this was about the zero sequence current. Voltage I am not discussing because the line voltage and phase voltage are same. So there can be zero sequence component of the line and phase voltage. Okay. So I hope it is clear now. So last part we will do today, that is the complex power. After that it will be done. So power derivation in case of a symmetrical component, right? What will be the power equation basically? So how do I find out the power equation? So I know power is equals to VI conjugate. Okay, I know power will be equals to VI conjugate. I know voltage will have three components, current will have three components, right? Voltage will have three components, current will have three components. So it is a the normal formula for power. I know power for a three-phase system, right? It will be VA into IA conjugate. Like if it is unbalanced, if all the voltages are not equal, VA into IA conjugate plus VB into IA conjugate, IB conjugate plus VC into IC conjugate. Okay, so VA into IA conjugate, VB into IA conjugate, VC into IA conjugate. Okay, so can I write this down in a different manner? Can I just write this down in a different manner? So I can write this in the form of matrices, right? I can write this in the form of matrices. So this will be equals to VA, VB, VC. This will be multiplied with IA, IB, IC. Okay, IA, IB, IC. So yeah, that is clear. Now, what is VA, VB, VC? If I want to write this, right, and what is IA, IB, IC? So this conjugate I can take outside. Conjugate I can take outside, whole conjugate, right? This will still be valid. So do you remember this? What was IA, IB, IC equals to? So your IA, IB, IC, if you remember, IA, IB, IC was this matrix, right? It was basically, if I want to write this in terms of symmetrical components, this will be 1 1 1 1 1 1. Here first alpha square will come, then alpha will come, right? Because it lags by 120. Okay, so this will be alpha alpha into IA naught, IA naught, IA1, IA2. Okay, this was my components of current basically. What was the voltage? So voltage, right, this I can actually rewrite in terms of this. So I can take this because I want my actual format. So I can write it like this whole transpose into the other matrix. Okay, because I want to get to a proper format, that's why. Like this proof is not important, just understanding the final result actually is important in this case. Okay, so in this case this will be equals to, what is my VA, VB, VC? It is the same, right? This matrix will be same. This matrix will not change. This will be same. Okay. So now here, now I can put this, right, this here, I can put this one here. Okay, so this will come out to be this whole thing whole conjugate, right? So if I copy this thing and take the conjugate, I will do it. This whole thing conjugate, so not conjugate, transpose, and this whole thing I will copy and take the conjugate. Okay, so now you have to remember the property of A conjugate. What is alpha? So not A conjugate, what is alpha conjugate? So alpha conjugate is what? It is basically alpha is plus 120, it becomes minus 120, which is alpha square. So alpha conjugate is nothing but alpha square. Okay, so if I take the transpose, like if I take, there are two matrices A, B, and if I take the transpose, the result is B transpose A transpose. I hope these properties of matrices are clear. And if I am taking the conjugate will simply come inside. That's it. So what is alpha square conjugate? So alpha square conjugate, right? If I conjugate this whole equation, this will be alpha square conjugate. This will be alpha conjugate conjugate. That is simply alpha. So alpha conjugate is alpha square. Alpha square conjugate is alpha. Okay, it's just the property. So this I can write. This will be what? VA0 VA1 VA2 whole transpose, and this whole transpose, right? This whole transpose will be 111 111 transpose. Transpose means rows will be column, so this will be row and this will be the this will become the second column. Okay, if I take the transpose, right, this will come here, this will come here, 1 alpha square alpha, this will 1, sorry, this is alpha square, right? Alpha square, sorry, alpha square yeah. So yeah, if I take the transpose, this transpose is same, this will not change. This A transpose is it same? A transpose is same only, right? If I take the transpose of this, it is same, yeah, because yeah, it is symmetrical matrix, it is almost, it is symmetric matrix, right? Yeah, it is symmetric matrix. So A transpose will be same. This will be alpha square alpha 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 square, right? Multiplied by this value. So 1 conjugate, it's a real number, so 1 conjugate will be 1 only, so these will be 1, right? 1 1 1 1 1 1. Okay, now what will be alpha square conjugate? Alpha square conjugate will be alpha. What will be alpha conjugate? Alpha conjugate, we have written it, it is alpha square. Alpha square conjugate is alpha, alpha conjugate is alpha square. This will be alpha square. So basically they will reverse their places. This will become alpha square, this will be alpha. Now this is simply IA conjugate, IA not conjugate, IA not conjugate, vector is there, IA1 conjugate and IA2 conjugate. Okay, so the thing is, do you remember, is this something familiar? It is, this is just the inverse, right? But extra 1 by 3 term used to come, right? The inverse of this was, if this is A, this is supposed to be A inverse, but here extra 1 by 3 term should come, right? So what I will do, I will actually multiply and divide by 3, right? So to make it A inverse. Okay, so this whole thing becomes A inverse. This is A and 3 can come outside, right? 3 is just a scalar, so 3 can come in front. So this is equals to my complex power, basically I forgot to write, this is equals to my complex power. So my complex power S comes out to be this value, 3 into VA0 VA1 VA2. Now it is A into A inverse, right? A inverse is just identity matrix, and I have here IA0 conjugate, I1 conjugate, IA2 conjugate. So what will this come out to be? So this is simply VA0 IA0 conjugate, VA1 IA1 conjugate, VA2 IA2 conjugate into 3. So like the conclusion is, crux is, your 3 phase power is basically 3 times the individual power components, right? Individual positive sequence current, positive sequence power, negative sequence power, and zero sequence power. So I can write here, so I can write actually here your S, right, complex power is equals to 3 into VA not IA not conjugate plus VA1 I1 conjugate plus VA2 I2 conjugate. Okay, so basically what I can say, this is the what, this is the zero sequence complex power. This is the positive sequence complex power. Negative sequence complex power. Okay, and so basically my complex power overall three phase complex power is equals to the individual complex power multiplied by 3, of course, because this was only the single phase complex power. I have to multiply by 3, right? So very important relation that can get asked in GATE examination. Okay, so yeah, I hope it is clear now. I hope everything is clear. So we have solved this question. So today we are done with symmetrical components. In the next lecture, we will be discussing about sequence network. So we will divide our circuit. So circuit also will be divided. So star, delta, all those things will be divided. Alternator also will be divided. So we will discuss that in the next lecture. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. So today we will be covering regarding sequence networks. So in the previous lecture we covered, like, I can break down my unsymmetrical like unbalanced system to three symmetrical components, three balanced components. So we will break down our network as well into three balanced components to do the per phase analysis. So sequence network will help us do the per phase analysis. Okay, so first of all, let's take the example of a star connected winding. Okay, it's a star winding with a neutral grounded. I will say what happens if neutral is ungrounded. So if neutral is not grounded, I know if I am providing, let's say, voltage VAB here, like phase voltage will be here, VA, here there will be phase voltage VB, here there will be phase voltage VC. Okay, so VABC, these are the voltages basically. So now what I can do is I can break this down, because I know my VA is a combination of VA0, VA1, VA2. So what happens if I just apply the positive phase sequence? So first of all, we will see what happens if I just apply the positive phase sequence. So positive sequence component. So I can break it down, right? I can use superposition. So we will use superposition here, where in one case I will consider only the positive sequence components. Superposition, positive sequence components. So positive sequence components will be this, right? This will be here. I will only apply the positive sequence component voltage VC1, VA1, VB1. One more assumption we will take, that the impedance provided by the winding changes depending on what kind of sequence voltage I am providing, right? So for if I provide positive sequence voltage, the impedance will be Z1. If I provide negative sequence voltage, the impedance provided by the winding will be Z2. If I provide zero sequence voltage, the impedance will be Z0. Okay, most cases they are same only, they are same, equal, but we will assume that if I'm providing positive sequence voltage, the impedance will be Z1. Okay, that's our assumption. Okay, so the impedance will become here Z1. This Zn will not change, Zn will be same only. So here also it will be Z1, impedance of the winding, star winding. Here also it will be Z1. Now can you do the analysis? So what will be the current flowing through? If I am applying a positive sequence voltage, what will be the current? Current also will be what? IA1. This will be IC1. This will be VV1, IB1, right? So what is the neutral current? Can you tell me what is the neutral current here? Neutral current will be the sum of all these three currents, correct? So my IN will be equals to IA1 plus IB1 plus IC1, and I know, of course, it's a positive sequence component, so it's a balanced system. I know addition of these three components will be simply 0. So the important conclusion is your IN is 0. That means the drop over this impedance is 0, right? So if the drop over this impedance is 0, that means this point will be grounded. Okay, this point will be grounded. Okay, so drop is 0, this point will be grounded, right? Now the important point is uh, the important point is uh, if the drop is 0, then what is the equivalent per phase equivalent impedance? What is the per phase equivalent impedance? It is Z1, right? Per phase equivalent impedance is simply Z1, because there is, like, neutral is anyways grounded, it is grounded. So between this point, between the point A and the ground, what impedance am I seeing per phase? So between point A and ground, I am seeing Z1 impedance here, because this is grounded. So this point becomes 0. So actually this is the ground, but as there is no drop, this becomes ground. Between point B and ground, between point B and ground, what impedance I am seeing? Z1. Between point C and ground, what impedance I am seeing? Z1. So the per phase equivalent of positive sequence component will be Z1. Okay, so if I want to replace my per phase equivalent of the positive sequence component, it will be simply Z1, that's it. Okay, so this is the per phase equivalent, right? So this is basically the ground, and this is my Z1. Okay, so I hope this one is clear, this part is clear to you. Now let's do the same analysis for negative phase sequence component. So it will be same, right? There will not be any difference, because all the equations are same, it will not change. So again, for a negative phase sequence component, right, for a negative phase sequence component, negative sequence component, if the currents are negative, if the voltages are negative, right, this will be what? This will change to VA2, VB2, VC2. Okay, and this currents will become now what? Negative sequence component current. And the impedance will become basically Z2 now. It will not be Z1 anymore, it will be Z2. Okay, so it will be Z2. Currents are IC2, IA2, IB2. Okay, and the impedance will be Z2, Z2, Z2. Okay, so what will be the, it's the same, right? So again, what will be your neutral current? It will be IA2 plus IB2 plus IC2, IA2 plus IB2 plus IC2, which is again 0, because it is again symmetrical, but in the opposite phase sequence. But it does not matter, phase sequence does not matter. Ultimately the neutral current is 0, then again this point will be shifted to ground, this neutral point will be shifted to ground, right? So again the same analysis, the per phase equivalent will be Z2. Okay, what about the 0 sequence? So here you need to listen to me very carefully. So basically what I'm doing, I'm measuring the impedance between point A and ground. Per phase impedance means what? Measuring the impedance between one of the phases and the other ground. So in this case always it is Z2. If you measure for any of the one of the phases and ground, it is always equals to Z2. Now what happens if I'm applying 0 sequence component, right? 0 sequence, things will change now. So be attentive. Okay, so if I copy the circuit, I know I will for a 0 sequence component I will apply 0 sequence voltage, VA0, VB0, VC0. Current will be VA0, VC0, VB0. What will be the neutral current now? So the neutral current will be equals to IA0 plus I B0 plus IC0. Okay, so neutral current is IA0 plus IB0 plus IC0, and we know all of them are equal. I know for a 0 sequence component your IA0 will be equals to IB0 will be equals to IC0. Why? Because your voltages are also equal, so currents also will be equal because the potential here is VA0, right, between each phase. Okay, now as it is 0 sequence component current, okay, is the VA0 VC0 will directly come? No, actually no. So in this case the VA2 is actually applied between these 2 points, right? Basically VA2 is actually applied between phase A and neutral, right? That is where my VA2 is applied. So in this case we can actually reduce the VA2 to here because neutral is grounded, so VA2 is actually applied here. In this case also VA1 is actually applied between here. I will have the neutral and here I will have the phase 1, right? So this is where the VA2 is applied, VA1 is applied, but actually as this system is balanced, so simply I can like it will be actually across this phase because it is this point is ground, right? Same for VA2, but this, right, VA0 is not applied here, VA is not directly applied here. VA is actually applied between this and the VA0, between this and the neutral, and this time this point is not the neutral, this is the ground. So VA0 is actually applied between these, VA0 is actually applied between this point A, point B, C. So VA0 is applied between point A and the neutral. Okay, now this point is not the ground, sorry, not the neutral, sorry, neutral is this point. VA0 is applied between this point and ground. Previously same VA1 was actually applied between phase A and the ground, but as there was no 0 sequence current, sorry, as there was no neutral current, that's why the ground was here because there was no drop here, right? So VA1 effectively was applied along about Z1. Same here, right? VA2 was effectively applied between point A and the ground actually, but in this case as well there was no neutral current, so there was no drop, so this ground got shifted here. So this is my VA2 basically. This is my VA2. Okay, I directly applied it across Z2. Now what about VA0? Okay, what about VA0? So VA0 will be, I have to decide what about VA0. So VA0 here, right, VA0 is applied between point A, phase A and the ground. Now I know VA0 is 0 sequence component voltage, due to that some 0 sequence component current will come, IA0, IC0, IB0. Now I know what will be the neutral current now. So neutral current will be 3 IA0 because all of them are equal, so I have assumed them to be IA0. So current through here is 3 IA0. Current through here is 3 IA0, right? So basically what is effectively happening is what am I applying across VA0? Like I'm applying VA0 If I just consider the phase A voltage, I'm applying VA0 between this point A and the ground. So effectively, what is the drop here? This will provide Z0 impedance, right? So this drop will be Z0, right? Because this is what? Let me write the KVL. Let me write the KVL, right? First, then you will understand. Let me write the KVL. So KVL will start from ground, right? So this point is the minus VA0 point. KVL will start from here, minus VA0, this drop, and then end to ground. So I am applying a ground to ground KVL, right? So if I write the KVL equation, minus VA0 plus IA0 plus IA0 into Z0 plus 3IA0 into Z0 equals to 0, right? That is sorry, into Zn equals to 0. That is my ground to ground KVL. So if I find out the ratio of VA0 upon IA0, what do I get? VA0 upon IA0, actually this time it comes out to be Z0 plus 3Zn. So the Zn impedance now gets multiplied. So basically the per phase equivalent impedance is Z0 plus 3Zn. Here also if I do the same analysis, right, you will observe the same thing. So here VA1 is here, right? Again ground to ground KVL. This is ground now. This is ground. So again if I apply the KVL, same thing if I do, right, you will see that minus VA1 then plus IA1 into Z1 equals to 0. So my Z1 equals to VA1 divided by I1, okay, V1 divided by I1, that is what my Z1 is. So same thing I've written, sorry, not Z1, sorry, my V, sorry, yeah, same thing only. So V1 divided by I1 is equals to Z1. So per phase positive sequence equivalent impedance will be Z1 only. So that is what is present over here. So here is my V1 and here is my I1. What about here? So here again the same, if I apply the same KVL here, same procedure, right? So minus VA2 plus IA2 into Z2 will be equals to 0. So again your VA2 by IA2 will be equals to Z2. Okay, this is what my VA2 by IA2 is equals to. It is equals to Z2, right? Same procedure if I apply, I am getting VA0 by I0 is Z0 plus 3Zn. So this time the per phase equivalent will be, I will have a Z0 here. Okay, actually I should not make coils, I should actually make impedance. If you make coils, right, you will think that it is just a that's my bad, I should have not made a coil, right? It is just an inductor, right? That's my bad. So I have already made a mess. Please, okay, I have to change all this. That will be okay. Let me change. If I change all this, that will be difficult. So I hope you understand that coils, basically here coil is not coil, coil is impedance. Okay, coil is not inductor, it is a impedance. That is, I hope it is clear. Okay, so here in this case for the zero sequence component, the per phase equivalent will be, you can do the same, you can apply the same KVL for other phases as well. You will observe that I am getting first of all a Z0 impedance, then I am getting a 3Zn impedance, and then that is connected to ground, right? So this becomes 3Zn. So basically the thing is, sequence components are same, right, for positive phase sequence and negative phase sequence per phase impedance, but just for the zero sequence component, the neutral winding gets added in series with the zero sequence impedance multiplied by 3. Okay, so the per phase equivalent sequence network for star. Sequence network for star. So what will be the sequence network for star? Sequence network for star will be equals to this will be the positive sequence component Z1, this will be the 0 sequence component Z2, and this will be the, sorry, not the 0, negative sequence components, and this will be the 0 sequence component Z0 plus 3Zn. Now if it is solidly grounded, Zn will be 0, okay, 3Zn. Now how will you solve the circuit basically? So you will first of all break it down to 3 components: VA1, like the voltage, VA2, VA0, and then you will find out the currents IA1, IA2 and IA0, right? And then you can find out the overall IA current. So you cannot directly find out IA current, you have to individually break it down, okay? That is what you have to do, right? So there is a special case, right? So if Zn is 0, if so, let me write, this is the positive sequence network and this is the negative sequence network, and this is the 0 sequence network, okay? So positive sequence, 0 sequence, negative sequence network. So the thing is that if now there are 2 cases, if neutral is solidly grounded, if neutral is solidly grounded, then you will say that your Zn is equals to 0, then basically your 0 sequence network will be converted into this, okay? 0 sequence network will be converted into this. Now if your neutral is ungrounded, right? So this was the first case. If ungrounded, your Zn will be what? Infinity. It is ungrounded, right? So there is no grounding, neutral grounding. So there will not be any path for the 0 sequence current. So conceptually, IA0 should be 0. Is it happening in the sequence network? Yes. So if neutral is ungrounded, Zn will tend to infinity. So the circuit 0 sequence network, you will observe that this will be open circuit, right? Zn will be open circuit. So even though there is Z0, there is no path for the 0 sequence current to flow. So whatever we have learned conceptually, that the 0 sequence current should be 0 when the neutral is ungrounded, that is actually proving, like we are able to prove it, that yes, it is correct, it will be 0 actually, there will not be any issues, it will be 0, okay? Now let's discuss about like delta connected network. What will happen to delta connected network, okay? So actually one more thing I want to mention, that this point is actual ground, okay? This point is actual ground, right? This is actual ground, and these points are actually not a ground, these points are virtual ground. Why? Because due to the 0 drop, we are getting drop almost 0, because actually really the ground is here, but there is no current flow. So this point is also ground only, but this is not the actual ground, this is virtual ground, similar to op-amp concept, right? Not actual ground, virtual ground. So the potential here is 0, so it becomes something similar to virtual ground. So these points are basically virtual ground. Okay. So now let's discuss the same regarding a delta network. Okay, we have discussed this for a star network. This was for a star network. So sequence network for delta network, right? Delta. So for delta, things will be similar. Okay, for delta, things will be similar. Few things will be different. Okay, so let's say if I'm applying a VA1 voltage here, right? VA1. So obviously I'm expecting that a current will flow. Let's assume that that is IA1, right? Because I'm applying across the line VAB, which is same as, like, this is also line current, right? So like the line also will have a sequence component of VAB1, right? So per phase equivalent will be what? What I can do, I can convert this delta into star. We can convert this delta into star. So for positive sequence and negative sequence, for positive sequence and negative sequence, right, we can convert delta to star, and the analysis will be exactly ditto carbon copy. There will not be any difference because the neutral point will be grounded, because there will not be any voltage drop, right? Even though there is no neutral here, but as it is a balanced system, automatically the neutral points will be connected, right? The neutral points of the voltage source and the neutral point of the balance load, right? So then this will be same. Basically, if positive sequence and negative sequence network, this will be same, z delta, z delta. Okay, there will not be any difference. Okay. What about zero sequence component? So what will happen to the zero sequence component? So for zero sequence component, you have to be careful. So if I am applying a zero sequence voltage here, will there be any current here? For positive sequence, yes, there was some current, so that's where we got the impedance. For zero sequence component, you know, I have already written it, there will be a circulating current, right? Because IA0, IB0, IC0 all will be same. So whatever current is incoming here, same current is going out. So through here current is zero. Through here current is zero. So whatever voltage I apply, no matter what, whatever zero sequence voltage I apply, current is always zero. That means what does that mean? That means my impedance is tending to infinity. But still there is some current, right? If I am applying some voltage, there is some circulating current. How will I represent it? How will I represent that? So zero sequence network, what you do in per phase, in per phase, okay, in per phase, this will be, so this will be here, right? And I will represent that if I am applying a zero sequence voltage here, right, VA0, I am not getting any current. So current here is zero. But still there will be some circulating current through the Z delta, right? What will be the value of the circulating current? It will be IA0. What is IA0? IA0 is basically my IA0 is equals to VA0 divided by Z delta. So this voltage will also be appearing across this, okay, like we will not be able to, so what we can say is IA0 will be there, circulating current will be there through the Z delta, but it will not appear in the per phase model. So zero sequence network will be this. This will be my zero sequence network, and this will be, please focus here, this will be used in transformer as well, right? In transformer, we'll just see in transformer now, this will be used. So this is the zero sequence network. This is the positive sequence network, and this is the, sorry, this is the negative sequence network, and this is the positive sequence network. So I hope it is clear, right? So there will be some phase component current, but there will not be any line current. Okay, line current will not be there. I hope it is clear, right? So here there will be some circulating current that will flow through this network. Okay, so to represent this, we have this network formation, but you might have it outside here, there is zero potential difference. How is there current flowing? So that is just one way to represent this. Otherwise, we will not be able to represent a circulating current. So we are just representing a circulating current that is flowing through this impedance Z delta by this network. That's the way, because ultimately what is important, so there will not be any zero sequence component current in delta. That is discussed in the previous lecture as well, right? So there cannot be any zero sequence component of current in delta. Okay, I hope it is clear. Okay, so now let's discuss about the transformer, the sequence network of transformer. Why? So if I am applying a positive VA1 voltage, then I will get, the transformer will give me ZT impedance, no problem, because it's a balanced three-phase supply, no problem. If I am giving a negative sequence voltage, it will give me ZT impedance, no problem. So for positive sequence, negative impedance, for now positive sequence voltage, for negative sequence voltage, the impedance provided by the transformer will always be ZT, no problems, right? It is just a three-phase balance supply. One is along the original phase sequence, other one is in opposite direction to the original phase sequence. Okay, but now what about the zero sequence component? So what will happen, because zero sequence component, I'm not applying a three-phase balance supply. Like zero sequence component, it's also a sinusoidal, it's not a DC, right? It's a sinusoidal only, but all of them are in phase. So for that, we will analyze one by one. What will happen to the zero sequence component, we'll analyze one by one. So let's say if I have a star ungrounded transformer, can you tell me, will there be any zero sequence component of current? If I am applying a voltage here VA1, will there be any zero sequence component of current? We have already discussed, if star is ungrounded, there cannot be any zero sequence component. So the primary, I see it is ungrounded, so zero sequence component cannot exist. So per phase equivalent, what I will do is, first of all, for zero sequence as well, of course it will provide ZT impedance, that will be there. For zero sequence, always it will provide ZT impedance, that will be there, right? ZT. But along both sides, what can I say? I can say that as the primary of the star is ungrounded, so this will be open circuit. Okay, because like I'm applying a zero sequence voltage and I know current is zero, so your impedance will be zero, right? Because my zero sequence current must be equal to zero. That's why the primary has to be open circuit. The secondary also has to be open circuit, because here also the neutral is ungrounded. So whenever neutral is ungrounded, you will make the primary and secondary open circuit. Of course, ZT will show, but it will be of no use because the current here is zero. Okay, this I can reduce the okay, and of course neutral will be here, right? So it is not grounded, that means there is no impedance, there is no path for the zero sequence current to flow. That's why it is open, that's why it is open circuited. Okay, so these are called as isolated neutral, right? These are called as isolated neutrons because it is ungrounded. So these are called isolated neutrals. Okay, so that was the sequence network if my star is ungrounded. So in anywhere else they will first show you some switches, right? They will sell close this, close that. No, understand conceptually what is happening. There is no possibility of zero sequence component, so of course this will be open circuit, right? Now let's say if one end is solidly grounded, other end is open. Will there be any 0 sequence current? I know it's a series circuit, right? We convert our transformer into continuity like a single series impedance. So if one side is ungrounded, other side is grounded, still there will not be any 0 sequence component. Why? Because this is open circuit. So there is no path for the 0 sequence current to flow. So this will be open ended. So the circuit will be here. How will I show the circuit? So I will show the circuit like this, that yes, this part is connected. So I can directly connect this part. It is solidly grounded, so there is no neutral impedance. So I can directly connect this part. This part is connected, but the secondary is not connected. It is not grounded. So there is no path for the secondary for the 0 sequence current to flow. So overall 0 sequence current will not flow. Although primary is connected, but as the secondary is disconnected, so 0 sequence current cannot flow. That's it. That's done, right? So that's how you draw the, these are whatever we are drawing, these are all 0 sequence component network. Negative sequence and positive sequence already we have learned that it will be ZT only. It will be ZT only. Okay. Now the other case, if now the primary is ungrounded, right? What will happen? Please tell me in the comments below. Tell me what will happen. Same thing, right? Same thing. This time it will be just the opposite. That this time primary will be ungrounded. If primary is ungrounded, then automatically again 0 sequence current will be 0. But as this is grounded, then this will get connected. This will be connected here because this is grounded. This will be connected, but still 0 sequence current will be still 0. 0 sequence current will be still 0. Okay. Now here, if both of them are solidly grounded, now is there a path of 0 sequence current to flow? Yes. Both of them are grounded. So basically, if I am sending some primary, 0 sequence current can flow, and from the secondary as well, 0 sequence current can flow out. So it will come in from here, flow out from here, right? Ground to ground. Ground to ground connection is there, right? So now what will happen? There is full path of 0 sequence current, and as it is solidly grounded, remember there is no impedance through the neutral, so I can directly connect it. I can directly connect it, no problems, right? So here, now here what will happen? I am grounding the neutral, but it is not solidly grounded. It is connected to impedance Zn. Do you know what happens if it is connected to impedance Zn? It becomes 3 times, right? The neutral impedance becomes 3 times. If you see during star, our star was grounded, the neutral impedance became 3 times. This is Zn. It became 3 times, right? So here as well, the neutral impedance will simply become 3 times. It will not be 0, it will be 3 times. Okay, it will not be Zn, it will be 3 Zn. Okay, here just the opposite. Here it will become 3 times, here it will be directly short circuited. So if I copy this, on the right hand side it will become 3 Zn. Okay, so it will become 3 Zn. Now here both sides are connected with Zn, so both sides are connected with Zn, so both sides will be 3 Zn, right? I am not telling you to remember anything, just following the sequence, right? Just following the sequence. So both side is connected to Zn. So this side also will be 3 Zn, this side also will be 3 Zn. I hope it is clear. Now what about delta? What will happen to delta? So we know for delta, right, if the right hand side is delta connected, so will any 0 sequence current be present in the lines? Will I be able to receive any 0 sequence current? No, right? I will not be able to. It will just circulate in the circuit itself. I will not be able to receive any zero sequence component of current. Correct? So what will happen if I have a delta connected in the secondary? Will I be able to receive on the line? No. So it will be open. So zero sequence current on the line will be open, but it can circulate in the transformer. How will I show it? How will I show it? So here I will take this case where, like, if you see here, the primary is ungrounded and the secondary is delta. So both primary and secondary, I will not get any zero sequence component of current. So this will be the first circuit only, but the difference will be the zero sequence current can circulate, but still it will not be able to circulate. Why it will not be able to circulate? Because in the primary as well, neutral is ungrounded, so there is no possibility of circulating current here. There is no possibility of zero sequence current at all. So basically what will happen, I will draw a line, right? This line represents that there is a possibility for the zero sequence current to flow in a circulating current manner, but here in the primary I don't have any delta, so the circulating current will not be able to flow, so there will not be any zero sequence current. So ultimately zero sequence impedance is infinity only, it is infinite. Okay, it is infinite. Now here, if it is grounded, so if this is grounded, solidly grounded, then I will copy the circuit again. Secondary is delta. So zero sequence current can flow from the primary and go in this loop, but in the secondary I will not observe any zero sequence component of current. In the secondary I will not observe any zero sequence component of current. The current, circulating current, can flow in this loop. Okay. What about delta? What about this 3Zn? So if it is 3Zn, simply what will happen, that this is 3Zn. So this will become just 3Zn, that's it. This will become 3Zn because neutral is grounded, so this will become 3 times. Neutral impedance will become 3 times. Now if both sides are delta connected, okay, this is both, not both sides. Now if the right hand side is isolated, same we will follow. Just the difference will be, now a wire will be connected here, right? Here, this point, wire will be connected here. Okay, so I will copy when the primary is connected, the secondary is ungrounded. So if the primary is delta, then zero sequence current will flow from here. Zero sequence current will flow from here, but it will not flow from the line. So the line must be open, right? Line must be open. Line must be open, right? Zero sequence current will not flow from the line. Okay. So here as well I haven't made any mistake. No, this is correct only. This is ungrounded. Yeah, both. Here also if you see, both ends were open, right? Here also basically zero sequence current cannot exist in the line, but it can flow circulating. It can circulate in the line, but this point is not connected. So there is no possibility of zero sequence current in circulating nature as well. Okay. But here if it is delta star same only, okay, this is not isolated anymore. So now what will happen? Now this will be connected basically. Now zero sequence current can flow in the secondary, but not in the primary. This will be connected, so zero sequence current can flow in this loop. Okay. What about delta Zn, 3Zn? So 3Zn, if it is, basically it will be, sorry, if it is Zn, so basically it will be replaced with 3Zn. Okay, it will be replaced with 3 Z and that's it. Okay, what about delta delta? The last one. What about delta delta? So what will happen to delta delta? Delta delta, it's very simple, right? So the left hand side and the right hand side will be open circuit. Left hand side and the right hand side will be open circuit. This point also will be connected. So circulating current will flow through the transformer, but it will be not there in the primary and the secondary because it is delta, right? Delta means circulating current can exist in the loop, but it cannot exist on the line currents. So zero sequence circulating current will exist in the loop. So all these were zero sequence current, right? So if you are having confusion, please go through this like 10-15 slides again. It will be a good revision for you, right? So that was the delta delta basically. I hope it is clear now. So now we will discuss about the alternator. So for alternator, what will happen? So let's say if I have an alternator here, 3-phase star connected alternator, how will I replace the network? So for alternator, it's very simple. For alternator, it's very simple. I can draw this. If my EA, right? EA has 3 components. Let's say EA1 plus EA2 plus EA0, and let's say my ZG has 3 kind of impedance: ZG1, ZG2, and ZG0. Right? 3 kind of impedance I have. So I can use the superposition. So whenever I can break this down into positive sequence network. So what will happen in the positive sequence network? Positive sequence network. We know if it's a positive sequence network, all of this will be replaced with what? EA will be replaced with EA1. Z will be replaced with Z1, right? ZG1. This will be ZG1, this will be ZG1, this will be EB1, this will be EC1, right? So due to this, there will be some, like it will deliver some positive sequence current. Let's say IA1, right? We have assumed it delivers some positive sequence current. So this also, let me, actually I should mark the dot polarities, otherwise there will be mistake, right? So here IB1 say this is IB1, this is IC1, right? So what I can say again, what is the neutral current coming out? So IN will be equals to IN will be equals to IA1 plus IB1 plus IC1. Okay, and I know it's a balanced system, so again this becomes 0 because it's a balanced current, right? It's balanced voltage I'm giving, so it will be balanced current, so it will be 0. So if it is 0, there is 0 drop. So what is the per phase equivalent? So what is the VA1 basically? What is VA1? So VA1, if I use the KVL, VA1 is simply equals to EA1 minus IA1 into ZC1, right? Because this current is 0. So basically if I want to draw this, represent this in terms of a circuit, what will be the circuit? Circuit will be, I will have a voltage source, EA1, I will have a impedance ZG1, and I am taking the voltage VA1 and the current is IA1. Okay, I hope it is clear. Per phase, this is the per phase equivalent diagram. For negative sequence, exact same analysis will happen. For negative sequence, exact same analysis will happen. Just here I will have C and here I will have B. That's it. Like the phase difference will be separate, but for other than that, everything will be exact same. Okay, so for negative sequence network, this will be EA2, this will be V2, this will be EC2, this will become ZG2, okay. So this will become ZG2, EA2, current will be I2, this will be VA2, everything will be same, nothing will be different, right? Because again the neutral current will be 0, this neutral current will be again 0, right? Because again it's a balanced system, although the phase sequence is different, but it is a balanced system. So what happens in negative sequence actually, what happens, the whatever voltage it generates, it tries to rotate the armature in the opposite direction. So previously, if armature rotates in the clockwise, let's assume armature rotates in clockwise direction. If armature rotates in clockwise direction, then we get positive sequence voltage. If armature rotates with what is the speed? With speed ns. So then I will get a rotating magnetic field. Okay. Now here my armature rotates in the anti-clockwise direction with speed ns, right? If it rotates in the anti-clockwise direction, then the EMF induced will be EA2, the negative phase sequence component, right? Then what will be the equivalent voltage? Equivalent voltage will be this EA2 ZJ2, same, right? Now I will derive like one more thing. I will derive few things. And what is the 0 sequence component? So the 0 sequence component will be interesting. It will not be exactly same. So for 0 sequence component, armature does not rotate, right? 0 sequence means all the phase are same. So it's like a standing wave. So 0 sequence basically means it is like a standing wave, that whatever we have learned in what special machines, right? We had few single phase machines, there we discuss about the pulsating wave. So armature does not rotate. Basically armature rotates both in clockwise and anti-clockwise direction with speed ns. Basically the net torque is 0. So armature tries to rotate in both clockwise and anti-clockwise direction. Okay, so we try to rotate clockwise and anti-clockwise. So the net torque will be what? Net torque will be 0 actually, right? Voltage EMF induced actually will be 0, but still if I assume that there is some 0 sequence voltage, like actually there will be no voltage, so I will tell you it will be 0 only. But if I assume, still let's say I have a 0 sequence voltage developed, so current will be, this currents also will be IA2, right? Currents also will be IA2, IB2, IC2, this will be IA2, so this will be IA0, IB0, IC0, okay, and this will be IA0, VA0. Now the interesting fact will be, if I apply a KVL, this will not be 0 anymore, right? IA0 plus IB0 plus IC0 will not be equals to 0 anymore. It will be equals to 3 IA0. So from here the neutral current is 3 IA0. So if I apply ground to ground KVL, so this will be, what will be the drop here? The drop here will be 3 IA0 into Zn. Okay, 3 IA0 into Zn. So this is the drop basically. So if I apply a KVL from ground to ground, what will be KVL? V minus VA1, that is VA1 will be equals to this drop, basically ZG0 into IA0. So this will become EA0 VA0 into ZG0, IA0 into ZG0. Also there is another drop. This is one of the drop, right? Current is flowing like this, right? Okay, sorry, this will not be, this will be plus minus, right? So current is actually flowing like this, right? So the drop is here, plus minus. So if I apply first here plus 3 IA naught Z0 minus EA0 plus 3 IA0 plus VA1. So this basically becomes, you apply the KVL, you will see here another additional term will come, that is IA0 into 3Zn. Again this 3Zn term will come, right? I know why, because the current gets multiplied by 3, that's why. So zero sequence component network, I will have EA0, I will have ZG0, along with this I will have another additional impedance, that is 3Z0. Okay, another additional impedance, that is 3Z0. Okay, so there will be another additional impedance, that is 3Z0. So 3Zn, right? Because neutral impedance is there. Now if neutral is ungrounded, this impedance network will be open circuited. If neutral is ungrounded, this impedance network will be simply open circuited, no problems at all, right? Very simple and easy to understand. Now in most of the books, right, in most of the books, what will be taught, you will be actually, you will not be like, this might seem something new to you, right? This might seem something new to you, this is familiar, this one will be familiar, but this one will be new, because in your book and in everywhere else, in every other coaching, you will be taught that it is only ZG2. But one day, if the voltage will come out to be a unbalanced voltage, unbalanced sources, right, then you will just not replace with ZG2. You have to replace with its negative sequence voltage as well. That day, everyone else will not be able to solve the question. You will be able to solve the question, because they have just mugged up the thing that your negative sequence impedance will be ZG2. That's it. There will not be any voltage. So I will tell you the special case. What is the special case? So special case that will be present in your books, right? The special case will be if my source is balanced. If my source is balanced, then what will happen? If my source is balanced, then what will happen? Then what I can say is, I will have here my positive sequence impedance, my positive sequence voltage EA. If source is balanced, it will be only VA only, right? EA only, right? And then I will have this positive sequence network VA1. What will be the negative sequence network? I will not have any source, that will be 0, because source is balanced, so there is no EA2, so it will be only ZZ2. That's it. This will be my VA 2. Current will be flowing like this. This will be my IA1, this will be my IA2, and this will be my zero sequence network. Okay. Now another special case, if my neutral is ungrounded. If my neutral is ungrounded, basically this will become open circuit. So basically then it will be open circuit, so there will not be any current. That's it. Okay. or if it is solidly grounded, this will become short circuit. Okay, this will be the diagram that will be present in your books. So this will be the positive sequence network, this will be the negative sequence network, and this will be the zero sequence network. Okay, so positive sequence, zero sequence, and negative sequence network. I hope it is clear to you what will be the different sequence. So all these values were there if the source is unbalanced, right? If the source is unbalanced, so of course if it is not rotating at all, it will develop a pulsating voltage. There will not be any phase shift. It will develop a pulsating voltage that has been taught to you in single phase motors, right? Okay, so I hope it is clear. Now what will happen for delta? For delta, what will be the like equivalent voltage? So what we can do, we can convert this into star. How do we convert this into star? So if the voltages are balanced, right? If the supply voltage is balanced, you will convert your delta to star. How do you convert? So here it is EC. In star, the phase voltage will be EC by root 3 because EC is supposed to be the line voltage, right? So the star network will be something like this. I will have this coil, and the coil also, the impedance also will be reduced by half, by 3, because from delta I am going to star, so it is division. So this will be Zg by 3. This will become EA divided by root 3, right? Here I will have a dot. Sorry, here I will have dot. Okay, so EA divided by root 3, and then I will have here again Zg divided by 3, EC divided by root 3. Here I will have EB divided by root 3. This will be Zg divided by 3. Okay, so that's it basically. That's how, like, now I hope you will be able to compute the equivalent delta, but only valid for a balanced supply. If it is not balanced, I will not be simply able to convert this into EA divided by root 3. It is only valid for balanced. If the supply is balanced, that is the impedance is also balanced and the voltages are also balanced. So one more key point is there regarding the impedances, right? So one thing is there, right? If my armature is rotating, that means what? It is developing potential. That means flux is getting cut. That means there will be armature reaction. So if armature rotates, armature reaction will be more, because armature reaction will be more, because the load current also will increase, because that is why it operates in the rated condition. So armature reaction will be more. Okay, either it rotates with speed ns, right? Right? So armature reaction will be high. So if armature reaction is high, what can I say? I can say that if it rotates in the positive direction or negative direction, it does not matter, the armature reaction will be high. If armature does not rotate at all, so there will be no flux produced. So armature reaction will be low. Okay, armature reaction will be low. Okay, armature reaction will be low. Now what I can do is what I can do. If armature reaction is low, that means your zero sequence impedance will be lower, right? It will go down because your zero sequence impedance is a combination of the armature resistance plus the reactance. So reactance only will change. Resistance is constant. It does not matter. It does not care whether it is zero sequence, negative sequence, positive sequence. It does not care. But here we get impedance as Z1 and Z2, right? So basically ZG1 and ZG2, they will be more. And roughly we say that it is rotating in the forward direction or it is rotating in the negative direction. Basically the impedance provided, the reactance provided, armature reactance provided will be almost same whether it is rotating in the forward direction or reverse direction. Okay, so here armature reaction will be low, here armature reaction will be high. So what we say generally, that my positive sequence impedance will be roughly equals to negative sequence impedance, because it does not matter if I rotate in the forward direction clockwise or anti-clockwise, impedance almost will be same, will be also will be greater than, much greater than the zero sequence impedance. So this is also a very important conclusion that you must keep in mind, right? So for a generator, the positive sequence and negative sequence impedance will be much higher than the zero sequence impedance, and the positive and negative sequence impedance will be almost equivalent to each other. Okay, this is another key point to understand. Okay, this can be asked in theoretical MSQ. Okay, so yeah, I hope it is clear to all of you, right? So now one more thing is there. What is there? So what else is there? So if supply is balanced, I forgot to tell you, we will convert delta to star for the positive sequence network and for the negative sequence network. For delta, we don't need to convert it to zero sequence network. So what will happen to the zero sequence network? So for positive sequence and zero sequence, what will be the positive sequence network? So positive sequence network will be like this, right? Here I will have Zg by 3. Here I will have, let me take a page. So what will be the positive sequence network? Here I will have Zg by 3. Then I will have E divided by root 3, and of course neutral current is 0. So this will become my VA1. Okay, for delta connected. This is the positive sequence network. For negative sequence network, here I will have Zg by 3 again. This will be Zg1 by 3. This will be Zg2 by 3. Of course, it is balanced, so there is no negative sequence voltage. So this will be my VA2. This will be my current IA2. This will be my current IA1. Okay, so IA2, IA1. Now what about the zero sequence? So for zero sequence, I will draw it separately. For zero sequence, I have to directly draw. I will directly draw zero sequence. There is no possibility of zero sequence current to flow, because we don't have neutral, right? We don't have a neutral here. So basically, the zero sequence network will be I will have the zero sequence impedance Z0, but neutral is not there, so this will be infinity, right? There is no possibility of the zero sequence current to flow, right? So neutral is not there, but it will flow through the loop. Zero sequence component of current can flow through the loop, right? So neutral will be not there at the line side. I will not see any current, zero sequence component of current at the line side. So this will be open circuit, but of course it will flow through the loop, right? Zero sequence component of current will flow through the loop, correct? So I hope it is clear to you that it will flow through the loop. So am I doing anything? Okay, one more mistake I may have made. Now I am thinking it's kind of a mistake by my end. So for delta, right, one kind of mistake I have made for delta. Yeah, one mistake I think I have made. Actually, like in all the books, they give this in all the books, right? I will show you what like I just right now I thought of this. So first let me come to star. So in all the books, what they tell you, no, let me come to delta. So in all the books, what they tell you, this is zero voltage, right? Actually, it is not technically correct. This is not technically correct. If I am applying VA0 here, this VA0 is coming across this phase, right? So actually what will happen, this VA0 will actually come across this as well. So basically what am I telling? Actually in the books they show it like this, but how current will flow? So actual circuit should be for the zero sequence network. I will show you the actual circuit for zero sequence network. Actual circuit should be this. But it does not matter basically because anyways the line current is 0. So here I will have Z delta, okay, and then I will have the voltage source, that is VA0, and due to this a circulating current will flow, that is IA0. So basically what is a circulating current, right? What is a circulating current? Can you tell me? So each of them, like this has VA0 voltage, this will also have VA0 voltage, this will also have VA0. So if I apply KVL here, it is 3 VA0 by 3 Z delta, all of them are a series, it is VA0 by Z delta, right? So current IA0 will be actually VA0 by Z delta, right? So current IA0 will be VA0 by Z delta. So trust me, this will not be present in any book, right? कोई भी बुक में ये नहीं मिलेगा, ठीक है? तो अगर आपको अच्छा लग रहा है तो लाइक ठोक दो. So like this, just what I'm telling is this is not present in any book. Okay, if you are enjoying the concept, you can obviously appreciate it by hitting the like button. Okay, it's because in all the books they will say it is short circuit, but if it is short circuit, how the current will flow, right? Some current has to flow. How the current will flow? So I will apply a additional source, that is VA0, but it does not matter whatever I do here because ultimately I know my current, line current IA0 will be 0, right? So it does not matter whatever I do here. So the current flows through here in a loop, but it does not, it is not a concern to me because here the current is 0. Okay, so I hope it is clear. Like one more new thing we learned. Okay, although like you will draw this circuit only, you will not draw that one because in books everywhere in standard textbook they will use this, but don't get surprised if they use this. Okay, just wanted to clear this out, don't get surprised, right? Okay, so why it clicked in my mind, because here, right, there will be some zero sequence voltage in the delta, correct? There will be some current, so that's why it clicked. Like it will not be exactly 0, this voltage VA0 will be here, but actually here it is a balance supply, so there is no possibility of zero sequence voltage, so it will be zero current only. Zero sequence current will be 0 only because it is balance supply, there is no zero sequence voltage, correct? Okay, I hope it is clear. So this is my zero sequence network. Okay, okay, so these are the things that is we learned, that is what we learned. Now we will do a question. One more thing, whatever we learned will be applicable for synchronous motors. So same, I will write here, same sequence networks networks can be used for synchronous motors. Okay, so basically my EG will be replaced with EM and my XG will be replaced with XM. Okay, that's it. Everything else, not XG, sorry, ZG. Will be replaced with ZM. Okay, so I hope it is understood by you. So okay, I forgot to mark down the questions. So let's do few questions. What was the last question that we did? 40, right? So this will be 47 question. Okay, so a 2 bus zero sequence network is shown, okay, corresponding to this system. They are asking me the transformers T1 and T2 are connected in what? Are they in star star, ungrounded, star delta, star star, grounded, star delta, ungrounded? Like, what is the connection? So here what I am observing is the zero sequence network is shown, right? So here I have 3GN. So I see, yes, it is 3GN because it is grounded, right? Neutral is grounded with reactance XGN. Here I see I am getting XOG. So it is the zero sequence reactance of the generator. Here I am seeing I am getting XOT. XOT I am getting, and this is open circuit. On the left hand side I am seeing it is connected. If it is connected, it's a zero sequence network. If it is connected, that means the ground here is solidly grounded, and if it is connected, it is not shunt connection, it is a series connection. That means it is a star network, star grounded. So the left hand side of the T1 should be star grounded. Star grounded I am seeing here, here. So these are automatically eliminated. Now on the right hand side I am seeing it is open circuit, right? It is open circuit and there is no parallel connection. So if it is just open circuit and no parallel connection, that means it is what? It is delta connection, not delta, sorry, it is star connection, but it is ungrounded star. It is ungrounded star. It is series, but it is ungrounded. So it will be secondary will be ungrounded star. So that is only present in the option B, right? So let us further confirm it with the second transformer. Then I have this XOL. XOL is nothing but the line reactance, zero sequence line reactance. Then I have this transformer T2, for which I am observing that the primary is short circuited series connection. So it is star grounded. So I see, yes, it is star grounded. Here again it is delta. Delta is not possible here, right? Then I see in the secondary shunt connection is there and it is open circuit, right? So that means basically it is a delta connection. It is a delta connection. So delta connection is present in the secondary here. Here delta connection is not present. So of course option B will be the correct answer for this question, right? So that's how simple questions can come. So this will be the solution for this question. Now let's move on to the next topic, that is sequence network for a transmission line. Sequence network for a transmission line. Okay, sequence network for a transmission line. Now if the transmission line has some transmission line resistance, transmission line inductance, okay, and of course we are assuming the transmission lines have some mutual impedance. So mutual impedance means what? If some current flows here, right, so there will be some drop here across this transmission line B due to the current IA, that will be equals to IA into Zm. That will be equals to IA into Zm. Okay, So I hope it is clear. That is what my Zm is. So Zm is the mutual impedance. Zm is the mutual impedance. Your ZTL is equals to RTL plus XTL, that is the transmission line impedance. Okay, yeah, and of course Zn is what? Zn is the neutral impedance. Zn is neutral impedance. So Zn will be neutral impedance. So one more thing, here the current is Ia, here the current will be Ib, here the current will be Ic, right? So what will be the neutral current? Neutral current, it will be the Ia plus Ib plus Ic, right? Because at some point there will be some star connection and all of the current will come back through neutral. That is understood, correct? That is understood. Okay, so let me write down the voltage drops. So what is the potential drop from VAN minus VA dash N, right? So it is a drop across this transmission line. What is this drop? So VAN minus VA dash N dash. What is this drop? So this drop will be equals to the current into this drop, that is ZTL, right? Current is Ia into ZTL transmission line impedance plus, I told you, right, there will be some drop due to mutual impedance. So if some current Ib is flowing, due to this Ib, due to the mutual impedance, there will be some drop in the line A. So it will be plus Ib into Zm plus, again due to the line C current flowing Ic, there will be some mutual impedance between line C and A. Now what you will say, sir, why there is no mutual impedance between neutral and line A? Because neutral is like grounded, it is in the ground. These three are very close to each other. That's why. So one more thing, the three lines are very close to each other. Then three lines ABC, right? Then ABC are very close to each other. Then what will happen? There will be some mutual impedance. but neutral is far, so neutral there will not be any mutual impedance. Okay, so this will be IB plus IC into Zm plus, now I have to find out the difference between these 2 points and these 2 points. So Zn is also there, right? So if I apply KVL, so let me apply KVL. So let me apply KVL, you will understand what I am talking about. So this is minus plus. So I will start from here. I'll go here, right? I will write down the drop of this line. So the drop of this line is this much, right? This much. Then I will come back here. This will be my VAN dash, right? So minus VAN plus VAN dash. So that is basically VAN minus VAN dash. I'm applying KVL simply. And then I'm coming back here. So I have to close the loop, right? So I will copy this circuit and just show in a brief how is my KVL happening. So KVL, I'm doing this KVL. I'm starting from here, going here, then again ending here, right? That is my KVL basically. So I hope you understand the loop of the KVL, right? This is my loop. So you apply the KVL, you will see same. This Zm are coming due to the mutual impedance. Okay. Plus, of course, there will be this drop, that is IA plus IB plus IC into Zn. Okay, IA plus IC plus IB into Zn, right? So this is what basically. So this will be applicable for all the phases, all the other phases. So here I will have VBN minus VB dash n. This current will be IB. This will now become IA and IC. This will be same. This drop will be same. Same will be applicable for VB dash. Any other way I can write it. So I will show you how can I write it in a different manner in matrix format. So this will be VC minus VC dash. This will be IC. Okay, this will be IA. This will be IA. This will become IB. Okay, everything else will be same. Now, the thing is, can I write this in a matrix format? Yes, I can. So I can write this whole thing in a matrix format. So let me delete this IA, IB, IC. This will be required later. So can I simplify this further? Can I simplify this further? I think we can simplify. Okay, let me first simplify this, right? Let me first simplify this. So this VAN minus VAN dash, what I can write? I can write this as delta VN, basically the drop across the line, right? And this will be delta VBN. This will be delta VCN. Okay. So I can take common here IA. IA will be equals to what? IA will be IA into ZTL plus Zn. So here I will have ZTL plus Zn, right? So this can go away. This will be ZTL plus Zn. Now what will be IB into Zm plus Zn. So with all of them, right, extra Zn term will come. That's it. So this will go away basically. With all of them, this Zn term will come. Okay. So plus Zn plus Zn. So can I write this in a matrix format? Yes. So what I will do, I will now properly arrange the terms. So this will be, first I will write IA. IA will be first. Then IC. IC will be last. Okay. Now if I draw this properly, right, I can write this in matrix format. IA, IB, IC. Okay. So this is my matrix format basically. So this is called as the, this matrix is called as the, so this line, right, this is the sending end voltage, right, this point is called as the sending end voltage, this is the receiving end voltage, right. So this actually is called sending end, this end is called as the sending end, and this end is called as the receiving end, because we are receiving the voltage here, receiving end. Okay. So here this will be basically sending end minus receiving end and voltage. Okay. And this one is actually called as the impedance. Matrix. So this point is called as the impedance matrix, and this is basically the line currents. Okay, these are called my line currents. So how do I find out the how do I write this, like how do I find out the zero sequence component of the transmission line, positive sequence component of the transmission line, and negative sequence component of the transmission line. So do you remember this relation whatever we had discussed previously here, right? Where is that relation? Where is that relation? Where did it go? Here, this one, right? Not this one, actually, this one. This relation if I use, so I will replace, basically I want to find out the zero sequence amount of voltage drop, positive sequence and negative sequence voltage drop. So I will use this equation. So here, right, VABC is there, so I will replace this with this matrix, right? So my matrix I will replace like VAN, delta V, delta VN, delta VBN, delta VCN will be replaced with this VA0, VA1, VA2, 1 plus alpha square, that is matrix A. So I will replace here this matrix with A into VA0, VA1, VA2. This will be equals to this matrix that is known as impedance matrix. For now I will write this as Z into the line currents. Okay, also I can replace my line currents as well, right? Same I can do for the line currents IA, IB, IC. So same can be followed for the line currents, right? So I can say that my IA, IB, IC is the same, right? This is the same. I have to just replace the voltage with currents. So this will be currents. IA, IB, IC will be replaced with IA0, IA0, IA1, IA2. So this will be, this is what? This is A, right? So this is A times this IA0, IA1, IA2. Basically I want the positive sequence impedance, negative sequence and the zero sequence, right? So I have to find out the ratio of VA0 to IA0. So what I will do? I will multiply by A inverse on both sides. So if I multiply by A inverse on both sides, it will be A inverse Z into A. So I hope you remember what is A inverse Z into A. What is A inverse Z into A? So A inverse Z into A is simply, what is my A inverse? The A inverse is equals to the same value, right? But my alpha will be replaced with alpha square and I will divide by 1 by 3. That's it. Alpha will be replaced with alpha square and I will be divided by 1 by 3. Okay. So the homework task for you is to do this matrix multiplication, right? A inverse I know, A I know. Do this complex matrix multiplication. The final result, what you will get, I will directly write the final result. Okay. Of course, we don't have that much amount of time, so I will directly write the final result that we will get. Okay. So the result that we will get is, this will become your Z transmission line. Okay, the transmission line impedance. Sometimes this is also called as ZS. So don't get confused if it is written ZS or Z transmission line. This is the transmission line impedance plus 2Zm plus 3Zn. Okay, and the rest values are simply 0. And here VA1, this value will be 0. This will be ZS, not ZS, sorry, Z transmission line minus Zm 0, and this also will be 0. Here the negative sequence current will be there, that's why this will be Z transmission line minus Zm. This will be the matrix. Matrix will be symmetrical. Okay. So here what do I notice? The thing that I notice is my VA, basically my Z0, right? Z0 is what? That is VA0 by IA0. So it is VA0 will be equals to this into IA0, 0 into 0, right? So it is basically ZTL. Z0 will come out to be ZTL plus 2Zm plus 3Zn. So in zero sequence component, everything is getting added. 3Zn, I hope it is easy for you to remember. You have to remember this, right? 3Zn is easy for you to remember because we always know whenever there is some zero sequence current, the neutral is multiplied by, neutral impedance is multiplied by 3. Now whenever, like with Zm, so 1 is multiplied by 3, right? Your actual transmission line impedance will be just there directly. So you have to multiply by 2 with the mutual impedance. How to remember? That is what I am explaining over here. Okay. What will be your positive sequence impedance, your positive sequence impedance is equals to ZTL minus Zm. Basically your positive sequence, right? I have to subtract the mutual inductance because that is going against the positive sequence current. That's why it is ZTL minus Zm, and Z2 also will be same, ZTL minus Zm. You see, right? VA2 is equals to ZTL minus Zm IA2. Sometimes it is also written as Zs plus, like everything will be replaced with Zs, right? ZTL will be replaced with Zs. So please don't get scared by Zs. It's the same. Nothing is different, right? Do you notice one thing here? Okay. Do you notice one thing here? So the thing that you notice is that my Z0 is actually greater than Z1 and Z2. Z1 and Z2 are equal. So it is just the opposite of synchronous machines. So this is also another way to remember which one will be greater, which one will be lower value. There is also another way. Like with Z0, everything will come in addition. With other two impedances, it will come negative, and always Z1 will be equal to Z2. Same for synchronous machine. Z1 will be equal to Z2, but there Z1 and Z2 were greater. Why? Because intuitively, if you want to understand, here there is no rotating parts. So if rotating parts are not there, that means that sequence current, three-phase balance supply is not there, right? So that's why the positive negative sequence impedance are very low than the zero sequence impedance. Okay, so I hope it is clear. There are no rotating parts over here. Okay, so yeah, that's it basically for this lecture. This lecture was mainly for derivation purpose. So if I want to draw the sequence network, let me draw the sequence network as well. So what will be my sequence network, right? Sequence networks. Okay, so my sequence networks, right? I will draw the circuits. Okay, one more thing I have to do actually. This point was, okay, that is fine actually. This point here is, let me draw the zero sequence. This will be VA0 and this will be VA dash 0 dash. This will be VA1 dash, sorry, VA1. This will be VA dash 1 dash. This will be VA2. This will be VA2 dash, A dash 2 dash. Okay. Now this is my Z0. This is my Z1. This is my Z2. Where Z0 and Z2, all these values are already written over here. So that is how you will draw the positive negative sequence networks, right? So yeah, let me place it over here. This is my zero sequence network. This is my positive sequence network. This is my negative sequence network. Okay, so yeah, I hope it is clear what is my positive sequence network, zero sequence network, and your negative sequence network. Now can you find out the like the admittance. Do I need the admittance? Admittance also you can find out. So what will be the admittance? So this matrix, right, is the sequence component matrix, Z sequence. Okay. So admittance will be what? Admittance will be just inverse of Z sequence. Now interesting is, if I observe one thing, right, it is a diagonal matrix. So the inverse of a diagonal matrix is nothing, just the inverse of its individual terms, right? So your admittance sequence matrix will be what? Admittance sequence matrix y of 0 1 2. What will be y of 0 1 2? So y of 0 1 2 will just be the inverse because it is a diagonal matrix, right? So I will copy this directly. The diagonal elements will be inverse, that's it. Okay, so this I will delete, this I will delete actually, because I need more space. Okay, ZS minus ZM. So this will be the admittance matrix basically. So yeah, that's it basically for this lecture. In the next lecture, mainly we will solve the questions on sequence networks and we will finish our symmetrical components. After that, we'll start with unsymmetrical faults. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 10, that is the assignment 4, right? So today we will be mainly solving questions of symmetrical components. Also we will be summarizing whatever we have learned. So this is the first question. So I will give you I will give you time. So this is the first one, second, okay. This is the third one, then this is the fourth one, then we have this fifth one. Like there are a lot of questions that we will solve. Sixth one, seventh. Okay, after this a bit of summary will come. Yeah, so you try to solve all this, right? And of course I will solve start with the first one, this one, right? So here the series impedance matrix of a short three-phase transmission line in phase coordinates is shown. What does this mean? This basically means they have provided me this VABC matrix equals to the impedance matrix Z ABC Z matrix into the current IABC. Now, is this something familiar to me? Does not look like it is familiar, right? Because the impedance matrix that we derived was actually this one. So it's a big matrix. How it became so small? So it's a special case of this one only. If you observe, like here I have Z transmission line. They have mentioned Z transmission line as ZS. So please don't get scared if it is written ZS. It is just the ZS, like transmission line impedance. That's it. But there is no Zn. In all the places there is no Zn. So basically, if I make Zn 0, if I make my Zn 0, my this impedance matrix and this one will be same. I hope you are able to notice, right? So my Zn is 0. Now they tell me the positive sequence impedance is this 1 plus Z10. And what was your positive sequence impedance that we derived? It was Zs or ZTL plus 2Zm plus 3Zn, right? And in our case, Zn is 0. So it is equals to Zs plus 2Zm equals to 1 plus Zn. Okay. Okay. So yeah. Now this is one equation, and zero sequence impedance is 4 plus j1. So what is z naught? Sorry. This was z naught, right? Sorry. This was actually z naught. So z naught is actually this, right? I'm sorry. Z naught is this value, 4 plus j31. I also tend to forget this sometimes. And so your then your zs plus z 2zm will be 4 plus j 31. So your now your positive sequence impedance z1 is equals to what? That we derived, it was zs minus zm. Zs minus zm, there was no zn, right? So which is equals to, given to me, that is 1 plus j10. 1 plus j10. So I got two equations and two unknowns. So what are they asking? The imaginary part of zm will be, what will be the imaginary part of zm? So I will be able to find out what is my zm and what is my zs. So what can I do? I can, from 1 I can subtract 2, right? If I subtract 2, zs will be cancelled. 3zm will be equals to, this will be 3 plus j21. Okay, 3 plus j21. So zm will be 1 plus j7. Zm will be 1 plus j7. Okay, this is what my zm is equals to. So they are asking me what is the imaginary part of zm. So imaginary part of zm will be 7 ohms. So this will be an answer. Okay, that was the question. Let's now do this next question. So next question is, it's like a theoretical question. Okay, so for a fully transposed transmission line, positive negative zero sequence impedance are equal, positive negative sequence are equal, zero positive sequence are impedance are equal, negative zero sequence impedance are equal. So full, what does transposing means? Transposing basically means this. Okay, what is this? So what we do is, we initially, if my transmission line E was at the highest point, then I bring it to middle, and at the end I bring it to the lowest point, and basically I transfer the positions of each line after a certain distance. Like 1/3 of the position E will be at the top, 1/3 of the position C will be at the top, 1/3 of the position B will be at the top. Why is it? Why do we do this? Because what do you notice here? The distance between, let's assume that this small distance is 10 meter, right? Distance between A and B is 10 meters here. Here the distance between A and B is 10 meters, and here the distance increases to 20 meters, right? Same, distance between B and C is 10 here, distance between B and C is 20 here, here is 10, here it is 10. So we know the mutual reactance or mutual impedance Zm will depend on the distance, right? So what we try to do is, we try to make the distance symmetrical throughout the line for each of these phases, each of the three phases, so that the Zm is same for all three lines and for both positive and negative sequence impedance. Sequence impedance. Okay. Now Now, what you have to understand is we want to make it symmetrical. Basically, I want to make my positive sequence impedance is equals to my negative sequence impedance. We actually that time I told you that positive sequence impedance is equals to negative sequence impedance during the derivation, but actually in reality they will not be exactly equal unless and until we do this transposition, because there we assume Zm is same for all the three phases, but in reality Zm is not same for all the three phases. Then your sequence impedance will be different, right? So this kind of approximation we had taken there, I did not explain. So basically we make the positive and the negative sequence impedance equal, we do transposition so that my Zm is same throughout. Okay, so it's a theoretical concept. Why we do this? So these are a few like reasons why we do this. You can go through this, I'm not explaining, but main concept is I have to make the Zm same throughout the line. Okay, so let's solve this one. This one is actually a good question. So here they have asked you, consider the transformer connections they have shown you in part of a power system. The nature of the transformer connections and phase shifts are provided. Nature means delta star, and phase shift also they are providing. So if I'm at this position, if I'm moving here, so the phase shift is minus 30. If I'm at this position and moving here, the phase shift will be plus 30. Okay, which, but for one, right, one transformer it is not shown. This transformer they are not showing me the phase shift. This transformer they are not showing me the phase shift. Okay, which of the following connections and the corresponding phase shift should be used for the transformer between A and B? Okay, so which connection should be used for A and B? That is what they are asking, right? So how do I understand? So how do I solve this? So if you remember this thing, that star star transformer does not, like star star transformer can provide either 0 degree or 180 degree phase shift, right? Star star transformer can provide either 0 degree or 180 degree phase shift. This we have learned in machines. Star star or delta delta, it will be either Z. If you remember, the connection was either YY0 or YY6. Here the connection was DD0 or DD6, right? So the phase shift will be either 0 degree or 180 degree. Here also the phase shift will be 0 degree or 180 degree. Whenever it was star delta, like YD, it was either 11 or YD1. I'm just like, if you are not able to understand, please go and revise the three phase transformer, I think lecture 1. Okay, then we had this DY11 and DY1. Okay, so either it will be like this was minus 30, this was plus 30, right? This was minus 30, this was plus 30. Okay, this would have been a phase shift. Now here it is delta to star and it is providing me plus 30 phase shift. So one thing you should keep in mind, the phase shift at this point should be same if I come through this path or through this path. So if I start from here, let's assume that this has a phase shift of 15 angle 0, right? So this is providing a phase shift of plus 30. So here the phase shift will be overall 30 degrees. Now after this point, again I have an auto transformer that is providing 0 degree phase shift. So here the phase shift is 30 degrees if I come from the left hand side path, right? Or if I assume this, let's say this is 15 angle 5, this will be, this phase shift will be 5 plus 30, this will be again 5 plus 30, because auto transformer is providing this 0 degree phase shift. Okay, now if I start from here and move here, so if I come from here to here, it is providing me minus 30 phase shift, but if I come from here to here, how much phase shift will be there? Plus 30. If I come from this point to this point, minus 30 phase shift I am getting, but if I go from opposite side, right, from here to here, I will get plus 30. So this will be, this one will be 5, here this will be 5 plus 30, this will be 5 plus 30, right, and this will be what? So if I go from point A to B, the phase shift will be theta. So here the phase at point A is 5 plus theta, so here the phase will be 5 plus theta, 5 plus 30 plus theta. So 5 plus 30 plus theta must be equals to 5 plus 30. So what should be equals to my theta? What should be the value of theta? So because at this node there is only a single potential, so the phase shift also will be same. So I can write here 5 plus 30 plus theta must be equals to 5 plus 30. So my theta must be equals to 0 degree. My theta must be equal to 0 degree. So either, like, only one case I have where the theta is 0. So either it can be delta delta or star star. So it has to be star star 0 degree, because only due to star star phase shift of 0 degree is possible. Any other connection, right? Star delta, delta star, phase shift will be plus 30 or minus 30. Okay. So this question was good. So option A will be correct. So in only one of the options, the phase shift is 0 degrees. Okay. So now let's solve the next question. So here a three-phase alternator generating unbalanced voltage. Now the alternator has unbalanced voltage, is connected to an unbalanced load. So load also is unbalanced. If you see the imaginary part, this is J1 J1, this is J1 J2, J1 J3. The neutral of the alternator and the star point of the load is solidly grounded. So both are solidly grounded. So there will be some path for the zero sequence current. So these are the phase voltages. The positive sequence component of the load current will be. So they are asking me what is the positive sequence component of the load current. So before that, let me find out the currents. IA, IB, IC. What was IA, IB, IC? So IA, if I apply a simple, so I will copy the circuit, KVL, ground to ground KVL. I will start from here, ground, then EA I will cross, and I will end at ground, right? So it's very simple actually. This basically, if I draw the per phase equivalent, so EA is just connected across two reactants. So EA, like IA will be EA divided by G2. Okay. E divided by G2. So EA is 10 angle 0 divided by G2. Right, that is minus 90 basically. Sorry, plus 90. So this will be 5 angle minus 90. What will be your IB? IB will be EB, same relation I will follow, EB divided by, what is the load now? It is J3. And what is your EB value? EB is 10 angle minus 90. 10 minus 90 divided by 390. So this will be actually minus 180. So minus 10 by 3 basically. Okay, and this is basically 5 minus of 5J. Right, just give me 1 second. Now what is my IC? IC will be EC divided by J4, right? J4. So this will be EC is 10 angle plus 120. 10 angle plus 120 divided by 4 angle 90. This will be 2.5 angle 30. Okay, so this is my IC. Now I can use that formula, because they have asked me what? They have asked me to find out the positive sequence component of the load current. How will I find out the positive sequence component of the load current? So I know this, right? IA0, IA1, IA2 equals to, now this will be 1 by 3, right? It is inverse 1 by 3. Now this is 1 1 1 1 1. So here the phase B component needs to come, which used to lack the difference. So it is alpha square, but it is inverse. So alpha square has been replaced with alpha. So this will be alpha, then alpha square, then alpha square, then alpha. This will be my IA, IB, IC, right? So I just need the positive sequence component. So positive sequence component IA1 will be 1 by 3. Okay, 1 by 3, it will be IA plus alpha into IB plus alpha square into IC. Okay, so I will be able to find this out. So IA is basically minus J5 plus alpha into IB. So IB is 10 by like minus 10 by root 3, alpha is plus 1 2, so it is 10 by root 3 minus 60. Okay, because minus 1 is minus 180, I'm adding 120, so it will be minus 60. Okay, and your IC is 2.3 angle 30, and I'm multiplying alpha square, that is I'm subtracting 120, so it will be 2.5 minus 90, right? So basically this will come out to be 1 by 3 minus 7.5 J plus 10 by 3 minus 60. So this will be minus J 2.5 plus 10 by 9 minus 60. Okay, okay, so how will I solve this basically? So I have to solve this. So let me break this down. Let me break this down. So this will be 60 cos into 10 divided by 9. So this will be 0.555 minus J. Okay, so 60 sine into 10 divided by 9 minus 2.5, so 3.462. So this will be equals to whole square plus 0.555 whole square whole under root. So it comes up to be 3.506 angle. This will be 3.462 divided by 0.555 tan inverse. Now remember, which quadrant is this? This is the fourth quadrant, right? Fourth quadrant. So this will be minus 81 degrees. Okay, fourth quadrant, that's why it will be minus theta. All this has been taught in phases, right? So this is the answer basically. The positive sequence component of current will be 3.506 angle minus 81. Okay, this is the solution. I think this was a, okay, this is not a gate PYQ. Okay, let's now solve this one, right? So a generator is connected to a transformer which supplies power to another transformer as shown. The zero sequence impedance values given in per unit on a common base. So these are given on a common base. Determine the Thevenin equivalent zero sequence impedance seen from the point B. So what is the Thevenin equivalent zero sequence impedance seen from the point B? Okay, so this is again, you see star is grounded through a resistor. So what will this become? This will become 3 times R, right? Zero sequence component becomes 3 times R. So this will be 3 times R. So this will be, I will have 3 times 0.25 a resistor here, okay, and this is my point B. Then I have the, because you see both of the stars are grounded, this is solidly grounded, so it will be just short circuit, right? With obviously reactance I have to provide here. Reactance is 0.07, right? So x naught reactance they have provided, that is 0.07. Now it is shorted, that's why I am directly connected. Here it was grounded with a resistor, that's why I have to multiply 3 into Zn. Now here it is just transmission line and no mutual impedance is shown to me, right? And no neutral impedance is shown to me, so I will directly write this zero sequence impedance only, okay? So if you notice one thing, that your zero sequence, what was the transmission line zero sequence impedance? It was Zs plus 2Zm plus 3Zn, right? So in our case this is 0, this is 0, so automatically it is Zs only, whatever is the transmission line impedance. In our case it is reactance, so this will be 0.05, okay. Then if you see here, the neutral is grounded on the star side solidly, so it will be directly grounded, so it will be connected here, this switch will be closed, and then I will draw the reactance, zero sequence reactance, that is J 0.1. Now one interesting thing happens, that here I have a delta. So if I have a delta, then this point will not be connected, it will be directly shorted to the reference bus. I will have a reference bus, right, neutral bus, it will be directly shorted because there will be path for the circulating current to the flow. Circulating current will not come to the generator, even though I have a generator here that is grounded with a resistor and a reactance is also given to me, right? But I will not care about it because there is no path for the zero sequence current to flow. So this will become 3 times 0.25, but this is the reactance, so this will not be multiplied with 3, this will be multiplied with 3 because it is going to ground, okay. So this will be ground, right? This will be connected to reference. Why? Because this is grounded. So now I hope it is clear what is the ZTH seen from here. What have they asked? They've asked me the determine the Thevenin equivalent impedance, zero sequence impedance seen from the left hand side. Now I hope you can easily find it out what is the Thevenin equivalent impedance. So it will be basically, if I say my ZTH will be like this, is this point is closed, right? So this will be equals to, now as they are talking about if impedance, that's why I have shorted the sources, right? So this will be ZTH will be equals to 0.75 plus this is J.12 plus J.1, so this will be J.22, okay, J.22. So this will be equals to what will be the equivalent, like in polar format, so 0.75 into 0.22 whole square whole under root, so 0.1905, so this will be 0.22 divided by 0.75, tan inverse 16 point 35 degrees, okay, 16.35 degrees. So this is the answer basically for this particular question. Now let's move on to the next one. Find the sequence current circulating in the loop if one line is open circuit. So this is just like the open circuit fault. So this is the open circuit fault. So we will see what happens if one line suddenly opens up, right? Open circuit fault. So IA, IB is given to me. I have to find out the sequence circulating current in the loop. How will I find out the sequence circulating current in the loop? Okay. So do you know what is the sequence circulating current in the loop? Do you know what is the sequence circulating current in the loop? So there will be some current IAB, there will be some current BC, and there will be some current IC, right? I know what is a like circulating current basically means the zero sequence component of current. What is a zero sequence component of current? It is 1 by 3 of the sum of the all the three currents. How? I can again come back here. I can I can copy this, right? What is the zero sequence component IA0? It is basically the 1 by 3 IA plus IB plus IC. Okay, so IA plus IB plus IC, right? IA plus IB plus IC. So IA0 is IA plus IB plus IC. Okay, 1 by 3 into IA plus IB plus IC, right? So that is what my IA0 is equals to. That is what my IA0 is equals to. Same thing I will do here. My IA0 will be IAB plus IBC plus IC. So IAB plus IBC plus IC. Now, what is my IAB or what is my IA? So IA is equals to IAB minus ICA. If you observe here, IA is equals to IAB minus ICA. What is my IB is equals to? IB is equals to IBC minus IAB. And IC is simply 0, right? IC 0. So, okay. Can I do anything here? So one more relation I can say that my IC0 which is equals to ICA minus IBC. So from here I can say that ICA will be equals to IBC. So ICA and IBC are same. ICA and IBC are same. So if ICA and IBC are same, so this I can put here, right? So this will become IA will be equals to IAB minus IBC. IB is equals to IBC same, IBC minus IAB, right? So it's anyways. So from here I is negative of IB, which is already given to me. I is negative of IB, right? That is already given to me. What are they asking? Circulating current, right? Okay. So I need to find out IAB. What will be IAB? Okay. What will be my IAB? That is what I am trying to figure out. Actually, IAB is easy. Is IAB easy for us to find out? Yes. So basically, why am I doing all this? This is actually not required. So basically, some IA current is coming here, right? So there are only two paths. Either it will go from here or it will go here, right? So these two are same only, right? Because this current is 0. So I can apply simple current division rule. So what will be IAB? IAB will be IA times the other resistance path divided by the overall resistance, right? So equivalently I can draw the circuit. Like, why am I doing all this? This is not required. What am I doing? So I have this path, right? So here IA current is coming, and here I have two paths, this R and this 2R, right? Because here if you see, they are basically in series. These resistors are in series because there is no current here, right? So there are basically what I can say is this is my IAB. So IAB will be equals to what? IAB will be equals to IA into 2R divided by 3R. So 2 by 3 IA. And what about this current? So actually this is the current that will circulate. So what is this current? So ICA is just negative, right? Because if I apply here, right, if I apply this division, now I will apply this division, that IB is coming here and it is getting divided into this R into this 2R. So what will be this value of current? ICA, which is same as IBC. If you see, IBC and ICA are in the same value because here there is current 0, right? So this will be ICA will be equals to IB into R divided by 3R. So this will be IB divided by 3, which is equals to IBC. So my zero sequence or circulating current IAO will be equals to 1 by 3 of IAB, that is 2 by 3 of IA, plus IB by 3 plus IB by 3. And what do I know about IB and IA? So what do I observe? IA is 1 angle 0, IB is 1 angle 180. So IA is minus of IB. So I can replace here IA with minus of IB. So this will be 1 by 3 into 2 by 3 IB minus of 2 IB. Sorry, this will be minus, this will be plus of 2 IB by 3. So ultimately your circulating current is actually 0. So there is no circulating current. Okay, open circuit fault, there is no circulating current. This is the answer. 0 is the answer. So now let's move on to few summary. I have removed one question because that question, the calculation will go very high and we don't want to like increase our calculations too much. So I have basically removed that question. Okay. So few summary we will discuss. In delta networks, we know that if it's a balanced delta network, right? If the delta network is balanced, so line currents cannot have zero sequence component of current, right? So zero sequence component of current will only circulate in the loop. Already has been discussed. Same thing is written over here. So external line will not have any zero sequence component. For star, if the star is not grounded, there will not be any zero sequence component. But if it is grounded, then there can be zero sequence component, right? So if I ground the star through any impedance, then there can be zero sequence component. Otherwise, zero sequence component will not exist if the neutral is ungrounded. Same thing is written over here. So this is very important point. Very important point, right? Now, briefly, I will discuss about the faults. So we have discussed that most dangerous fault is triple line to ground fault, right? Because here the current is the maximum, but that is with respect to transmission line, because in transmission line, if the current is very high, there will be huge copper losses and it can damage the other components in the transmission line. But for a generator point of view, already I have discussed this previously as well, the most dangerous kind of fault will be single line to ground. Why? Because due to zero sequence component of current, that zero sequence component of current will make my generator unstable. Okay, there will be a negative sequence as well, there will be zero sequence. So generator only generates purely positive sequence components of voltage, right? But if negative sequence and zero sequence components are there, the rotor may rotate in some other direction that can cause the generator to go unstable. That's why for a generator point of view, LG fault is the most dangerous fault. Now one more thing is that this zero sequence component of current, positive sequence component of current and negative sequence component of current, they actually don't flow through the generator. They are all hypothetical. For our understanding, for easily breaking down components, we have made them zero sequence, positive sequence, negative sequence. Actually, the current that flows is I actual through the generator. It is a combination of all the three components, right? But we break them down for our circuit analysis. That's it. Okay, this is one another key point, because Sometimes in interview they can ask, do these currents actually flow in the circuit? No, these do not flow in the circuit. Okay, actually what flows? Actually actual current flows the summation of all the three. So the vector sum of all these three sequence component of current will flow. Okay, one more thing, one more important point that about regarding the sequence impedance. So I know Z1 will be equal to Z2 will be much greater than Z0 for a synchronous machine. And my Z0 will be much greater than Z1 equals to Z2 for a transmission line. Okay, so I hope it is clear. I hope it is clear from here, right? Now what about this one? So here we know that, like, one more summary, that if I have two phasors equal magnitude, phase shift of 60, then the resultant will lie in the middle and its value will be root through times v. Okay, there is one another summary that you can keep in mind. Okay, now few more things I want to explain, right? Few more things I will explain for star connection and for star delta for star connection and for star connection and delta connection. I think it is written over. Okay, it is not written, so it should be written. It is not written now. Okay, there are only questions here. That's bad. Okay, there are only questions, so I will write, basically I will write this, write the point. So this was one of the summary. So for star connection, what happens? For star connection, if I bring the if I bring this voltage only, the line current and the phase current are same. So there is no problem with line current and phase current. But I know the voltages are different. I have line voltage here and phase voltage here. Correct? So for star connection, actually load is wrong. I should not draw the load. That is wrong. I should bring the generator. Right? Generator, yes. We know that my line voltage actually leads the phase voltage. This is my line voltage and this is my phase voltage by 30 degrees for a balanced load. This has been derived in B6 of 3 phase in the first lecture. So everything is important. Everything is important. So for a star, my line voltage will be phase voltage, magnitude of phase voltage times the root 3 times root 3 into angle plus 30 degrees. Okay, so angle will be plus 30 degrees. So magnitude root 3 into V phase into plus 30. Okay, that is what my line voltage is. Line voltage will lead the phase voltage by 30 degrees for a positive sequence. For a positive sequence. So if it's a positive sequence, then it will lead positive sequence. Correct. For a negative sequence, the line voltage actually just will be opposite. For a negative sequence, it will be opposite. It will be root 3 times V phase, it will lag minus 30 for negative sequence. Okay, so this will lead, this will lag. So this thing you should keep in mind, right? The voltage, what happens to the line voltage and the phase voltage. Okay, and for star, the line current and the phase current are same. So I line will be equals to I phase. So these are very, very important conclusions. Okay, these are very, very important conclusions. For delta, one more thing for star is that for star, line voltage will not have any zero sequence component because it is equals to VA minus VB. So if phase A and phase B has zero sequence component, automatically it will get cancelled, right? That is one important conclusion. Now for delta connection, what will happen? For delta connection, if I copy this thing, right, for delta, I will not have the neutral. For delta connection, I know my line voltage and phase voltage will be same, right? Because this is my line voltage. This is my phase voltage. Okay, so I will just draw in brief. For delta, line and phase voltage are same, right? But currents are different. Currents we have to see. So here I will have the current IA. This current will be IAB. This current will be opposite. So ICA. This current will be IB. This current will be BC, right? Yes, and this current will be IC. Okay, so this is my IA. So in case of delta, what will happen? In case of delta, my I line current, right? I line current will be root 3 times the phase current. Okay, and it will be just opposite. So delta and star are dual of each other. So I think, okay, I think this has been covered in basics of 3 phase. That's why I'm remembering. So I'm just revising this again. So this will be, the angle will be minus 30, not plus 30. Angle will be minus 30. So for positive sequence component of current, the line current will lag the phase current by 30 degrees. For negative sequence component, the line current will lead the phase current by 30 degrees. Okay, line current will lead the phase current by 30 degrees. So this will happen for negative phase sequence, right? This will lead. Okay, now here one small doubt can be there. One more thing, that zero sequence component of line current, say line current will have no zero sequence component of current. Same reason as the star for voltage, no zero sequence component. Okay, now one important point, you might have a doubt, sir, which phase current should I choose? Should I choose this one or this one? Here it's very easy for me to tell, it will be IAB, right? So basically this relation will be IA will be equals to root 3 times IAB angle minus 30 for positive phase sequence, and IA will be equals to, so IA1 will be this, IA2 will be root 3 times IAB plus 30 for, so this will be IAB1, IAB2 for negative phase sequence, right? Okay, now you might have a doubt, sir, what if here IAB is not written, ICA this is not written, how will I identify? So basically you choose that current which is along the direction of line current. So out of these two currents, IAB and ICA, which one is along the direction of IAB? So that's why here IAB was here, not ICA. So this is very important doubt, and no one will clear, right? I know this doubt will be throughout your preparation journey. So I wanted to clear this doubt. So this IAB and IA has the same direction. ICA does not have the same direction. Okay, this IAB and IA has the same direction. That's why IAB is written here, the positive and negative sequence current. Okay, and voltage, basically line voltage, this is what delta, right? Delta connection. I know my line voltage is same as phase voltage. That is already understood. Okay, so I hope it is clear. So let's solve the question. The current of a single phase load from a three phase system has, okay, it is a single phase load. So if it is a single phase load, what will be the current taken? What will be the current? Basically the current of a single phase load drawn from a three phase system. So it's a single phase load. Single phase load, one point will be grounded. Okay, what will be the current taken, they are asking me, right? What will be the current taken? Okay, so here I will have this voltage source connected. Let's say balanced three phase voltage source is connected, and the other points are basically open circuit. Here there is no current, and neutral is connected, right? Neutral is connected. So it's a single phase load. If it's a single phase load, right, so first thing is there will be some current in the neutral, because like these are open circuit. So current in, let's say this is phase A, like EA, EB, EC. So current in A is 0, current in C is 0, because these are open-ended. Only a single phase load is connected. So through EA, IA current will go, right? IA current will come here, and it will go to ground. So of course your neutral current is not 0. That means zero sequence component has to exist, right? Negative sequence component current more than positive sequence zero sequence component equal, negative sequence less than positive. Okay, so zero sequence component of current will exist. So IA naught cannot be equal to 0. It has to exist. Now I can easily find out the like symmetrical components here, very easy to find out, right? So I know IA0, IA1, IA2 will be equals to 1 by 3, 1 1 1 1 1 1. Now alpha square should have come, but this is inverse. So here alpha will come, this will be alpha square, this will be alpha square, this will be alpha. And what are the phase currents? It is IA over here 0 0. Okay, so what is my IA0? IA0 is basically 1 by 3 into IA. What is my IA1? IA1 is equals to 1 by 3 into IA, right? Just doing matrix multiplication. What is my IA2? IA2 is equals to 1 by 3 into IA. So what is happening? So basically all the sequence components are equal, right? IA0, IA1, IA2 all are equal. So positive, negative, zero sequence components will be equal. So option C will be the correct answer for this particular question. It's a very elegant question, okay? Very simple yet bit difficult to understand, okay? Let's now solve this one. If phase conductors of a three-phase line shielded magnetically, okay, flux does not link the other, right, with another, then positive, negative sequence, zero sequence impedance of the line will be what? So basically they are telling me that flux of one of the conductor will not link with the flux of the other conductor. That basically means my Zm will be 0 because there is no mutual coupling, right? No magnetic coupling. So no magnetic coupling. Okay, there is no magnetic coupling. There is no magnetic coupling. So Zm is 0. That much is sure, right? Zm is 0, and they have not discussed about anything about the neutral impedance. So I will assume Zn to be also 0, right? Nothing is mentioned. Zm also I will assume to be 0. So what is my zero sequence impedance? It was actually Zs plus 2 Zm plus 3 Zn. Okay. So Zm is 0, Zn is 0. So this will be Zs. Z0. So Z0 will be equals to Zs. Okay. Now what about Z1? Z1 is Zs minus Zm, and Zm is 0. So it will be Zs, which is equals to Z2, because Z2 is also Zs minus Zm. So from this relation, if there is no magnetic coupling, I can say Z1 will be equals to Z2 will be equals to Z0. So option D will be the correct answer for this particular question. Okay. So let's solve the next one. So a zero sequence current can flow from a line in the transformer bank if the windings are in, okay, so zero sequence current can flow here if there is some zero sequence current in the delta. How the zero sequence current can flow here? How it can flow? So we need to ground the neutral, right? So we need to ground the star. So grounded star and delta. Delta zero sequence current can flow, but for zero sequence current to flow in the primary side, the star must be grounded, right? So option A will be correct, grounded star. So this is the last question that we will solve. So we have to for the following delta circuit, we have to compute its star equivalent. Okay. Also the compute the overall power consumed in the circuit. So previously I told you, right, how to compute the star equivalent. So how do I? So this is not a balanced supply. If this is not a balanced supply, I told you that we can compute a star equivalent because there I told you that delta was balanced. If delta was balanced, it was very easy to compute the star equivalent. But what if delta is not balanced? How will I find out the voltage EA, EB, EC? If delta is not balanced, right? This is not balanced. Then first of all, you have to find out in delta itself the positive sequence component, negative sequence component, and zero sequence component. So the V delta will have V delta 0 plus V delta 1 plus V delta 2. Now I can convert this into star. So what will be the star equivalent of this? So zero sequence component, there will not be any division, right, of root 3 or minus because it is zero sequence. So all of them are in same phase. So zero sequence component of star and delta will be same. But what about zero sequence component of so what about the positive sequence component and the negative sequence component? Okay. Zero sequence component of star and delta will be same. They will not be different because all of them are in same phase. But for positive sequence component, it will be 1 by root 3 times V delta 1 magnitude, and this will be 1 by root 3 times V delta 1. So the magnitude will be reduced by 1 by root 3. Correct? Magnitude will be reduced by 1 by root 3. And what will happen to the phase? So for delta, it is the line voltage, right? I'm going to phase voltage. So basically I want to measure the phase voltage in star. So line voltage will be V delta. So here, right, this voltage and this voltage are same, right? Phase AB voltage and here phase AB voltage are same. But I want to find out the star equivalent. So I know the phase voltage for a positive phase sequence, the phase voltage lags the line voltage by 30 degrees, or the line voltage leads the phase voltage by 30 degrees, just has been covered in today's lecture. So this will be V delta 1 because it is the line voltage, right? This is the V delta is the line voltage here, right? So it will lag. There will be minus 30 here, and with the negative sequence component, so this will be V delta 2. It will lead, right? Just the opposite. So that's how you will break it down. So I will explain one by one how to break it down. So first of all, of course, I have to find out the zero sequence, negative sequence, and the positive sequence component. So of the voltage. So this will be my VA0, VA1, VA2, one, one, one. This will be alpha, this will be alpha square, alpha. Okay, so this will be VA, VB, and VC. So VA0 will be what? VA0 is just the sum of the three components, right? So 1 by 3 VA plus VB plus VC. So in this case, it is 100 plus J100, right? 100 root 3 minus 45. So it is basically one by 3 100 angle 0 plus J100. So VB is J100, or okay, no, sorry, this is my V, it is my VAB, and actually the dot here is wrong, right? Dot should be here or here only. No, sorry, dot should be here only. And this is my VBC, and this is my VCA. Actually these are the line voltages. I should have written here line voltage, not phase voltage, line voltage, right? So this will be VAB0, VAB1, VAB2. This will be VAB, VBC, VCA. So this will be VAB is this, VBC is 100 angle 100 root 2 angle minus 135, and VBC is 100 angle plus 90. So I know this, right? This is what? This is 100 plus J100, which is 100 angle 100 root 2. What is the angle? Plus 45. So addition of these two components will be here. So here I have 100, here I have 100, right? So the addition of these two will be here, 100 root 2 plus 45. And where is 100 root 2 minus 135? 100 root 2 minus 135 will be exactly here, right? If you see, this much is 90, another 45. This angle is also 45. Right? It's just a bisector. So basically, your zero sequence component of current will be 0. and actually it has to be 0. Why it has to be 0? Because in delta, in line voltage, 0 sequence cannot exist, right? Otherwise it's not proper, right? So this has to be 0. This is 0. Now what about VA1? What is VA1? VA1 is equals to 1 by 3 of VA0. Okay, VAB0, sorry, VAB into alpha into VBC. So VAB is 100 angle 0 into alpha into VBC. VBC is this. I will multiply alpha. So this will be 100 root 2 angle minus 15 degrees plus alpha into alpha square into VCA, that is this will be 100 minus 30. So this will be equals to so how will I add this, right? So how will I add this? Basically that is what I want to know. So again this is 100 only. So again its resultant will be in the bisector only, but this time the angle it will be 15 only, but it will not be exactly 100 root 2. That is the problem. The angle will be 15 only, but it will not be exactly bisector. So okay, so basically I have here 100, I have here 100, right, minus 100, right? So this is minus 30, 100. So its resultant will be somewhere here only, but what will be the magnitude? What will be the magnitude? So for finding out the magnitude, we can do this formula, right? What is the magnitude of V? This will be under root 100 square plus 100 square plus, will it be exactly bisector? Kind of no, right? Okay, I can break it down, right? I can break it down actually. So this is 100, right? So it will have two components. One will be this component, that is 100 sine 30. Sine 30 is 1 by 2, right? Another one will be along this component 100 cos 30, that will be root 3 by 2, right? So overall, actually sorry, it will not be angle bisector. Overall it will be 50 root 3 here plus 100, right? In the x direction, in the negative y direction it is 50. Okay, so what will be the resultant? Resultant will be, okay, I have this one as well, right? This component is also there. So let me add this component as well. If I'm adding this one, so let me add this one. Okay, let me add this one as well, right? So this one, what will be this one? So another vector is there, that is between this, right? That is magnitude is 100 root 2 and it is minus 15, angle is minus 15, right? So it will have one component here, that will be 100 root 2 cos of 15, and one component here, it will be 100 root 2 sine of 15, right? So what is 100 root 2 into sine of 15? So it is 36 point, so here I will add this component 36.6 and plus what is 100 root 2 cos of 15, right? Cos of 15 into 100 into root 2, it comes out to be 136.6. Am I absolutely correct? I will just quickly cross verify. 100 into root 2, 100 into root 2 into sine of 15. So yeah, it is correct. So now I got all the equivalent values along x and along y. So 50 into root 3 plus 100 plus 136.6. So this will come out to be 23.2, and this will come out to be 86.6. Okay, so 323.2, 86.6. So this whole square plus 86.6 whole square whole under root, this comes out to be 334 divided by 3, so it will come out to be 111. So your VA1 comes out to be 111. Okay, and what will be your angle? Angle I have to find out. So angle will be 86.6 divided by 323.2 tan inverse. So it is almost minus 15, right? So okay, it will be along this direction only, along minus 15 only. How is it possible? Okay, I don't know how is it possible, but it is minus 15 only. Okay, minus 15 because it is in the fourth quadrant. Okay, so this will be minus 15 VA1, right? What will be VA2? VA2 will be 1 by 3. Now it will be 100 angle 0. It will be, this time it will be alpha square into VBC. So alpha square into VBC, that is minus 120 will multiply with minus 135, that is minus 255. So this will be minus 255 plus alpha into VCA. Alpha into VCA is 120 plus 90, that is 210 degrees. So this will be 100 root 2, right? This will be 100 root 2. So this will be 210. So if I add and subtract 360, right, this will be even better. So this will be 100 angle 0 plus 100 root 2 let me just check this once more. 100 root 2 is 141.2, right, into cos of 15. Yeah, it is correct. To sine of 15 into, yeah, that is what. So this plus 105, I'm adding 360 and here I'm subtracting 360. This will be 100 angle minus 150. So what will be these components? What will be these values? So this will be a bit difficult. Okay, this will be a bit difficult to tackle. So I have a vector here that is 100 angle 0. Right. I have another vector here that is 100 angle plus 105. So plus 105, 100 root 2 plus 105 will be somewhere here. Right. 100 root 2 plus 105. And I will have the vector component here. Right. So this is 90. This whole is 105. So this will be 15. And this is 100 angle minus 150, so minus 150, this is total 90, so minus 150 will be somewhere here. (100 minus 150), right? So what will be this angle? So this whole angle is 150, this much is 90, so this will be 60, right? So I can break this down again. So this will have two components, one will be along here, 100 cos 60. So what will be 100 cos 60? It is half, so it will be 50. 100 sin 50 will be here, right? That will be 50 root 3. This 100 root 2 also will have two components, 100 cos 15, 100 root 2 cos 15. So 100 into root 2 into cos of 15. So this will be 136.6. And 100 sine of 15. 100 sine of 15 also will be in this direction, 36.6. So 141.2 into sine of 15 is 36.6. Okay, so 100 root 2 is here, actually it is here, 36.6. Now it is very simple, right? So along the left hand side, what is the total value? So along the left hand side, it is 36.6 plus 50 into root 3. So it comes out to be 123. 123.14. And now here in the bottom I have 50, here in the top I have 136. So overall I will have resultant in the top. So 136.6 minus 50 is coming out to be 86.6. Okay, so now what will be the resultant? If you see, overall resultant is on the left hand side, 100 minus this, right? Overall resultant is on the left hand side, that is 23.14, and on the top. So overall my resultant vector will lie in this quadrant, right? So overall resultant will be 23.4 and this whole square, right? So 86.6 whole square plus 23.14 whole square whole under root will come out to be 89 divided by 3, because a division is there by 3. So approximately it comes out to be 30. Angle will be what? So angle will be y component upon the x component. It is lying on the fourth quadrant, sorry, not on the second quadrant. So it is it will be, now this is coming out to be 75 in this direction, right? So it will be 180 minus theta, 180 minus theta, it will be 105 degrees. So I will not explain how to calculate angle and all these things. All these have been explained in network theory. All these have been explained in network theory. That's why we made our base very strong. Okay. Okay, I hope it is clear now. Now, will you be able to find out the positive sequence equivalent? So what will be the positive sequence equivalent? So positive sequence equivalent, right, will be this VA1, right? So what will be the okay, this is still in delta, I don't want in delta, right? So I want to just solve the first one. So what will be my EA? They have asked me E. What will be my EA? So EA will be equals to my EA0, that is 0, right? EA0 is 0 simply. EA0 is 0, it is gone, plus my EA1 plus my EA2, which is equals to EA0 is 0, right? This is 0, right? Because VA0 is 0, right? There is no 0 seconds component. What is my EA1 and EA2? What is my EA1 and EA2, right? So EA1 will be VA1 lagging by 30 degrees, right? So it will be VA1 lag 30 plus VA2 lead 30, right? Because it is the negative phase sequence component, so it will lead VA2 by 30 degrees, right? So one doubt I am having, how will I find out so the 0 sequence component? That is what I am thinking, because VA1 VA2 I will be able to find out for delta, right? Anyways 0 sequence component gets cancelled, 0 sequence component is not there. Okay, actually this overall thing is kind of wrong. We will not be able to find out the 0 sequence component of EA, EC, EV. That is not possible. Yeah, because why? Because when you find out the line voltages, the 0 sequence components gets cancelled, right? So you will not be able to find out the 0 sequence component, because in line voltage 0 sequence component never exists. So actually this we should have only asked the convert the following delta circuit to star equivalent and to star equivalent positive sequence and negative sequence network. Okay, because 0 sequence you will not be able to find out. I'm sorry, this is wrong. This is wrong. I made a mistake here. This is wrong. I have to figure out. I have to study about this. How can I convert 0 sequence star to delta? Because no, you cannot. Because in delta 0 sequence does not exist. So this is wrong. So that's why I was also thinking I'm doing something wrong, right? So you can only, this is not 0 actually. This is wrong. So you can only comment about EA1 and EA2. So what will be your EA1 equivalent star EA1, that will be VA1 plus minus 30, and your EA2 will be VA2 minus 30, and from there you can easily find out what will be EB1, EB2, like just plus 120 minus 120, just use the alpha operator, right? So this was the first part, and second part they are asking what is the overall power consumed in the circuit. Okay, I forgot to actually draw the load, right? Load I forgot to draw. Okay, this has to be balanced load, I forgot to draw this, sorry about this. So okay. So how do I find out the, like I have to change this on that circuit as well, right? There as well, to change this question actually. So if you guys know about the zero sequence component, you can let me know. I don't have the time to study again. Okay, so I'm not able to, because like these things no one will even teach you, no one will even touch, right? You go and check in any other notes, okay? Any coaching, like those big famous coaching, the two famous coachings are there and one independent coaching is there. They will not even do this, right? I'm doing this. Okay, I'm studying extra things. Trust me, right? We are researching so much, and like this needs reach. Basically, this needs reach. If you are finding something new, right? If anyone has studied like something like this, just tell me. It will not be present in any coaching notes. None of the coaching notes. Okay, so that's why like I have not studied this one about the zero sequence component. So this I have to study. Okay, so yeah. So what we will do is we have to find out the power consumed. They have asked me to find out the power consumed. So I have already found out the positive negative sequence network. I can convert this star into delta, right? And then I can simply find out the power consumed. It is just like the voltage here is, I know the voltage, right? What is the voltage here? Magnitude of the voltage. What is the magnitude of the voltage? Magnitude of the voltage is 100, right? This voltage was 100 if I remember correctly. This was 100 angle 0, 100 angle root 2, and this is 90. So this will be 100 angle 0, this will be 100 angle 100 root 2 angle minus 135, this will be 100 angle plus 90, right? So the main thing is how do you find out the power dissipated across a resistor? Voltage whole square divided by the resistance, right? So it's very simple. So because the magnitude of the voltage is known to me, that is 100, it is a line voltage. So I have converted this star into delta. So this will be 100 whole square divided by 3, and power will simply get added. So here the power consumed is this much, 100 whole square divided by 3. Here what will be the power consumed? Because there are 3 components, it will be 100 whole square divided by 3 plus 100 whole square divided by 3, because I am only concerned about the magnitude. So this will basically be 100 whole square, that is basically 10 kilowatt. So the power consumed will be simply 10 kilowatt. This will be the answer of this question part 2, and part 1 is already solved over here, right? So yeah, I hope it is clear. This question is clear. This question was the interesting question. This is no coaching will take this question, right? So yeah, I hope you've enjoyed this lecture. With this, we have finished completely our our symmetrical components. Now we will move on to the unsymmetrical faults. So we will try to analyze what happens in unsymmetrical faults. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone. So today we will be discussing about unsymmetrical faults. So in the previous lecture we discussed about symmetrical components. So now finally we are in that state of zone where we will be able to analyze unsymmetrical faults. So there will be 2 lectures. First lecture will be mainly understanding different types of unsymmetrical faults, drawing the sequence networks, and yeah, that's it basically. And the next lecture will be numericals, right? We'll do few questions. So unsymmetrical faults, as you remember, we had discussed when the post fault condition, right? The system is not balanced. In the post fault condition, the system is not balanced. Now I hope it is clear. I hope it is clear that what do I mean by balanced system and what do I mean by not balanced system. So there are many kinds of unsymmetrical faults like short circuit fault, right? And open circuit faults are also unsymmetrical because the voltages are not balanced and currents are not balanced. So let's say it's a single line open circuit fault. That means in one of the line current is 0, in the other two lines there is current. So the currents are not balanced, right? So that is also a unsymmetrical fault. So the most common type of unsymmetrical fault is line to ground fault. Then we have line to line fault and line to ground fault, right? So these ZF are the fault impedance. So if some wire is shorted, right, the wire might have some impedance. So to consider that, we have considered ZF as the fault impedance either to ground or through the between the two lines. Okay. So these three are my main short circuit unsymmetrical fault. Now, are these only the short circuit unsymmetrical fault? Will my, like this, if I draw this circuit, right? If I draw this power system, let's say I have a winding like three-phase winding whose reactances are shown. Let's say this reactance is J 0.3, J 0.2, J 0.1, and this is phase A, phase B, phase C, and let's say there happens a triple LG fault. Now, is this symmetrical? You will say, sir, we have learned that triple LG fault is symmetrical. But is it? It is not symmetrical. No one will tell you all these things, right? So it is not symmetrical. It is a unsymmetrical fault. It is a type of unsymmetrical fault. Although triple LG fault in itself is symmetrical, but I know that post fault the impedances are not balanced. If the impedances are not balanced, that means it becomes a unsymmetrical fault. So post fault condition impedance are not balanced. How do we solve this? So you have to do the rigorous analysis. You have to do the rigorous analysis, that is you have to do symmetrical components. You have to break down the currents and voltages to symmetrical components. How? I will explain with LG, LL and LLG fault. There, if you understand the analysis, if you understand the derivation, you will be able to solve these kind of questions, right? So symmetrical, we have to take help of symmetrical components. Okay, we have to take help of symmetrical components. Okay, so these are the short circuit faults. We have open circuit, let's say one line open circuit, two open circuit fault. So here the currents are 0, right? Here the current is 0. So but through here there is balance current, but through one of the phases current is 0. Here also the current is 0. Here the current is 0, but through here I have a balance current. So this becomes a unsymmetrical fault. This also becomes a unsymmetrical fault. Okay, so this is what my open circuit is. You will be able to understand how to derive the voltages here as well, right? We have done a question like this, one line open circuit fault in the previous lecture where it was delta connected, right? So like that you have to do the rigorous analysis. So let's first analyze the most common and the most dangerous for alternators, that is single line to ground fault. Single line to ground fault happens when one of the phases is connected to directly to ground suddenly through a fault impedance ZF, right? So one of the phases suddenly goes to ground through the fault impedance ZF, right? So let's see from a generator perspective what happens. So other two phases will work as it is, but suddenly through phase A it will not supply the load, it will supply the ZF, while ZF will be very low value. Okay, so here few assumptions we have to take always during unsymmetrical fault analysis. So what are the assumptions? Assumptions for unsymmetrical fault analysis, that pre-fault condition, we will take pre-fault condition as no load. Why? Because that will provide me the maximum terminal voltage so that I am able to calculate the maximum short circuit current. So pre-fault voltage will be no load. Sorry, pre-fault condition will be no load condition. Okay, that is fixed. Pre-fault is no load condition. Now that is one of the assumption, right? So now here, if I want to analyze this, so what is the pre-fault condition? So pre-fault condition, I have told you, is no load. If it is no load, that pre-fault, that means my IA current will be equals to IB current will be equals to IC current, that is 0 ampere. Yeah, they are phase shifted by 120, but it is 0 ampere, so it does not matter if it is balanced or not balanced, right? It is 0 ampere. That is my pre-fault current, right? Now what is the post-fault condition? So pre-fault, one more thing is there. What is VA? So as there is no load, so VA will be equals to EA, right? Because here also neutral current is 0. So this is virtual ground, right? This point will be virtual ground. Virtual ground. So VA will be equals to EA. VB will be equals to EB. So I have also changed the reactance to XG, right? Because otherwise there will be confusion. I just pause the video and change the reactance to XG. EB and VC will be equals to EC. Now what about the post fault? So post fault, what will happen? Post fault, suddenly what will happen? This will be connected here, right? So these are still at no load, right? So IB and IC are still at no load. So IB is equals to IC is equals to 0. They are still at no load, but IA will be not equal to 0. Okay, and my VA will not be equals to EA, right? VB will be equals to EB, VC will be equals to EC. Okay, VB will be equals to EB and VC will be equals to EC. Now, so I can observe that the phase A is unbalanced, right? So if I break this phase A into 0 sequence, positive sequence and negative sequence, so I know my IA current, because other currents are anywhere 0, I know my IA current will be combination of IA0 plus IA1 plus IA2, right? So I can obviously use this matrix, right, in which I know that IB and IC are 0, right? IB and IC are 0. So this will be equals to 1 by 3, right? This I can copy directly. IB and IC will be simply 0. One more thing you have to understand is that what will be your like what are these components? What is IA0, IA1, IA2? Let me find out what are each components, right? Okay. So one more point I want to say. So my supply here, whatever power will be delivered, that will be delivered by EA, right? Because here the current is 0. Here the current is 0. So this voltage source is delivering 0 current. This voltage source is delivering 0 current. So power is 0 due to these two voltage sources. So LG fault MVA will be only due to EA. So EA is unbalanced. So we have derived the formula for unbalanced power, right, using symmetrical components. So what was that formula? The formula was, if I have a voltage source EA, so it will be EA1 into IA1 conjugate. There was a multiplication of 3 as well, plus EA2 into IA2 conjugate plus A0 into I0 conjugate, okay, into 3, because I have 3 phases. Okay, this was the formula for 3-phase power using symmetrical components. But for LG fault, what will be the LG fault MVA? LG fault MVA. So LG fault MVA will be, I know my uh, okay, IB and IC are 0. My IB and IC are 0. I know my machine, right, is balanced. Machine is balanced. So I know my machine is balanced. So I know one more assumption is my supply is balanced. Okay. So if supply is balanced, that means all EA, EB and EC are phase shifted by 120 degree, and basically they don't have any. So EA0 will be 0, EA2 also will be 0, right? They will not have any positive, or they will not have any negative or 0 sequence component. Okay, so this will be LG fault MVA. So my EA2 and EA0 will be 0, right? Because my supply is balanced. So ultimately my LG fault MVA will come out to be 3 times EA1 IA1 star. Okay, and of course we will find out what is my IA1 from here, right? I don't even need to find out IA0 and IA2 for finding out the LG fault MVA. Okay, so yeah, this is the overall 3-phase fault MVA. For single phase it will be divided by 3. Okay, remember this is the 3-phase fault MVA. 3-phase fault MVA. Okay, now this is the actual value per unit. You can simply divide by the base of the system, and you will get your value. You will get your LG fault MVA in per unit. So I know my IA0, IA1, IA2, right? IA0, so what will be my IA? What will be my IA0? What will be my IA0? So IA0 will be IA1. So it will be IA by 3. IA0 will be simply IA by 3 because others are 0. So IA0 is IA by 3. What about IA1? What is IA1? IA1 is also IA by 3. IA1 is also IA by 3. What about IA2? IA2 is also IA by 3. IA2 is also IA by 3. Okay. So what does it mean? So all the sequence currents are same. So all sequence currents are same in LG fault. When current becomes same, when does current become same? When they are in series. So basically all sequence network will be in series. So now let us draw the individual sequence networks. Let us draw the individual sequence networks. Okay. So if I draw the individual sequence network, so the sequence network for like positive sequence network will be what? It will be EA, JG, and this will be included. No, this will not be included because this is connected to ground, or this will be included. No, this point is common point. I just want to find out the sequence impedance till point A, right? Till point A. Okay. So till point A, I know the sequence impedance. What will be the positive sequence impedance, negative sequence impedance, and zero sequence impedance. So till point A. So this is my point A, right? Till this point, what is the positive sequence impedance seen from the left hand side? It is JXG will be there. It is a positive sequence impedance, and EA will be there because it is the voltage, positive sequence voltage. And let's assume that XG has a positive sequence impedance as XG1. Okay, so this is my JXG 1. Okay, and then I will have the voltage source, that is E. Okay, then I have the voltage source, that is EA. So then I know this is the positive sequence current that will flow through the positive sequence network, that is IA1, and what will be the potential, that is VA1 across the positive sequence network, right? So what is the negative sequence? In negative sequence I will have a reactance, that is JXG2, but I will not have the voltage because voltage will not be present. JXG2. Okay, then what will be the zero sequence? So zero sequence, the generator will provide JXG0. Also remember, in zero sequence neutral will come into action, so this JXN will become 3XN. So all these have been covered in the previous chapter, right? So I will have the generator zero sequence reactance plus the neutral reactance, that will be 3 times because the zero sequence current will become 3 times, right? So it will become 3XN, and this will be connected to ground, that is the reference. And here again I see that ZF is directly connected to the ground, so this point will be here where ZF is directly connected to ground. And since this is also connected to ground, remember this also will become 3ZF. Okay, don't make this mistake. Since this is also like through here zero sequence current is flowing, so this will also become 3ZF. This will also become 3ZF because zero sequence current is flowing, because through this wherever zero sequence current flows, like it is flowing through ground, right? Zero sequence current is flowing through ground, so this will become 3ZF. Now why this does not becomes, why these does not become 3xg1, 3xg2, xg0? Because their impedance is always already measured with respect to their sequence. So with respect to positive sequence, I already know it will provide xg1. With respect to negative sequence, I already know it will provide xg2. With respect to zero sequence, I already know it will provide xg0. But here the normal reactance is xn, but if I am drawing the zero sequence, it will be 3xn. Here the normal impedance is zf, but with zero sequence it will be 3 times zf. Okay, so now finally we can calculate the value of the fault current. So this will be my IA2, this will be my IA0. Basically all of them I have connected in series, right? You see all of them are connected in series, as we can see from here as well. IA0 will be equals to IA1 will be equals to IA2, that is IA. What is IA? If you see what is IA, IA basically is the fault current, right? IA is the fault current. IA is the fault current. So IA will be equals to IF. So from here I can directly say what is IA0 or any current. All these are in series. So my IA0 will be equals to EA divided by all of the reactances. It will be JXG1 plus JXG2 plus JXG0 plus 3JXN plus 3ZF. So JXG1 plus JXG2 plus JXG0 plus J3XN plus 3ZN. Okay, now this is my IA0, but what is my fault current? I know IA0 is IA by 3 and IA is IF. So I can say from here this is IA by 3, that is equals to IF by 3. So IF will be equals to 3 EA divided by this value. Okay. Okay, this is what my fault current is. So this is a very, very important relation that you must, like, you don't need to remember, you need to remember the circuit. Circuit is the most important one, right? Now can I prove it that what is this? This point potential is VA. So basically I can say my VA is equals to VA0 plus VA1 plus VA2, right? You can see this potential is VA2 and this potential is VA0. So everything is matching basically, because I already know VA will be equals to VA1 VA2 plus VA0. Okay, now how will I find out VA? What is VA? So VA will be, if they ask you what is the voltage at the point E, VA will be this current, whatever current is flowing, that is IA1, right? What is IA1? Hold on a second. Yeah, VA will be IA1 or IA0, that is this value. So VA is equals to 3 times IA0 times ZF, right? Because this is 3 ZF here, this becomes 3 ZF. So V is equals to IA0 times 3 ZF, or you can directly say VA will be equals to IF into ZF. It's very simple. Here also it follows the same relation, right? If you see here, yes, it is correct. VA will be equals to IF into ZF, right? I know IF, I will be able to find out the VA value. I know IF, I will be able to find out VF. What is IF? This value, right? So now there are few special cases. Now if you are able to find out VA, so your potential VC and VB also will change actually. Your potential VC and VB also will change, right? What will be your VB and VC, right? Your VB and VC will change. So your VB is equals to what? VB is equals to VBO plus VB1 plus VC VB2, right? So VBO is simply VO plus VB1 will be alpha square times VA1 plus alpha times VA2. So your VB also will change, right? This potential, this node potential will try to change because unbalanced currents are flowing. So EA potential develop will change. So all these will change basically. VB will change, VC will change, right? So they can ask you the potential at point B. The potential at point B will be this value. The potential at point B due to the fault will be this. So all these values will change. So this is how you can find VA. Now there are few special cases. Okay, there are few special cases, right? What are those special cases? So the first special case is when if my alternator is not grounded. If my alternator is not grounded, that is my Xn is infinity, that means there is no possibility for zero sequence current to flow. That means the IA0 will be 0. That means my fault current also will be 0. Is it valid on the formula? Yes. If my Xn goes to infinity, fault current goes to 0. Okay, that is one important point. And you can replace your Xn with some reactance as well. You can replace that. That is, I hope that is understood. Like I can solidly ground it. If I solidly ground it, right, what will happen? This formula, this will go to 0. So do you need to remember the formula? No. Remember the circuit and remember this thing, right? All sequence networks will be in series. For a LG fault, all sequence networks will be in series. You have to remember this. This part and this part. So these parts you have to remember. Okay, all sequence currents are same in LG fault. All sequence networks will be in series. These two things you have to remember. Okay, so you don't have to remember the formulae as per, but you have to remember the concept, right? What will be VA? All these things you have to remember. right? Like you have to understand, no need to remember, but you have to understand so that you will be able to solve it in the exam hall. So if xn is 0, simply it will be solidly grounded. So you can put here xn 0. Xn can be anything. It can be like purely real, or it can be like complex number as well. Anything, it can be anything, right? Your fault impedance also, a special case will be when it goes to 0. If fault impedance is 0, then this ZF, sorry, this is not Zn, sorry, this will be ZF, right? This will be ZF. This is not Zn, sorry, ZF. Yeah. So if fault impedance goes to 0, this value will go to 0, so automatically your fault current also will change. Okay. So or your fault impedance can be purely resistive or inductive. I hope that part you will be able to solve. That part you will be able to solve. Now what is the problem if xn goes to 0? If xn goes to 0, you say fault current is 0, but of course suddenly if you short circuit something, fault current actually wanted to go to very high value, but your short circuit, so there will be arcing. There will be arcing if you don't ground the neutral. So you have to provide path of zero sequence current, right? So there will be arcing. Okay, that is bad, can damage the insulations. Okay, that's it basically. LG fault is this much only. So let's solve a question. Pause the video, try this question by yourself, and then I will come back with the solution. Now before starting this question, few more points I want to explain. Is that why? Because in the previous lectures I have explained that the LG fault is more dangerous than the three-phase fault. Can I here show it to you that it is more dangerous than three-phase fault? So why is, like, theoretically I have explained there will be unbalanced nature that will basically damage the alternator. Why LG fault? But numerically can I explain? So why LG fault is more dangerous than dangerous than LLG fault on terminals of generator. Numerical explanation. So I know I have a generator here, right? It's a three-phase generator. It will have some xg. Drawing is very bad, ignore. So we have a three-phase fault, right? If I have a three-phase fault, this will be the fault current. What will be the fault current? IF. I can do the per phase analysis, right? If this is grounded, so per phase analysis, this will be Eg, right? This will be Eg, and this will be this will be A basically. So I know that we are doing it is a symmetrical fault, pre-fault, post-fault, it is balanced. So the fault current IF will be what? IF will be, because there is no ZF here, IF will be simply per phase voltage upon the per phase reactance xg1. Okay, that is what my IF is equals to. Now if this was the IF LLG fault, if I talk about IF LG fault, now I will consider the case where my neutral is solidly grounded, and where my neutral is solidly grounded, and the the fault impedance is 0. So what will this become? What will this become? So this will be 3EA xg1 xg2 plus xg0, right? 3EA xg1 xg2 plus xg0, because this is 0 and this is 0. So it will be 3EA xg0 plus xg1 plus j xg0, sorry, xg2. Now one more thing I will say, is that if I multiply and divide by 3, this is 3EA by j xg1. So we have multiply and divide by 3EA by 3xg1. So I know this, that my xg1 is equals to xg2 almost roughly, and it is much greater than x0. X0 is much lower. So what can I say? I can say 3xg1 will be much greater than xg0 plus xg1 plus xg2. Why? Because even though these are equal, but xg0 is much lower than xg1, but I'm multiplying by 3. So basically this term will be much lower than 3xg1. So I hope it is understandable. X0 is much lower. So here, if I assume all of them to be equal, this becomes same, right? 3x, this becomes same, 3xg1. But I know xg0 is lower. So let's take few numbers. So let's take xg1 equals to 10 equals to xg2. xg0 equals to 1. So xg1 plus xg2 plus xg0 will be what? It will be 21, right? This will be my xg1 plus xg2 plus xg0, that is my 21. And what is 3xg0? So 3xg0, sorry, what is 3xg1? 3xg1 will be equals to 30. So I am observing 3xg1 will be larger than this sum. So this value will be larger than the denominator here. So if the denominator is larger, that means the overall fault current will be lower than this one. So that's why numerically also I have proven to you that the line LG fault is greater than the LG fault. Okay, LG fault. So I hope it is clear. For what? For generator. So numerically also it will be higher, so it is more dangerous for a generator. Okay, it is more dangerous for a generator. Okay, now few things we can find out. What is the fault current in per unit? Fault current in per unit will be equals to, so if I assume my EA to be base, right? EA to be base, then this will become, I will assume that my reactances are already given with respect to their base rating, that is EA. So they are already in per unit, and this will become what? EA will become, hence in per unit EA will become 1 angle 0. So basically the expression will become 1 divided by 1 j xg0. Sorry, not 1, sorry, this will be 3, right? There will be 3, obviously. It cannot be 1. So it will be 3 divided by j xg0 plus j xg1 plus j xg2 plus 3jxn plus 3z. Okay, so this is my fault current in per unit. Assumption is all these bottom also are in per unit, right? These are given per unit with respect to generator base, right? What will be short circuit MVA? So short circuit MVA is same as IFPU, right? Short circuit MVA is same as IFPU. Okay, that is what my short circuit MVA is equals to. Now, what will be the like short circuit MVA in like actual value? It will be IFPU into S base, right? That's how simple it is. So this you can directly equate with this value. Where did it goes? We derived, right, this one. 3EA1 IA star IA1 star to confirm, right, whether you have solved it correctly or not. So these are few relation that was like that we needed to discuss, right? I think most of the thing has been discussed here. Now, okay, one more thing we have discussed, like what if source is unbalanced. If source is unbalanced, right, sequence network will just change. So what will be the sequence network? Sequence network now will have negative sequence voltage and zero sequence voltage. So sequence network will have now negative sequence and zero sequence voltage. So instead of just being JXG2, there will be a voltage that will be equals to EA2, right? This we have already discussed. If the source is unbalanced, a extra additional voltage will be developed. This will be EA2, and this will become also like this will not be 0 anymore. This will be EG0. Okay, so what will change? Will your IF change? Tell me in the comments below. IF will change. Will IF change? No. IF actually will not change. Why it will not change? Because again the same thing, right? What is the fault current? So fault current will be where did it go? Fault current is this time instead of EA there will be three values because there are three voltage sources, right? If you see there are three voltage sources, right? So it will be 3 into EA1 plus EA0 plus EA2, right? And luckily this is what? This is simply EA only, right? So the previous fault current is same as this one. So fault current will not change, won't change. But your VA1, VA0, VA2 will change, definitely change, right? Because there is additional potential here. So these will definitely change. These will definitely change no matter what. Okay, that is one additional thing that I wanted to like discuss. Okay, so let's now finally solve this question, and this case will not be asked anywhere. Most of the cases this will not be asked, but one day if they ask, right, you will be able to solve it. So let's solve this question. A salient pole synchronous generator is rated at 20 MVA, 13.8 kilovolt, has the following sequence reactance per unit. The neutral is solidly grounded, right? So Xn is 0 or Zn is 0 and operating in unloaded condition. So pre-fault condition is 0. Calculate the subtransient fault current of the generator in per unit for a single line to ground fault. So what will be the subtransient current? For subtransient I have to choose the subtransient reactance, right? And as it is operating in no load, so the voltage EA will be 1 pu. right? EA will be 1 pu. So I can directly draw the reactance diagram. It's a single line to ground fault, so the reactance diagram will be this. I will have here jxg1, so that is jxd double dash, that is given to me as 0.25 pu. So I will write here j 0.25, and then I will have 1 angle 0, and then I will have the negative sequence reactance. Negative sequence reactance is 0.35, j 0.35, and then I will have the zero sequence reactance. Zero sequence reactance is j 0.1, right? So this will be j 0.1, and ultimately it is what they are telling me, it is a neutrally solidly grounded, and they have not mentioned whether the fault is solid or not. So I will assume ZF to be 0, nothing has been mentioned, so I will assume ZF to be 0, so it will be directly connected to ground, right? So what will be the fault current? So this is my sequence current, right? This is my sequence current, IA0. Fault current is what? Fault current is 3 times IA0. So IA0 is this, right? 1 upon whatever this value is, j 0.25 plus j 0.35 plus j 0.1. So your fault current will be what? It will be 3 IAO, right? I just have to find out the magnitude. They are asking me the subtransient fault current, so I can just find out like the magnitude. This will be 3 by whatever this value comes out. This is j 0.7. Okay, so 0.7, so minus j 4.28 pu. Okay, so the fault current is minus j 4.28 pu. What about the what about the other values? So what have they asked? They have asked the resulting line to line voltages during fault. So they are asking me the resulting line to line voltage. What does line to line voltage means? So line to line voltage basically means VAB, VBC and VCA. So let's find out like what is my VA equals to. So what will be VA equals to? VA will be equals to VA naught VA1 plus VB1, right? Sorry, not VB1, sorry, VA2. If I am able to find out the individual sequence component, right, I'll be able to find out the other voltages. So VA is 0 actually, because this is the point A and that is directly grounded. VA is 0. What is VA naught, VA1, VA2? So my VA1 will be this. What is happening? My VA2 will be this. My VA naught will be this. Okay. So what is my VA naught? VA naught, if you see, like the current is going like this, right? And this is my VA naught. Okay. So my VA naught will be something negative, right? VA naught will be something negative. So I will just calculate the value of VA naught. What will be the value of VA naught? So VA naught will come out to be this minus, because current is flowing like this, right? This is the 0 sequence current, minus IA naught into j 0.1, and I know what is my IA naught. IA naught is this value divided by 3, because 3 should not be there. This is my IA naught, right? So this will be minus IA naught will be 4.28 divided by 3, so it comes out to be 1.42, and it is minus of j into 1.4267 into j 0.1, right? So minus minus, this will be basically minus of 0.14267. So here the VA1 will come out to be minus of 0.14267. Okay, so now let's calculate the other phase voltages, like this VA2 and VA1. So what will be VA2? VA2, again there is some voltage drop here, right? This current is flowing. What is that current? That current is negative sequence current, right, which is same as zero sequence current, and this is the reactance drop. So it will be minus of IA2 into J 0.35. This will be equals to IA2 is the same as IA0, that is minus of J 1.4267 into J 0.35. Okay, so this divide by 0.1, say not 0.1, what am I doing? So 1.4267 into 0.35, that is it will be 0.5. So it will be minus of VO2 will be minus of 0.5 angle 0. Okay, or it is like negative, like it is real only, angle 0. Now VA1, this will be the most interesting one. What will be VA1? VA1 will be 1 angle 0 minus this drop, right? So it will be 1 minus this drop, that is IA1 into J of the positive sequence reactance, that is 0.25. Okay, so 1 minus IA1. IA1 is same as IA0, that is minus J 1.4267 into the reactance J 0.25. So 1.4267 into 0.25, this will be yeah, so negative sign is already there. This will also be minus minus plus minus. So 1 minus 0.356675. So this comes out to be 0.643325. Okay, so these are my basically like positive sequence and zero sequence and negative sequence voltages, right? So will I be able to find out VB and VC from this? Will I be able to find out VB and VC? What will be VB and VC? So VB will be equals to what? VB, we know VB is, I have already told you, it is VB0 plus VB1 plus VB2, which is equals to VA0 plus what will be VB1? VB1. VB1 is positive sequence, right? So it lags A by 120, that means minus 120, that means I have to multiply alpha square. So this will be 1 angle minus 120 times the VA1. What is VA1? This value 0.633, and VB2 will lead A by 120 because it is negative sequence. Because it is negative sequence, it will lead, hence this will become 1 plus 120 into the VA2, that is minus 0.5. Okay, so VA0 is basically minus 0.143. Okay, so we have to solve this. Will be a hectic task. Okay, so minus 0.143 plus, now 120 cos into 0.6433, so this is actually minus 0.321 or 322, and 120 sine into 0.6433, so this is minus j 0.557 plus, now what will be this? Have I, oh, this will be positive only, this is negative, right? So I can write here, this is like minus 180, so minus 180 plus 120 will become 300 or minus 60. I can write this as this has minus 180 as well, so this will be minus 60, so 0.5, this will be basically 0.5 angle minus 60, so 60 cos into half, that will be 0.25, and 60 sine into 0.5, it will be minus j 0.433. So from here I can easily find out what is my VB. Remember, we have to find out the line voltages, not the phase. So this will be even more difficult, right? You have to find out the line voltages. So this will be minus 0.433 minus 0.557. This will be almost minus of G, and 0.143 minus and minus 0.322 and plus 0.25, this will be minus of 215. Okay, so now I can directly convert this into like the phasor format. What will be the phasor format? So this will be 1 square plus 0.215 whole square whole under root, so it becomes 1.023. And what is the angle? Remember, both the imaginary and real are negative, so it is in the which quadrant? It is in the fourth quadrant, right? Fourth quadrant, so it's in the fourth quadrant. So what will be the angle in the fourth quadrant? Okay, so both are sorry, not in the fourth, sorry, third quadrant, right? Third quadrant. I am also मेरा भी हो रहा है भाई, खत्म हो गया मैं. Okay, third quadrant. So this will be 1 divided by 0.215 tan inverse. So this and this 0.215 tan inverse. So it's this angle. I have to add 180. So plus 180, it will be 257. Or if I subtract 360, it will be minus 102. Like I will not say, मैं नहीं बोलूँगा एंगल कैसे निकालते हैं, ठीक है? ये आपको फिगर आउट करना पड़ेगा, ये सब करवाया हुआ है बेसिक्स में, तो मैं नहीं बोलने वाला ये सब. So 102 point minus 1.4. Now similarly you have to calculate the VC. Okay, similarly we have to calculate VC. VC will be VB VC0 plus VC1 plus VC, or I can directly write here, it is VA0. It will be alpha into VA1 because it leads the VA1 plus alpha square into VA2, which will be, this will be minus 0.143 plus 1 angle 120 into VA1, that is 0.6433 plus 1 angle minus 120 into minus 15. Okay, so this will be equals to this will be equals to 1 angle 0.143. So I'll just calculate the values here. So 120 into 120 cos into 0.6433. So this will be minus 0.143 plus minus 0.32165 plus j so 120 is sine into 0.6433. So this will be j 0.557. Okay, plus now this is minus plus 125 2. This will be basically 0.5 plus 60, just the opposite. So cos 60 is half, so this will be 0.25 and plus j 0.8, so 60 sine into 0.5, so plus j 4.3. Basically this signs will be reversed. Here if we see, this became plus and this became plus. That's it. Everything else is same, right? I do not need to calculate because the angles just got swapped. That's why. Okay. So the values will be this time. This will be 0.433 plus 0.557. So this will be again plus j, right? Previously it was minus j. Now it became plus j. And the real part will be, remember this became negative here, so this is positive, negative, negative, both are negative here. So real part will be same, that is minus 0.215, minus 0.215. Just the imaginary part change its sign, right? So this will become plus 10, right? So magnitude will be same, that is 1.23, 1.023. What about the angle? So what will happen to the angle? So the angle will be, this will become, now which quadrant is this? So here the real part is negative, imaginary is positive. This is the second quadrant. Okay, so second quadrant is 180 minus theta. So theta will come out to be 1 divided by 0.215 tan inverse 180 minus of this, so it comes out to be 102.134 degrees. Okay, so this is your theta. Okay, this is your VC. Now what will be your VAB? Do I have to do again complex calculation? No, because I know that VAB will be equals to VA minus VB, and VA is already 0. VA is already 0. It is directly shorted, right? VA is 0. So things become simpler, right? So VAB will be minus of VB. So what is VB? VB is this value. Minus of VB means adding or subtracting 180 with this angle. So I will add 180 with this angle, right? What will I get? It will be 77.87. So it will be 1.023 77.87 degrees. That is my VAB. What about my BC and VAB, VBC and VCA, right? Okay. One more thing, if they ask you actual values, if they want to ask you actual values, how will I? So let's because here, right, they have not mentioned in per unit, so maybe they are asking in actual. So if they are asking in actual, you will not do this subtraction, right? This I have taught in per unit. You will not do this subtraction. So first convert these into actual values. So if I want to convert this into actual, so 1.023 into 13.8, that's the line voltage, right? But this is the phase voltage, right? This is the phase voltage. So I have to multiply by the phase voltage, not by the line voltage, correct? Because this is provided as the line voltage, but this value whatever we have calculated, this is the phase voltage. So I have to multiply by the phase voltage base, not the line voltage base, correct? So this divided by √3. Just give me 1 second. 1.023 divided by root 3 into 13.8, yeah, 8.15. So the actual value here comes out to be 8.15 angle 102.134. Like what I have done, I have just simply, because the V base is given to me as 13.8, right? This is the V base, but this is the line voltage. What will be the base for the phase voltage? Base for the phase voltage will be VB line upon root 3. Previously, pre-fault condition, it was balanced, so that's why this will be applicable, right? So that's why I was able to divide this by root 3, and this will be the, if I multiply by the base value, I will get my actual value of VC in kilovolts. What will be the actual value of VB in kilovolts? It will be same 8.15 angle minus 102.14 in kilovolts. Okay, so this will be the kilovolts. So what will be the line voltage? So line voltage will be this value, and actual value of the line voltage will be 8.15 kilovolts, right? What will be VCA? VCA will be VC minus VA. So VC is, VA is 0, so it will be plus VC only. So plus VC is this value, right? This is plus VC, so it will be 8.15 angle 102.134 degrees kilovolts. Now what is your VBC? So for VBC, you have to do a bit of calculation, which is VB minus VC, right? So remember, whatever you have done, right, do that in fair. If you don't do that in fair, maybe you will not be able to use it. So I will use it now. So my VC in rectangular is this value, my VB in rectangular is this value, right? So basically what is happening, I'm subtracting VB from VC, sorry, I'm subtracting VC from VB, right? So this imaginary component will stay, the real component will get cancelled, because this is common, right? This will get cancelled, so only minus 2j will be there, right? Minus 2j, so minus 2j will be there, okay, minus 2j will be there, and of course I have to multiply by the base. Don't forget, each term I am multiplying by the base, that is 13.8 divided by root 3, right? What am I doing? I will just explain. So this, right, this is my VB, so this is my VC, so I'll first put my VB in per unit. So VB in per unit is this value, right? VB in per unit is this value. Then I will multiply, convert it to actual, so actual will be the base of phase, that is 13.8 divided by root 3. Then I will subtract VC, so VC is this value, VC is this value. Again I will multiply by 13.8 divided by root 3. Then finally what I will do is I will take this common 13.8 divided by root 3, and simply what will happen, this 0.21 will get cancelled, only minus 2j will be there. So that's why minus 2 into 13.8, 2 into 13.8 divided by root 3, which is 15.93. angle minus 90, right? Because it was minus j, so it becomes 15.93 angle minus 90. So these are my answers for this question. This was actually a very good question, and I'm expecting one day they will ask a question something like this. Okay, so let's now discuss the other two type of faults, that is LL fault and LG fault, double line fault and double line to ground fault. So this is also called as double line fault. Okay, so we will consider actually this case, we will not consider this one. This one will be like very hectic, right? This one will be the easier case to consider, right? Only one fault impedance is there. Although it does not matter. Like if there is 2 ZF, right? What will happen? If there are 2 fault impedances, it will become 2 ZF. That's it. No, this will not be complex. This will be easy. If there are two fault impedances between the lines, this will become 2ZF instead of ZF, but I am assuming overall fault impedance between the lines is ZF only. Okay, so let me, otherwise I know you guys will cry, sir क्या कर दिया, समझ में नहीं आता, क्या कर दिया. Let's make it single ZF. ठीक है, अब तो खुश हो, अब तो खुश हो, ये this is single ZF, right? So this is also single ZF, right? So overall impedance between the two lines becomes, suddenly they are shorted through ZF. The special case is they are directly shorted where ZF is 0. Okay, so let's do the analysis, same analysis, right? We'll do pre-fault condition. Pre-fault condition. So pre-fault condition, I know that my IA, IB, IC is 0. My VA will be equals to EA, VB will be equals to EB, VC will be equals to EC, because all the currents are 0. These are my XG, XG, XG. But post fault, what will happen? Post fault, what will happen? So post fault, what will be the IA current? IA current will still be 0. What will be IB current? So I see IB current is incoming here, right? IB current is incoming here and IC current is incoming, right? It's the same branch. So what can I comment? Simply IB is minus of IC, because if I put minus of IC, then IC will be on the left hand side and IB is incoming here, right? So IB will be equals to minus of IC. And what is my VB and VC? Can I directly comment what is my VB and VC? I can comment this much, that VB minus VC will be equals to IB into ZF. This much I can comment. And what is IB? IB actually is the fault current basically. IB is basically the fault current, right? Fault due to which, like this is the wire, right, through which the fault has occurred, right? So IB is the fault current. Now, will there be any zero sequence component of current here? The answer is no. There will not be. There will not be any zero sequence component of current. There will not be any zero sequence component of current. Why? Because ZF does not have a path to ground. This I will prove as well. I will prove this as well, that there will not be any zero sequence component of current. Right? Again, I will use the same same thing. I will explain what do I mean by it. So one more thing is there, that VA will not be equals to EA anymore, because there will be some unbalancing here. This will change. We'll see what will change. So again, I will use the same equation, right? This symmetrical component equation to get my result. This equation, right? This time the values will change. What will happen? This time IA is this value only, right? But I know this IA current is 0 because it is open. It is open circuit, pre-fault, post-fault same. So IA current is 0. So this will be 0. But this will become plus IB, right? IB current will be IB only, and this will be minus IB. Okay, so that is what will change this time, right? So we are just using our symmetrical components to calculate. Okay, so yeah, I hope you remember like why we will not be able to, like, why will there not be any zero sequence current? These are, I hope these all things are, I hope, clear, right? So now let's basically solve this like basic equation. If I want to solve this, it will be minus IV, right? So what will be the current equation and the voltage equation? That is what I want to find out. What will be the current and voltage equation? So what about the current? Let's first see the current component. So IA0 will be equals to 0, as you can see, right? It is 1 into 0, 1 into IB minus IB. So IB minus IB is 0. So automatically IA0 will be 0 only, no problem. Now what about IA1? So IA1 is 0 alpha into IB, and this is minus alpha square into IB, and your IA2 will be what? Alpha square into IB minus alpha into IB. So what do I understand here? The thing that I understand over here, that the positive sequence current is just negative of the negative sequence current. The positive sequence current is just negative of the negative sequence current. That is the first thing that I observe. Okay, that is the first thing that I observe. So if I draw the positive sequence diagram network, so I will have a J, XG1, then I will have E A1, and that's it, right? That's it. There is no zero sequence component, and I know positive sequence network will be this. It is JXG2, and there is no zero sequence current. So if I even if I draw the zero sequence network, right, it will be simply open circuited. There will be JXG0 and there will be 3XN. Okay, but it will be open circuited. IO0 will be simply 0. But one thing I know, if some current is leaving here, that is IA1, right? IA1 is a positive sequence current, and through this, how the current leaves like this, right? IA2, correct? If you remember the positive sequence current, if I draw this even better, right? Actually, not like this. The sequence current was like this, right? If you remember, the sequence current used to leave IA2, correct? And this is I1. So I know IA2 and IA1 will be negative of each other. So if I, like, I'm just doing an innovation here, okay, not innovation, like thinking, thought process, that if I connect these 2 points, what will happen? Then this will satisfy. So IA1 will be equals to minus IA2. Now, can I connect these 2 points directly, or is there any problem for connecting these 2 points? So for that, I have to find out the relation for the sequence voltages. So this is my VA1 and this is my VA2, correct? VA1 and VA2. So what is my VA0? So VA0 is 0. VA0 is 0, correct? This much I know. VA0 is 0. So okay, this is already there. Why is this there? It's not required. So VA0 is 0. If VA0 is 0, this much I know, VA0 is 0, right? What else information will I be able to find out? So I know that my VA0 is equals to what? VA0 is 1 by 3 VA plus VB plus VC, right? Which is 0. So VA plus VB plus VC is 0. Okay, this is one information that I know. One more thing I know, that the potential difference, right, VB minus VC is IB into ZF. This will be helpful for us. So VB minus VC is equals to IB into ZF. This is one equation. What about the other equation? So what is my VA1? So VA1 is equals to 1 by 3 VA. Okay, this again I have to write down that formula, right? Okay, I deleted that formula, but that is actually useful. So if I write down the formula for voltage in terms of the phase voltages, right? So my VA naught, already we know what is VA naught. VA1, what will be V1? So VA1 will be 1 by 3 VA plus alpha into VB plus alpha square into BC. Okay, so VA1 is this value, so I can say will this be helpful to me? Will I be able to use it? VA is this value. Can I change this? That is what I'm thinking. Okay. I will use it. Okay. So VA1 is this. VA2 is what? VA2 is 1 by 3 VA plus alpha square VB plus alpha square VC. So if I subtract these two, VA1 minus VB2, VA1 minus VA1 minus VA2, 1 by 3 will be common, VA will get cancelled, so it will be VB, or if I do this, right, if I take common here, so if I take common alpha square, right, if I take common alpha square, this will be VC minus VB. If I take common here alpha, this will be VB minus VC. So what I can do, instead of taking common alpha square, I can take common minus alpha square. So this will be VB minus VC. So I can again take this out. This will be VB minus VC into alpha minus alpha square. Okay, VB minus VC into alpha square, right? So what is VB minus VC? Now remember, I cannot say what is absolute potential here, but VB minus VC will be what I know, that is equals to IB into ZF. VB minus VC is IB into ZF, right? That is what my VB minus VC is equals to, correct? Yes. And what is alpha minus alpha square? What is alpha minus alpha square? Do I remember it? Do I remember the formula alpha minus alpha square? I kind of don't. So VB minus VC I already know, it is IB into ZF, but what is alpha minus alpha square? And what is my IB? So IB, right? Okay. This will be helpful. So IA1, what is my IA1? IA1 is IB into alpha minus alpha square. This will be helpful. Okay. So I'll replace here this will be 1 by 3 VB minus VB is IB into ZF into alpha minus alpha square. Now what is IB into alpha minus alpha square? That is equals to my sequence current IA1. Sequence current IA1 is IB into alpha minus alpha square. So I will replace it over here. This will become 1 by 3 also will be there, right? Sorry, 1 by 3, okay, 1 by 3 should be there, right? Yeah, sorry, sorry, 1 by 3 also should be there. 1 by 3 also should be there. What am I doing? So 1 by 3 obviously will be there, right? I missed this point. Okay, so what is 1 by 3 into IB into alpha minus alpha square, right? So it is basically IA1. So I can directly replace this whole thing 1 by 3 into IB into alpha minus alpha square as IA1. So basically the voltage difference between the positive sequence voltage and the negative sequence voltage will be IA1 into ZF. What does it mean? The potential here, the potential difference between these 2 points will be IA1, whatever current is flowing, into ZF. So basically I can model this as a impedance that is present between the two sequence networks. Okay, so now I hope everything is sorted, right? So IA1 will be equals to minus IA2 as from the circuit, and this potential difference between the two sequence networks is IA1 into ZF, right? So I have to connect the neutrals as well. Neutrals will be connected, right? Neutrals will always be connected, but remember the top side is disconnected, so there is no zero sequence network here. There is only positive sequence and negative sequence. Now remember, what is my fault current? Fault current is IB. Fault current is not IA1. Okay, fault current is not IA1. Fault current is IB, right? So I will be able to find out IA1. What will be IA1? So IA1 will be equals to this EA. I can bring this circuit here. EA1 divided by, which is EA only because it consists of like balance supply, which will be EA, like it is a balance supply, right? EA divided by J xg1 plus J xg2. Now is this the fault current? No, this is not the fault current. Okay, this is not the fault current, right? This is just the positive sequence current, right? So what is the okay, sorry, ZF is also there, right? Plus ZF. What is the fault current? So fault current is IB, and I know I have derived here my IB is what? IB is equals to IB is equals to 3 IA1 divided by alpha minus alpha square. Now what is alpha minus alpha square? So again you can draw the phasor, right? So alpha will be somewhere here. Alpha square basically means it is somewhere here, right? And minus of alpha square will be like, so basically, sorry, alpha will not be somewhere here. Alpha will be somewhere here. Positive 120 from here, right? This is what my alpha is. Alpha square will be somewhere here. There is negative 120, and reverse of that it will be somewhere here. This will be minus alpha square. This will be alpha square, right? I am doing fast. I will not explain. All this has been explained in the symmetrical components. So this angle, right? This angle is 120. This whole angle is 180. So this angle will be 60. This will be 60. And this angle is 120. So this angle will be what? 60, because this much is 60. So this has to be 60. So I have two vectors whose magnitudes are 1 and whose phase difference is 60, that means its resultant will be root 3 times the magnitude, that is 1. What will be the angle? It will be the bisector. So this much is 60, bisector is 30, so overall it will be 90. So what I can say is this value will be, so I can take this here. This value is root 3 into j root 3, right? So basically it will be minus of j, root 3 will be there, so root 3 ia1, that's it. It will be minus of j into root 3 into ia1. So your if will be minus of j root 3 into ia1, right? So this will be equals to minus of j root 3 into EA divided by j xg1 plus j xg2 plus zf, right? So this formula you have to actually remember, right? Because every time you will not derive, so you will remember the circuit diagram, you will remember the formula, fault current formula, okay, and you remember that the sequence networks are connected in parallel, okay. So I hope it is clear. Now what will be the like MVA? So in per unit, what will be the value per unit? So in per unit IFPU, it will be basically, if I want to just talk about the magnitude, it will be root 3, this will become 1, EA will become 1 divided by magnitude of JXG1. I am not writing, like I don't know what is ZF, so JXG2 plus ZF, right? Magnitude whatever is the bottom. So what will be the short circuit MVA? Short circuit MVA will be this value only, same. Short circuit MVA will be same only. And what will be the short circuit MVA in actual? So SCMVA actual. This will be into S base, right? That's it, okay. Or you can directly find out using this formula will always be valid, EA into IA1 star. You can find it out using this value as well, because the other sequence components will be 0, right? Both of them will work, both of them should give you the same value, okay. So this question, same question I wanted to try, and this one I will leave you as a homework. In the next lecture we will solve this, because otherwise this lecture will go long, right? So these are the few things that you must keep in mind, okay. And remember one more thing, one more key point, VB, VC and VA, the node voltages are undefined with respect to ground. You cannot comment what is the exact node voltage VA, right? Why? Because circuit does not have neutral connected to ground. So actually the circuit technically is wrong, right? Whatever I have drawn. So here, right, this also will be open circuited. This will not be connected. So this point is ground actually. Zero sequence component, this point is ground. So it is not connected, right? So there is no reference here. There is no ground connected in the circuit. So there is no ground connected in the circuit. So the node voltages, right? These node voltages, like voltage at a point, potential at a point, are undefined. Potential difference, of course, you can comment. You can comment about potential difference. So these are node voltages. What is node voltages? Node voltages are potential at a point, okay, potential at a point, but potential difference is defined, right? Potential difference is definitely defined. Okay, so potential difference is defined. Okay, potential difference is definitely defined. Okay, so these are the few important points. So what are the important points? This you have to remember, this like formula, this circuit diagram you have to remember. One more thing you have to remember, that your phase sequence current will be negative. This you have to remember, right? And if it is possible, you are able to remember this formula as well, that will be helpful, right? 1 by 3 into IB into alpha minus alpha square. This also if you are able to remember, that is good. Okay, I hope these things are clear to you. Okay, so now let's solve the like the last and final one, that is a uh, double line to ground fault. What will be the value of the double line to ground fault, right? So yeah, let's solve that double line to ground fault. Basically, we'll solve the double line to ground fault, right? So in double line to ground fault, if I have like two lines that are shorted and we're connecting it to through a ZF to ground, so now zero sequence current will be present because the fault impedance is connected to ground. So fault current has a path to ground. So the important point is, as fault current has a path to ground, that means zero sequence component will exist. Okay, that means zero sequence component will exist. Okay, I hope it is clear. So pre-fault condition, again we'll do the same analysis. Pre-fault condition. So pre-fault condition, my IA equals to IB equals to IC equals to 0, my VA equals to EA, my VB equals to EB, my VC will be equals to EC. Everything is balanced, sorted, right? But आपने कुछ कर दिया गड़बड़, ठीक है, आपने फॉल्ट कर दिया, तो इफ यू हैव डन फॉल्ट, देन व्हाट विल हैपन? पोस्ट फॉल्ट कंडीशन, पोस्ट फॉल्ट, if I've done the fault, right, double line to ground fault, I am observing, so here some IB current will come, here some IC current will come, okay, and then both of them are getting added to receive IF to ground. Okay, IA current is still 0, so IA current is still 0 because it is open, no load, IA is 0, IB plus IC is equals to IF. Okay, and now I know the potential at this node. Now I know the potential at this node, that is VB will be equals to VC, which will be equals to IF into ZF. Now the potential at this node is defined because ground is connected. Okay, because ground is connected, correct? Okay, so now let's solve this. So again, if I see the current, right, current is IBIC, current is IBIC. So if I replace this equation, IA current will be 0, okay, so this will be 0, this will be IB, this will be IC, right? So so what will be my IA0? IA0 will be 1 by 3 IB plus IC, and what is IB plus IC? That is fault current. So from here I can directly say that my IF will be 3 IA0. So this will always be the case. Whenever there is zero sequence component, the fault current will be thrice the zero sequence current, right? This is very important point. This will help you in LG fault as well if you tend to forget the thing, right? Okay. This is my fault current. Fault current expression I have found out. Anything else I can do? Now let's solve for voltage. Let's solve if I want to solve for voltage. Okay, how will I solve for voltage? That is what I want to know. So let me copy this for voltage. I will come back to fault. We can write down the fault current expressions. So what will be my IA1? IA1 will be equals to 1 by 3, it is 0, alpha into IB plus alpha square into IC, and my I2 is equals to 1 by 3 alpha square into IB plus alpha into IC. Okay. Now these are not same. So this is my IA1 and IA2. Okay, fine. This is my IA1 and IA2. Okay. I cannot further derive it. So let me. Sorry about that. I'm really sleepy. Okay, let me write the voltage values. VA0, VA1, VA2, VA, VB. We know VA and VC and VC are same. That is VB, VB only, right? So from here, can I do something? So what will be my VA0? So VA0 will be equals to 1 by 3 VA plus 2 VB. Okay. Okay. VA1 is equals to. So can I further simplify this? So what is VB actually? VB is IF into ZF, right? VB is IF into ZF. So this can be further simplified. 1 by 3 VA plus IF into ZF. What is IF? IF is 3 IA0. So this will be plus 3 I0. Three I0. Okay. 3 I0. So yeah. What else can I do? और क्या कर सकते हैं? Okay. So let us now. This is my VA0. What about my VA1? VA1 will be equals to 1 by 3 into VA plus alpha into VB. Alpha into VB, basically alpha into VB plus alpha square into VB, right? Plus alpha square into VB. So what is alpha plus alpha square? Alpha plus alpha square. So alpha will be here, alpha square will be here, this will be here, right? Alpha square. So resultant will be here. So it is basically J. This will be 1 by 3 . VA plus alpha minus so this will be basically minus of root 3, minus of root 3. I'm directly calculating it, minus of root 3. Okay, what will be VA2? VA2 will be 1 by 3 VA plus, now this will become alpha square plus alpha, which is same, right? This is same only, alpha square plus alpha minus of root 3 into VB. So what do you notice? You notice a important phenomena, that your positive sequence voltage and your negative sequence voltage are same. So if they are same, they must be connected in parallel. So your positive sequence network and negative sequence network are connected in parallel. So here is my positive sequence voltage xg1 EA, then I have my negative sequence network what am I doing? Okay, this is my negative sequence network JXG2. Now I have my zero sequence network. So what is a zero sequence network? So zero sequence network, if I draw, it will be JXG0 plus obviously the your neutral is grounded, so J3 xn will be there, and yeah, that's it. This will be there, right? Now one more thing, this is the ground. Okay, how will I connect this one and my, so this is my positive sequence voltage VA1, this is my negative sequence voltage VA2. Okay, VA1 VA2. Okay, so VA1 VA2. No. How will I connect the zero sequence? How will I connect the zero sequence? So VA naught is this value, right? VA naught is this value, actually 2 times VB. Okay, will I be able to find out VB from here? Both of them are same, right? VA naught, VA1 this. No, I will not be able to find out VB from here. Okay, what do you know that what is the current that is flowing here? I naught, right? Current that will flow through here will be I naught, correct? And I can observe that this 3 I naught into ZF drop is there along with VA. Along with VA, this 3 I naught into ZF drop is there, right? So what is actually my VA? Yeah, I was just thinking, I just made a blunder again. So this alpha square plus alpha, right? It's not, I'm sorry, but I should have used the property. So alpha square plus alpha, the angle difference is not 60, it is 120, right? It is 120. So if I have two vectors that are equal in magnitude, but the angle difference is 120, the resultant will be a magnitude, same magnitude 1, and in the angle bisector. So this will be actually minus 1. I'm sorry, this will be not root 3, minus 1. You can verify this with this property, 1 plus alpha square, right, is equals to 1, is equals to 0, cube root of unity. So alpha plus alpha square will be minus 1. So that, my bad, this will be actually minus 1. Okay, that's why these things were becoming difficult. But still VA1 will be V equals to VA2. But now I can actually find out a easy way out. That is, if I subtract VA0 with VA1 or any value. So if I subtract VA0 minus VA1, what will I get? So VA will get cancelled, right? So this will be 2VB, this will be minus of minus 1, so this will be plus VB. So 1 by 3, VA will get cancelled, this will be 3VB. So actually this becomes VB. And what is VB equals to? VB is equals to IF into ZF. VB is equals to IF into ZF. And what is IF is equals to? IF is equals to 3 IA naught is equals to IF into ZF, which is equals to 3 IA naught into ZF, right? So what is my VA naught in terms of VA1? So VA naught in terms of VA1 will be VA1 plus 3 IA naught into ZF. So basically there will be ZF in between, 3 ZF, not only ZF, there will be 3 ZF. Through which this I naught current will flow, and from the potential VA naught, right? VA naught is same as VA1 is same as VA2. There will be an additional drop. There will be an additional drop from VA1, right? So if I apply KVL now, it will satisfy. You will see, apply the KVL, it will satisfy. Apply the KVL, it will satisfy here. So I will connect the reference as zero sequence network is connected. So I will connect the reference to ground because there is a path for ground to flow. Okay, so this circuit you have to remember, right, for double line to ground. Now still we have not found out the expression for I naught, right? I have still not found out the expression for I naught, which of course we will calculate. What will be the expression for I naught? Because the voltage is here, right? Okay, this will be hectic. This will be hectic. So like what you have to do, you have to apply Thevenin's. Otherwise calculation will be a bit difficult. So you can convert this circuit into Thevenin equivalent, right? Or you can apply the, like, first of all you can apply the current division rule. Still this will be difficult. So either you have to apply CDR or something to find out the IA naught current, right? So what you will do is you can convert this whole circuit into Thevenin equivalent. So here there will be some VTH, that is the best way. There will be some VTH, there will be some XTH, right? And then finally this zero sequence network will be connected, right? The zero sequence network will be connected, and from here you will be able to find out I naught. So I naught will be equals to VTH upon JXTH plus whatever is the equivalent resistance here, X, like Z equivalent, right? So this whole network I am replacing with Z equivalent. Okay, so these things you can do, these calculations you can do, right, solving networks. Now remember, this is just the I naught. What is the open circuit voltage here? Open circuit voltage here, it will actually not be, just because there will be some drop here as well, right? So VTH will change, it will not be EA. Open circuit voltage will not be ETH, so it will change. So this will be my Z equivalent, this will be my fault current, right? This will be my zero sequence current. What is fault current? So IF is equals to 3 IA naught, right? So this will be 3 VTH upon JXTH plus Z equivalent. So solving networks, I am leaving it up to you. So this you can connect. So what is happening? So the crux is that all sequence networks, if ZF is 0, right, then all sequence networks will be in parallel. Okay, all sequence networks will be parallel if ZF is 0. Then there is no drop. So basically VA naught will be same as VA2, will be same as VA1. Okay, if you consider ZF to be 0. Okay, I hope these things are clear. You can find out the current voltage, all those things you can find out. Okay, I hope it is clear. Okay, so I will leave you with another homework. This will be the last homework, same question only. Or yeah, they are asking you to identify the type of fault that has occurred. Okay, so you solve this question. These are few homeworks. So before ending, actually I just remember I made a small error. Okay, here is the error I will tell you. that this, right, undefined with respect to ground. Actually I made a small error here. If I draw the sequence network, actually they will be connected. This will be connected here. This will reference bus neutrals will always be connected. But if my zero sequence network is not, basically if my neutral is not grounded, if my neutral is not grounded, where did it go? If my neutral is not grounded, then xn is infinity. If xn is infinity, then my zero sequence network will be ungrounded. So let me here bring the circuit. So there can be two cases, right? If I bring this circuit here, there can be two cases. There can be two cases. So one case will be where neutral is grounded. So this is the case, let's assume this case where neutral is grounded. So if neutral is grounded, that means this potential node potentials are defined. This VA, VA1, VA2 all are defined. So VA, VB also will be defined. Okay. If your neutral is grounded. So let me take the case. Let me first cut this and take another page here. So if neutral is grounded, right, then VA, VB. So if neutral is grounded, then your then your zero sequence network neutral will be connected to ground as it is shown over here. Okay, then all the potentials will be defined. VA, VB, VC, all node potentials will be defined with, I can define it with respect to ground. So then all node potentials will be defined with respect to ground. But if neutral is not grounded, so this is the case where neutral is not grounded. If neutral is not grounded, then your neutral is not connected to ground, right? So then what will happen to the circuit? So circuit, I don't have space here. This will be not connected, so this will be open circuit. So here xn will not be grounded, so this will be open circuit. Okay, so if this is open circuit, right, basically here is my ground, but ground is actually open circuit, right? There is no connection between the neutral and the ground for the zero sequence network. Hence I cannot define the I cannot define the the node voltages cannot be defined. I hope now it is clear why the node voltages will not be defined, but it is, if it is grounded, then it will be defined. Okay, that was a small error from my end. So you do the homework questions, and in the next lecture we will do all these questions along with more assignment questions. So I hope you have enjoyed this lecture, and if you did, make sure you hit the like button. Like, trust me, this kind of concept with clarity you will find nowhere else. So I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 12 where we will discuss the solutions of all the assignment questions. Right, that is what we will discuss today. So basically few questions I gave you homework and few questions we will do today, new questions, right? So these were the two questions, right? This was one of the question. Yeah, one when line to line fault will occur. Before that, that question we solved, right? This question I guess we solved. Yeah, this question already we solved. So this was the first question that I gave you as homework. So same question, right? Everything is same here. Everything is same. Just instead of single line to ground, now we have a line to line fault, right? Occurs at its terminals. So now what will be the diagram? If line to line fault happens, what will happen? So now this I have to draw the sequence diagram first. So I will copy like these things I will copy, right? Sequence networks I will copy. Of course, if it's a line to line fault, have they mentioned the fault impedance? No, they have not mentioned the fault impedance. So I will assume the fault impedance to be 0. Here have they mentioned the fault impedance? No, nothing has been mentioned. So I will assume the fault impedance to be 0. So fault impedance will be 0, right? Generator's neutral is solidly grounded. So this will be grounded, but this will be here. My VA2 will be here, right? And sequence networks will be in parallel, right? For line and for line to ground also sequence networks are almost in parallel, except there was a fault impedance in between, right? Which was ZF in case of line to line, which was 3ZF in case of line to ground. Why 3ZF? This was here, right? 3ZF was here actually, if you remember, in the zero sequence network. That's why it became 3ZF. So in line to line, we know that this will be parallel to each other. Okay, they will be parallel to each other, and I know my this is not IA0, right? This is IA1. IA1 will be equals to minus of IA2. That was the line to line ground. And if you remember, what was the fault current? The fault current IF was root 3 times IA1, right? J minus J root 3 times IA1, right? But mostly we are interested in the magnitude, but the fault current was minus J into root 3 times IA1. Okay. Now, so what will be my what have they asked? They have asked the subtransient fault current in per unit. So subtransient fault current will be, what is IA1? IA1 will be equals to 1 upon J 0.25. This will be connected here. This point will be connected. J 0.25 plus J 0.35. Okay. This will be 1 divided by J 0.6, right? 0.6. This is my IA1, right? What will be my IF? So IF will be minus of J. So minus of J, this will be simply J square. So minus root 3 into 1 divided by 0.6, which is actually 3 by 5, right? So this will be actually minus 5 divided by root 3, right? So the current in per unit will be equals to, the current in per unit I will calculate. This will be 5 divided by root 3. So root 3 into 5. So it comes out to be 2.886. Okay, this is the per unit current. I'm doing everything correctly, right? 0.35, 0.6, yes. 1 angle 0, yes. Root 3 times this, yes. So this comes out to be, your fault current comes out to be minus 5 by root 3. I will just quickly check what result we derived, right? Yeah, this was the result. It was root 3 times the IA1, right? the result was minus j root 3 times the IA1. Yes, this is correct. So yeah, so the fault current in per unit is minus 2.88. Magnitude will be 2.88. Okay, magnitude of the fault current will be 2.88 per unit. Okay. Now let us find out the next portion, that is they are asking me about the corresponding line to line voltages. So I know it's a line to line fault. If it's a line to line fault, right? If it's a line to line fault, then the fault is something like this, but I have node ZF. So this will be directly shorted. Okay. So VBC will be 0. Right? VBC will be 0, it does not matter. VBC will be 0 because it is directly shorted, right? So VBC is 0. What about VAB and VCA, right? What will be these values? So for that I need to find out VA. What will be VA? VA will be VA1 plus VA2 plus VA0. Okay. So here the current is 0. I know IA0 current is 0 because there is no 0 sequence current. So VA0 will be simply 0 because neutral is grounded. Neutral is solidly grounded. So VA0 will be 0. Right? There is no current, no drop, and neutral is grounded. So VA0 is 0. So VA0 is 0 because it is solidly grounded. Okay. Neutral, grounded. What about VA1 and VA2? So VA1 and VA2 are both same because they are directly connected in parallel. So it will be basically equals to 2 times VA1, right? 2 times VA1, or it will be equals to 2 times VA2, whichever one is suitable, because VA2 will be easier. It will be IA1 into J35, right? So VA2 will be equals to 2 times IA1 into J 0.35. Okay, 2 IA1 J 0.35. What is IA1? IA1 is this value, right? 1 by J 0.6. So this is 2 into 1 by J 0.6 into J 0.35. So 0.6 into 0.35 into 2, it comes out to be 1.167. Okay, so 1.167 is the VA potential, right? VA angle 0. Okay, this is the voltage of VA. Okay, do I know the potential of VB? I can find out the potential of VB. So VB will be what? VB will be equals to V B0 plus V B1 plus V B2, which is equals to V B0 is simply 0, right? V B1 will be alpha square into V A1 plus alpha square into V alpha into VA2, and I know VA1 and VA2 are same, so it is VA2 into alpha square plus alpha. And in the previous lecture, I remember and you remember, we made a mess of it. Alpha square plus alpha is actually equals to minus 1, because 1 plus alpha square plus alpha is equals to 0, cube root of unity. So this will be minus of VA2, right? And VA2 is this value, IA1 into J35. So it is basically equals to minus of IA1 into J 0.35 which is equals to minus of 1 by j 0.6 into j 0.35. Okay, so this will be equals to 0.35 divided by 0.6, so 0 point minus of 0.5833 angle 0. So basically it is minus 180. So it is minus 5.833, right? So what is my VAB? VAB will be equals to VA minus of VB. So VA is 1.167, VB is minus of this, so it will be actually plus. So 1.167 minus of minus 0.5833. But before this, right, what I will do, I'll first of all convert this into actual values, right? So if I want to convert this into actual values, what do I have to do? So I have to multiply this by 13.8 divided by root 3, and this also I have to multiply 13.8. Is this correct? Yes, it is correct, because this is only a positive sequence component, other components are inverse component. Yes, it is correct. 13.8 divided by root 3, right? So this will be equals to basically plus 1.167 into 13.8 divided by root 3, 13.94. Okay, angle 0. So the actual value of the voltage, line to line voltage, will be 13.94 angle 0, and this will be same as VCA. VCA will be like this is equals to my VC. This will be same as VC, right? Can I confirm this? Yes, VC will be equals to VC0 plus VC1. What is VC1? VC1 will be alpha into VA1. Alpha into VA1 plus VC2. VC2 is alpha square into VA2. Alpha square into VA2. Okay, so this, right, VA1 and VA2 are common. Again, it becomes alpha square plus alpha. This is 0, right? So what do I get? I see they are same only. So this becomes minus of VA2. Same result whatever I had written over here, right? So that's why. So what will be? So VBC is 0. VBC is 0. That is already certain, right? Because VB is equals to VC. So VBC already we have told you that this is one of the answer. This is the other answer. Okay, now what will be VCA? So VCA will be VC minus VA. VC is same as VB, so it is VB minus VA, so it is minus of VAB. So whatever we have derived here, it is just the negative. This will be minus of 13 point, so this is in kilovolt, minus of 13.94 angle 0, or 180 also you can do, whatever you want to do. Minus 13.8 kilovolt, you can also say this is the VCA, which is just the opposite. Okay, so this was the answer. This was the answer for this question. This was not that difficult as a single line to ground, right? Single line to ground, lot of calculation. So there was lot of unbalancing there. That's why that is the most dangerous current. That is why that is the most dangerous type of fault for generators. Okay, now let's solve this one. So here a fault occurs at the terminals of an unloaded synchronous generator operating at rated voltage. Following symmetrical components after fault we get. These are all the symmetrical components after fault. So I naught is there. So zero sequence current is there. So if zero sequence current is there, it can either be single line to ground or double line to ground. It cannot be line to line because zero sequence current is there. Okay. Now IA1, IA2 is there. VA0, VA1, VA2 all are same when all of the sequence networks are in parallel. So all sequence networks are in parallel. In case of single line to ground, in case of in case of single line to ground we know all sequence networks are in series, right? For double line to ground, all sequence networks are in parallel if the fault impedance is 0. That I have written in the previous lecture, right, as a short note. Will be in parallel if ZF is equals to 0. So here they have not mentioned anything about ZF. So this has to be a double line to ground fault. Also called as LLG fault. Okay. So these were the homework questions. So now we will solve today's question. This is the first one. I will show you the questions basically. This one, pretty interesting questions. We have this one. So this is 64, right? Yeah. Then we have this question. This is a gate PYQ. This one, ESC PYQ. Then this one, and yeah, this one. This is also gate. I don't remember exactly which year. This is also gate PYQ, and this one. This is the last one, I guess. No, not the last one. Okay, we have a lot of questions today. Okay, lot of questions. Oh my god, it's not ending, bro. It's not ending. So these many questions are there. Try to solve it. Now I will solve one by one each of them. So let's first solve this one. So here 3-phase alternator is given. These are the ratings. Positive sequence, negative sequence, reactance are given. The neutral is solidly grounded. So neutral is grounded. Okay. The alternator is unloaded, operating at rated condition. When a double line to fault occurs, determine the line currents in kiloampere under fault condition. What will be the line current in kiloampere under fault condition? That is what they are asking me, right? Line currents. Determine the line currents. Okay. So it's a neutral is, if neutral is there, it has to be star. Okay. So what are the line currents basically? So if a double line to ground fault has occurred, I know if a double line to ground fault has occurred, I know here the current IA will be 0. Okay. Here double line to ground fault has occurred. So this will totally go here. IF, right? And this will be my IC. This will be my IB. So if I am able to find out the sequence components, I will be able to find out my IB and IC. They are asking me the line currents. So IA is 0. That much is sure. IA will be 0. IA will be 0. Right? What are the other line currents? That is IB and IC. So before that, let me draw the equivalent fault reactance diagram. So I know here ZF is 0. So all the sequence networks will be in parallel, right? It's a double line to ground. So all the sequence networks will be in parallel. So here I will have the EA voltage, right? Then, so I can assume EA to be 1 angle 0 because it is operating in rated condition. Okay. So I can assume EA to be 1 angle 0. So this will be 1 angle 0. Then I will have the positive sequence reactance J 0.25. Then I will have the negative sequence reactance in parallel J 0.35. Negative sequence is higher. How is it possible? Maybe it is higher, okay. But generally they are almost same. Then I have the zero sequence reactance that is grounded actually. So there will be a path for ground that is x.1 and it is solidly grounded. So there is no xn, it is 0. So this will be j 0.1, right? J, okay, why, what is happening? J 0.1. Okay, so from here I can directly, like I can find out the individual sequence currents. IA1, IA2 and IA not. Remember remember to mark the sequence currents properly. They will always be outgoing from the impedance. Otherwise there will be problem of sign. Okay. So IA1 will be what? IA1 will be first of all this parallel with this. So what is the parallel combination? So IA1 will be basically 1 G 0.25 plus J 0.35 parallel with 0.1. Okay. So this will be 0.35 into 0.1 divided by 0.45. So this will be equals to 0.35 into 0.1 divided by 0.45. 0.078. Okay, 0.078. This will be the equivalent. If I add this with 0.25, then I take the inverse. So your IA1 current, IA1 becomes minus J 3.051. Okay, this is what your IA1 is equals to. Now what will be your IA2? What will be your IA2? So if you remember, it is just like a current division rule. So IA1 is coming here, two currents are getting divided, so ratio will be proportional to their reactances, right? So IA2, I have to add extra minus sign. I have to add a extra minus sign because actually if I divide IA1, right, division will be from up to down, from up to down, incoming up to down. But here the directions are opposite, so that's why additional negative sign will be there. Okay, it will be IA1 minus of IA1 into the opposite reactance, that is 0.1 upon J 0.1 plus J 35. Okay, so this will be basically, I can calculate these values. 0.1 divided by 0.45. So 0.22 minus minus will get cancelled. So plus of J 3.051 into 0.22. So this will be into 3.051. So this will be J 0.678. Okay, and your IA0 will be just the opposite. IA0 will be just the opposite, right? It will be minus, yeah, it will be, okay, I was just thinking one thing. No, nothing, I was thinking nothing. Okay, so IA0 will be minus of IA1 into this, but here I will have 0.35. This will be 0.35 divided by 0.45 into, so 0.771788. This will be plus J 3.051 into 0.78 into 3.051 051. So this becomes J 0.2.737. Okay, all these are in per unit. All these are in per unit, right? Okay. So I want to confirm one thing. What is IB and IC? IB and IC I can individually find out, right? Yeah. But they are asking me what they are asking me. They are asking me line currents. Okay, they are asking me line currents. So what will be the line current, right? What will be the line current here? What will be IA? So if we add these three, automatically it will be 0, right? IA not IA2 will be 0. So what will be my IB? What will be IB? IB will be IA naught plus, it is IB1, right? IB1 will be what? IB1 will be lagging IA by 120, so it will be alpha square into IA1 plus alpha into IA2. So this will be IA naught value is this, right? IA naught value is minus J 3.0 051 plus alpha square. Alpha square is minus 120. So 1 angle minus 120 with IA1. IA1 is this, right? So this will be 0.78. 1 angle minus 20 minus 30, right? This is minus 30. Okay, 90 minus minus 120. Sorry, this is minus 120 is, yeah, minus 30 plus alpha into IA2. Alpha into IA2. So alpha will be equals to what? Alpha will be equals to 1 angle 120 into IA2, right? So this is IA0. Sorry, what am I doing? This is, sorry, what am I? This is IA1, right? So minus 90 minus 90 minus IA0 is this, right? This is IA0. Plus 1 angle minus 120 into IA1. IA1 is already minus 90 angle, right? So I am doing minus 120 minus 90. So it is minus 210. If I add 360, it will be plus 150, right? So this will be 3.051 plus 150. So minus 90 minus 120 plus 360. Then I have this into plus 120. So plus 90 plus 120 is 210, or it will be minus 150, right? So this will be 0.678 minus 150, which is basically plus 90 plus 120 minus 360. Okay, so these things we have got, so we have to actually add this. That's it. So how will I add this? So I have a vector that is here, whose magnitude is 2.373. Then I have a vector that is 150, so that will be somewhere around here, okay, whose magnitude is higher actually, 3.051. So this will be 30 degrees. Then I have another vector that is minus 150, so that will be somewhere around here, right? So this will be 30 degrees, okay, and this will be, magnitude will be lower, zero 0.678. Okay, now I have to add all this. So what will be the resultant component here, right? So this will have some x-axis component, so 30 cos into 3.051 is 2.642 and 30 sine into 3.051 is 1.5255. This also will have some x and y component, right? So 0.678 into sine of 30, this will be 0.339, and on the left hand side I will have another component 30 of cos into 0.678, this will be 0.587. Okay, so ultimately this plus 2.642 will yield me, so this resultant on the left hand side will be 3.23. Okay, and resultant on the y side will be 2.373 plus 1.5255 minus 0.339. So overall it will be 3.5595. Okay, this will be 5252, this will be 339. Okay, so overall I get two components. What are the two components? One is real part is negative minus 3.23 and imaginary part is positive plus j 3.5, like j 3.56. Okay, so what will be the magnitude? 4.8 angle will be 3.23, 3.56 divided by 3.23 tan inverse. So it is 45, and remember it is in which quadrant? It is in the second quadrant. So it is 180 minus theta, so plus 180. So this will be 132.217 degree. Okay, this is my line current IB in per unit. But we can directly find out this in exact as well. Exact will be what? 4.8 into S base. What is the S base? S base is 30 MVA. What is the VL? 13.8, right? So 30 divided by root 3 into VL 13.8. This will be the amount of kiloamperes, right? Angle will not change. So this will be IBPU. So 4.8 into 30 divided by root 3 divided by 13.8, this will be 6 kiloampere, right? 6 angle 132.217 kiloamperes. Okay, so this is my IB actual. Similarly, you can find out IC as well. Can I find out IC directly? Like IC you can find out from here as well, or what you can say, what will be your IC? IC will be like we can do the verification. Okay, let's do the verification basically. So let's first find out IC with normal method, that is IC0, which is IA0 plus this will be alpha into I1 plus alpha square into IA2. So this will be IA0 is this one, alpha into IA1. So IA1 is this value minus 90 plus 120, so it will become this angle plus 30 minus 90 plus 120, yeah, this will be angle plus 30, and this will be minus 30, because here is plus 90 and I am subtracting 120, so that's why it will become minus 30. Okay, so again चलिए आते हैं फेजर पे. तो this will be like, okay, let me just, this will be here, I will have a plus 30 over here vector, it whose magnitude is the highest 3.051. I will have a minus 30 whose magnitude is the lowest, this is 30, right, 30 magnitude is 0.678, and I have a this perpendicular current whose magnitude is 2.373. So again this will have two components, one will be along this and another will be along this. Again this will be same because this cos 30, previously also this was cos 30 only, right, this 3.051. So this cos 30 we already had calculated 2.642. So I will save my time, this will be 2.642, this will be, let me use the same color, otherwise there will be a bit of confusion. Let me use green for this, let me use pink for this, yeah, and this was white. Okay, so this will be same, right, but the direction has reverse, that's it. This will be same, this value 2.642 will be now in positive, along positive x-axis, so 2.642. Y-axis it will be 1.5252. 1.5252. For the red component on the bottom I will have 0.339. On the right hand side I will have 0.587. Okay, this is what will happen at the right hand side. Okay, okay, now let me find out the resultant. So resultant, this time all of these three are added, right? All of them will be added on the right hand side, and on the top side will be same, right, like the previous one. This will be 3.5595 because here this is positive, this is negative, and this is positive, right, here also green positive, pink negative, and white positive. So the top side will be same, 3.5595, 3.5595, but this side will be different because all the all the two will be added. Okay, this also will be not be different, right, because both of them are added. Here also both of them were getting added. What was the value? 3.23. Okay, this will be same only, just the real component has changed. So like why is it, I will show you, like I will show you the conclusion basically. So this will be 3.23 plus j 3.5595. So what will be angle basically? Angle will be same, but this time this will be in the first quadrant. So this will be in the first quadrant. So magnitude will be same. Magnitude will be 4.8. but this will be in the first quadrant, so this will be basically 48. I think it was some 48 angle, right? So 132.217 plus 180, yeah, 48, 47.78 degrees. Now this is a double line to ground fault, right? Yeah, double line to ground fault. Now the conclusion that I want to get is, what is in kiloampere, what will be the value? Kiloampere, the same value, it will be 6 angle 47.78 degrees. Okay, now you will say, like, we are done. Answer, we have finished the answer, right? Divide by 3.23 tan inverse. Yeah, so this is one of the answer. I see, this is the answer, this is the answer. Okay, actual value. Okay, yeah, we're done. But one thing I want to check, what is fault current, what is IF? So for any kind of ground, right, fault current is always 3 IA naught. So what is IA naught? IA naught is actually IA naught is actually this value, right? This is my IA naught. So fault current will be 3 times this, which is equals to 3 into 2.373, which is equals to 7.119 J. Okay, that is what my fault current is. Now I want to check this. Yeah, it will match. So I know this, right? I know IB plus IC. IB plus IC will be fault current. So IB plus IC should match this, right? IB plus IC should match this. This should be equal to fault current. Is it happening? Is it happening? So what is IB plus IC? IB plus IC is equals to this. I will write in rectangular. This is my IC, right? This is my IC, and this is my IB. So the real component gets cancelled, only the imaginary component is left out, plus IC. So what is happening? Real component is getting cancelled, this is getting multiplied by 2, right? So 3.56 times 2, what is it? It is almost equals to J 7.12 per unit, which is exactly matching over here, right? So like, you can cross verify whether whatever you have solved is correct or not using this. So we have solved everything absolutely correctly. Okay, so I hope like clarity is there, right? Everything I have done, like with pen and paper, solving each thing, right? And with the best tricks and techniques, so that there must be 100% clarity what we are doing. Okay, so that's why our motto is concepts with clarity, where concept meets clarity. Okay, so now let's solve the next one. This took a bit of time for us. Let's solve this question basically. So what will be the potential if I close at t equal to 0? What will be the potential of VA, right, for the circuit 1? Circuit 1 is pretty simple, right? Circuit 1 is actually pretty simple. If I just close the switch at t equal to 0, I don't think I have to explain anything here. VA potential, VB potential, all of them will be 0. This will be 0. Okay, VA potential will come out to be 0. But what about circuit 2? Will it be 0? I told you that triple line to ground fault and triple line fault are almost same. So will the VA potential here also will be 0? Will it be 0? Tell me, like, what does your intuition say? Tell me in the comments below, will the VA potential be 0 or not for the circuit B? Okay, so for the circuit B, if the switch here is closed, right, will it be 0? Will VA be 0 here? So for that, we need to do a bit of rigorous analysis. So let's assume that it has some potential VA, right? So all these points have potential VA, VA and VA. And we know it's a symmetrical fault. So only zero sequence component of current will exist. The negative sequence component, sorry, it's a symmetrical fault. So only positive sequence component of current will exist. All the other components of current will be zero. So basically I can say, if I am doing the per phase analysis, IA0 will be 0, IA1 will be IA1, it will not be equal to 0, and IA2 will be equals to 0, because the fault is a symmetrical fault, right? It's a balanced system, symmetrical fault, symmetrical fault. Okay. What about the VA potential? So VA potential, again it will be a summation of VA0 plus VA1 plus VA2. Again your what do I know? What will be VA1? What will be VA2? Because currents, I know currents are symmetrical here. What about the potential? How do I find out the potential? So for potential, what I can do, like you see, all like your voltages are not balanced, but currents are definitely balanced, right? Currents are symmetrical, it's a symmetrical fault. Currents are definitely balanced, but voltages are not balanced, because directly you are shorting these 3 points. That means the voltage across phase B is VA, the voltage across phase C is VA, right? So it is not balanced, right? It is not balanced. So what is it actually? So it only consists of zero sequence component. Why? Because all of them are equal. So that happens only in zero sequence component. So I can prove it to you as well. If you write this down, so VA0, V1, VA2 will be equals to what? This will be equals to 1 by 3, 1, 1, 1, 1, 1, alpha, alpha square alpha into VA, 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 because all of the potential of VABC are same. They are shorted together. So from here you can directly say that your VA0 will be simply VA. Your VA1, if you see, VA1 is what? 1 plus alpha square. It is VA into 1 plus alpha square. What is it? It is 0, right? Similarly, your VA2 also will come out to be 0. 1 plus alpha square. That will come out to be 0. So only VA0 is there, that is equals to VA. VA0 is there, that is equals to VA, right? So, but what do you know? You know, you have 3 networks, right? 3 networks you have. So one is the positive sequence network. That we actually sort, right? So which is, here I have the E1 voltage, and then I have the JXG1, right? Then I have the negative sequence network, right, through which IA2 current will come, but it is open circuit, because IA2 is 0, right? IA2 is 0, so it will be open circuit. And this is my JXG2. And then I have my zero sequence component of network, that is JXG0, and I know this current is also 0. This current is also 0. Okay. Also, one more thing I know, this current is 0, right? This current is 0. If this current is 0, because I know that IA0 is 0. If this current is 0, that is IA0, that is 0. This is equals to what? This is equals to basically plus VA0, right? So VA0 is equals to what? VA0 equals to IA0 into J minus of IA0 into JXG0. IA0 is 0. And what is VA0? VA0 is VA. So VA actually comes out to be 0, because VA0 is VA and IA0 is 0. That's why VA comes out to be 0. So hence proved that VA is 0. So I hope now finally it is clear why this also will be acting as a virtual ground, right? This point will be acting as a virtual ground. So मजा आया, like हो, ठीक है. This point will act as a virtual ground. Okay. So this node actually it is not grounded, but it will act as a virtual ground. So VA also will be equals to 0 volts. So that's why triple LG fault and LLG fault, LLL fault are nothing but same. They are nothing but same. Okay. So I hope you have enjoyed this particular concept. Same thing here also will happen. What will be your VA2? VA2 will be IA2 into JX2 minus IA2 into JX2, that is IA2 is 0, that means VA2 is 0, hence here also VA2 is 0, right? Hence proved. Here also VA1 is 0 because it is directly shorted. So VA1 is this voltage, right? This is V1. And here also I am observing that VA1 is 0, hence proved. So if you enjoyed this concept, please do make sure to hit the like button. Finally, if it is clear that why we assume that this point is ground, like finally it is clear why we assume, if we assume, like finally it is clear why we assume this point to be ground, right? Virtual ground. Okay. So one more concept we will learn, one more concept regarding the current, right? Regarding the again symmetrical fault current. So let's assume that it's a three-phase symmetrical fault, right? So here what will be IF? So IF will be equals to, but basically I want to find out what is the fault current. So IF is equal, is this fault current and this fault current different? That is what I want to find out. So IF will be equals to IA, right? It is in the same, along the same direction. And what is IA? We know it's a three-phase fault. So only IA naught will exist. Only IA1 will exist. Only IA1 will exist. Correct? So IF will be equals to simply IA1 as it is a symmetrical three-phase fault. What is IF dash? So IF dash is equals to minus IC. What is IC? IC is minus of IC1 because it's a symmetrical fault. Only positive sequence component of current will exist. So IF is equals to minus IC1. What is IC1? IC1 is equals to minus of alpha into IE1. So this is my IF dash. So this is my IF dash. So what I can say is magnitude of IF dash will be equals to what? Because magnitude of alpha is 1. So it is same as magnitude of IA1, right? And what is the magnitude of IF? Magnitude of IF will be same as magnitude of IA1. So magnitudes will be same. So magnitude of the fault current, it will not change. IF1, IF will be same. But it depends on which exact node you are calculating the current, because phase can differ. So phase can differ. But magnitudes will be same. So basically it depends on which phase you are measuring the current. So it basically depends on which phase you are measuring the current. Okay. So yeah, I hope that is clear, right? So it does not matter wherever we calculate, but just the phase will be different, right? Hence magnitude will be same, but phase will be different. So it does not matter which point I am measuring the current, magnitude will always come out to be same. Okay. So yeah, that is one point. And let me summarize like whatever faults we have learned right till now. So we have learned about LG fault, LL fault, LLG fault. So I can obviously see, I will compare the positive sequence current, because ultimately the current will come from positive sequence only. The fault current will come from positive sequence. Why? Because a voltage source is present on positive sequence. So ultimately fault current will be supplied by positive sequence current only, because the voltage source is balanced, which is only present in positive sequence. So fault current will be supplied by positive sequence current only. As supply is purely balanced, hence my EA1 is not equal to 0, EA2, EA0 is equals to 0. Okay, I hope it is clear. Now we will, that's why we are comparing the positive sequence current, because the fault current will come from positive sequence current only. Okay, so IA1 for LG fault, it was E by XG1 plus XG2 plus XG3, right? This was the sorry, there was 3 as well, right? No, this was the positive sequence current, but fault current was 3 times this. That is separate discussion, right? Fault current is 3 times, that is a separate discussion. Okay, this was the IA1 current. I am not comparing the fault current. Okay, my LL fault, the magnitude of the IA1 current was root 3 E by XG1 plus XG2. For LLG fault, the magnitude of the fault current was E by XG1 plus XG1 parallel with XG naught, right? This was, if you remember the circuit. So this you can put in your short notes and remember the circuit diagram, right? Remember the circuit diagram. So what was the circuit diagram here? The circuit diagram here was, I had positive sequence, I had negative sequence, I had zero sequence, right? And then ultimately I am ignoring the ZF now. ZF was supposed to be here, right? This was C3ZF basically, right? So this was my X0, this was my X2, this is my X1, and this is my E, right? EA voltage. And this was my IA1, right? And my fault current was what? Fault current was 3 into IA0, which is same as IA1, right? Because IA1, IA0, IA2 all are same. So fault current is 3 times IA0. What about this one? In line, if you line to line, if you remember, basically the positive sequence networks and the negative sequence network were in parallel. Okay. So here the fault current was simply IA1. This was my fault current, right? This was my fault current. Okay. And for double line to ground fault, it is the extended version of line to line ground fault. So then my fault current changes. I have my ZF here, right? Actually ZF would have came here actually. If you consider ZF as well, ZF will come here. But it will be just ZF, but here it will be 3 ZF because it is to ground. This will be 3 ZF, and then I will have my X0, and if you do neutral as well, you can do neutral grounding. Okay, and my this will be my IA0, and my fault current will be 3 IA0. I am not drawing the symmetrical one. Symmetrical one is the easiest one, right? Only single voltage source and a reactance that is present over here. Simple. So if you observe that LG fault, the fault current will be the lowest. IA1 will be the lowest. Then LL fault, the fault current, like the positive sequence current will be the lowest for LG, then LL, then triple L, then LLG, and then triple L, LLG. Okay, triple LG or triple L, that will be highest. So basically I can conclude that my fault current for triple L will be the highest. The zero sequence component of current, sorry, the positive sequence component of current for triple L will be the highest, and for LG will be the lowest. But this will change when we are comparing in what place. So if I am comparing in transmission line, we have already discussed. Again I will discuss. If I am comparing in transmission line, if I am comparing in transmission line, what will I get? If I am comparing in transmission line, I see that what is the transmission line. So I know my x naught will be much larger. So actually I should not write here g, otherwise you will get confused. So basically my x naught will be much larger than x1 and x2. They will be equal roughly, right? So if x naught is much larger, I can approximate this value, right? So basically then my fault current for a LG fault, right? IF LG will be what? It is 3 times IA naught. So 3 times E divided by, I can neglect x1 x2 because the x naught is the highest, right? So this will be basically 2x1, or I can write 2x1 plus x naught, right? Okay, because x1 and x2 are equal, I'm writing it. I can neglect it also I can neglect x1 as well, okay, but let me keep it for a second. And my fault current for triple line to ground or triple line fault, both are same only, that is equals to, that will not change, that will be 3 upon x1. So which one is highest here? So x1 is very low, right? So if x1 is very low, of course this fault current will be very high, right? Here what I can say is x0 is there, so x0 will be very high, actually x0 will be very high, so overall the fault current will go down. So for transmission line point of view, the fault current for 3 phase, so 3 phase fault current will be much greater than the line to ground fault, okay. So for transmission line, for generator terminals, so terminals of generator, now in terminals of generator, our generally that what we do is our zero sequence reactance is very low because it does not produce any zero sequence EMF. So x1 is equals to x2, which is much greater than x0. So here what happens is x0 is much low, so I can neglect this, right? So your IF LG will become 3E upon approximately x1 to x1, and your IF 3 phase will become E upon x1. Now which is highest? Now you see that LG fault is the highest, right? Like this, like I'm trying to explain in multiple ways. Now you see LG fault is the highest. So if LG fault is the highest fault current, so of course it will be more dangerous, and of course there is zero sequence component, which is again dangerous, right? So for fault on the terminals, LG fault is the most dangerous, right? This is one thing that I wanted to cover. Now, what about reactance grounding, right? So if I am grounding it through reactance, let's say reactance of Xn, right? Then the fault current for LG fault changes. So what if I want to make these two equal? So if I want to make condition, so I will put another page. Condition for IF LG equals to IF 3 phase. So this will be IF LG equals to IF 3 phase. Then these two values has to be equal, and of course we know that x1 is roughly equals to x2. I'm talking about generator, right? I'm talking about generator. Okay, I know x1 is roughly equals to x2. That okay, this is valid for anything, for generator or for motor or for transmission line, because x1 is generally equals to x2, that is followed, right? So if x1 is equals to x2, then this will be 3e by 2x1 plus x0 plus 3xn. This will be equals to E by x1. So what will happen? X1, this will be 3x1 will be equals to 2x1 plus x0 plus 3xn. right? G will not be there. This is for any, actually here also G should not be there. This formula is valid for any kind of, not for only for generator, right? So kind of mistake on my end. This G should not be there. Like any G sequence network, it is not for generator, right? Not only for generator, valid for any sequence network. Okay. Wherever we are here, right? So from here I get the equation, what shall be the value of xn, right? So xn will be equals to x1 minus x0 divided by 3. So it can be capacitive or inductive depending if x1 is greater than x1 or not. Okay, so like it depends, if both of them are equal, xn has to be equal to this, right? If xn is greater than this value, if xn, the neutral reactance, is greater than this value, what will happen? Xn is greater than this, right? So xn will be higher, right? So the fault current of LG will be lower. So single line to ground fault current will be lower than 3-phase fault current. So I get a very special condition. This can be asked in gate examination, right? That if my xn is higher than 1 by 3 of x1 minus x0, then I can say that the fault current of line to ground will be lower than fault current of 3-phase. Okay. And if xn lower than 1 by 3, it will be x1 minus x0. So xn is lower, so this value goes low. If this value goes low, then the fault current will be higher, right? So fault current, so I'm talking about the magnitude, only, right? Magnitude. So fault current of single line to ground will be higher than fault current of 3-phase. Okay. Okay, I hope it is clear. I hope it is clear, right? So these are the few important conclusions that I wanted to tell. Also, one more thing, like if in the word it is mentioned lines are bolded to ground or something, right? That means your ZF is 0 or your XN is also 0, right? And it is grounded. Ground is connected. Okay. One more thing is that adding resistance or reactance between neutral and ground doesn't affect the positive sequence and negative sequence networks like currents potential difference. This will not change the currents and potential difference of the positive sequence, negative sequence. Those will remain intact, right? So here, right, even if the neutral is not grounded, this voltages will remain intact no matter what. Okay. Like it will not change currents here. Okay, here it might change if the neutral is not grounded. If the neutral is not grounded, if the neutral is not grounded, if the neutral is not grounded, no, it will change, right? Then there will not be any fault current basically. If the neutral is not grounded, then there will not be any fault current here also. So this point is kind of wrong, right? If neutral is not grounded, then there will not be any fault current, but neutral has to be grounded. Oh, okay. So this assumes the fact that neutral is already grounded, but still that will change. Okay, the thing is, I should not mention currents and potential difference. This is actually wrong. So the thing is, it will not affect the positive sequence and negative sequence network. Positive sequence, negative sequence network will not be affected, but currents potential difference can change. Just like here, if I let's say add a reactance, so this will be 3x naught. So current will change through the positive sequence network, but the positive sequence network itself will not be affected. Here as well, the negative sequence network will not be affected, right? If I add a 3xn here, so this will be 3xn here. Currents will be changed, potential difference will be changed, but positive sequence network and negative sequence network will not be affected. So whatever you do with the zero sequence network, the network will not be affected. So circuit elements, overall network will not be affected. So network is very important, right? Currents, voltages can change. So I will write here, note, current slash voltages can change, but network element will not change. Okay, network elements will not change. Understood? One more point I wanted to say is that you have to assume your transmission line to be always connected in star, right? For that only we derive the impedances. So that is given by default. Like you cannot connect them in delta. So transmission lines will always be connected in star. Okay, they will always be connected in star no matter what. So let's solve few questions. The sequence component of the fault current are as follows: I positive sequence current is this, I negative sequence current is this, I zero is this. So all three are different, right? So it's obviously it's an unbalanced fault, right? It's an unbalanced fault because other component exists, so it will be unbalanced fault, and all three of them are different, so it cannot be LG fault. So LG fault is gone, right? Because if all the sequence currents are same, then only it was LG fault. LL fault is also not possible because there exists zero sequence current. LLG will not be happening because it is a symmetrical fault. Other components exist, so only LLG fault is there. And anyways, you know, in LLG fault, all the sequence component current will be different. Okay, this you know, right? So this is the solution for this question. Let's now solve the 66th question. So in 66, for a system shown in the diagram, what is a line to ground fault on the line side of the transformer equivalent to? So if a line to ground fault happens here, what is it equivalent to? A line to ground fault on the generator side, is it? On the delta side, there is no possibility for zero sequence current to flow. So on the primary or on the alternator side, on the generator side, zero sequence current has to be zero. Whatever fault happens here zero sequence current will be zero on the generator side. So line to ground fault is not possible. It's not possible because line to ground fault means there is some zero sequence current. A line to line fault, it can be possible. Line to line fault can be possible. Let me read the other options. A double line to ground fault. A double line to ground fault. Again, double line to ground fault again is not possible because in double line to ground fault there is zero sequence current, but that is not possible because I am on the delta side. In delta side there cannot be any zero sequence current flowing because if we draw the equivalent diagram of the transformer, if you like, this is like old stuff. So here I will have the XT, right, and on this side neutral is grounded, so neutral is grounded, no problem, and this side fault has occurred, right? So there will be some IA0, right? There will be some IA0, and on this side delta is there. So if delta is there, it will be directly shorted to the ground. Okay, it will be directly shorted to the ground, and then I can directly say that this point will be open circuited. This point will be open circuited, and here the generator is there. It may have its star connected, but this will be only series. I'm just drawing this is the zero sequence diagram. Zero sequence diagram. Positive sequence, negative sequence will be there. I'm just drawing the zero sequence. So in zero sequence, of course, this will be open. It will not generate any potential. So there is no possibility of current flowing, right? Zero sequence current flowing. Three-phase fault on the generator side. Again, this is not possible. Why? Because it means it is symmetrical, but I know already it is a unbalanced fault. It cannot be symmetrical fault, right? It has to be unbalanced. So only one option is left, that is double line fault, right? Double line fault is possible. It can be possible because it will not affect the negative and positive sequence network, right? Zero sequence network. Okay, so this is a possibility. Now let's do the next question. So this is the next question. A synchronous machine 1 pu generating 1 pu 1 pu voltage is connected to a star transformer of reactance 0.1. Okay, its reactance is 0.1 and two transmission lines are in parallel. So xt is 0.1, right? This xt1, right? xt2 also will be same only. Yeah. And these two transmission lines are in parallel. The other end is connected to another transformer that is also generated, another transformer and a generator. Generator is generating the voltage at 1 pu and reactance is 0.1 pu. Okay, the star points of the machine 1 and 2 and of the two transformers are grounded, are solidly grounded, but this is not grounded, right? Remember, this is not grounded. So if this is not grounded, it cannot provide zero sequence current. Calculate the current fed into a double line to ground fault on the low line side terminals of the transformer 2, that is this point. If a double line to ground fault happens here, what is the current fed into it? So basically I have to find out the IF. Right? So for machine 1, the positive sequence, negative sequence, zero sequence current is given. Machine 2, positive sequence, negative sequence, zero sequence current is given. Machine line, positive sequence, negative sequence reactance is given, and zero sequence reactance is given. So if I draw the equivalent diagram here, right, this is the generator on the side 1 angle 0, right? I'm just drawing the positive sequence diagram. I will draw the negative sequence diagram as well, but first of all I want to convert this, right, into VTH and ZTH, because here overall what do I know? I know for a double line to ground, I know there will be a positive sequence network, like equivalent positive sequence network, okay. Then that will be connected in parallel, this EQV, parallel with equivalent negative sequence, like for fault I am talking about fault point of view, negative sequence network. So negative sequence network will be there, and then finally that will be connected in parallel with the equivalent zero sequence network, right? This is the basic structure of double line to ground fault, right? If fault impedance is not there, fault impedance is there, then there will be 3ZF, right? Okay, so let me find out the first of all equivalent positive sequence network about these 2 points, right? So here I will find out the equivalent positive sequence network. Okay, so what is the open circuit voltage? So if nothing is mentioned, right, it is generating voltage at 1 pu, I will assume it is operating in no load because they have not mentioned the load. So my VTH, what will be my VTH? Because I am calculating the, here, right, there is no voltage difference, so there will not be any current, right, right. So this whole, there will not be any drop, so this whole 1 pu will come here. So VTH will be equals to 1 angle 0. Okay, VTH will be equals to 1 angle 0. Now what about your XTH? What will be your XTH? XTH I have to find out. So for finding out XTH, basically I will short these, right, and I will draw the equivalent diagram. So this will go away, right? This will be shorted, this will be short circuited, right? So then your XTH, this will be in series, these two will be in parallel, this will be in series, right? And these, like basically about this, these 2 points, right, XTH about these 2 points. So the diagram will be, this will be J point 45, J 0.2, and about this point I am calculating the XTH, and here I will have J 0.4, and this will be short circuited, right? Okay, so your XTH will come out to be 0.4 into 0.65 XTH. So XTH will be, this value will be 0.4 into 0.65 divided by 1.05. So this will be J 0.24762 pu. This is my XTH 1, okay, 0 sequence 1, and this is my VTH 1. Obviously in the other two networks it is not there, right? Basically voltage source is not there, right? So for negative sequence everything is same, and I have replaced all the reactances with their negative sequence values, right? So you can go through this. I have replaced with the negative sequence values. Okay, so if I replace with negative sequence values, now obviously your, here the VTH2 will be 0, right? VTH1, this is VTH1, VTH2 will be 0, but your XTH2 will be what? XTH2 will be, if I further draw this circuit, so this, right, again will be J 0.35. Now I will have, now this is J 0.8, 0.4. Is this correct? This should also be 0.88. Both lines are in parallel. Sorry, this will, sorry, this, both of them will be J 0.4 only. How is it J 0.8? Sorry. Let me check whether I have done it everything correct or not. Maybe I may also mess up, right? So I have to be careful. So J 0.4 is there. J 0.4, machine 2 has J 0.2, and the transformer is 0.1 pu, that will be same, and machine 1 has J 0.25. Yes, so this will be J 0.2, and about these nodes I have to measure the XTH. XTH2 will be equals to, this will be so J into 0.55 into 0.3 divided by 0.85. Okay, so XTH2 will be equals to J, so this comes out 0.55 into 0.3 divided by 0.85, it comes out to be 1.94, right? 0.194. Okay, this will come out to be 0.194. What about the zero sequence diagram? So zero sequence, the important point to note here is this, right? This side is not grounded. So here this will have no connection between the ground. Okay. Other than that, everything is grounded. So all other things will exist. Okay. Your xt will be same. This time the line reactance will be double because the zero sequence line reactance was 0.8 and your zero sequence reactance for the generator machine 1 was 0.005. This was 0.004, but this will not come into effect because it is open circuit, right? So if this side is open circuit, now my xth is only on the left hand side, xth 0. So xth 0 is actually pretty easy. It will be j 0.15 plus j 0.4, which is j 0.55. So now finally I will draw the complete circuit diagram, which simplifies to this one. Very simple, right? This will be j 0.55, negative sequence reactance was j 0.194. Okay, j 0.194. And positive sequence xth1 was 0.248. I can approximate this to be 0.248. And your VTH was 1 angle 0. So I have to find out the fault current. So first of all, for finding out the fault current, I have to find out VA0, right? So sorry, IA0. So what will be IA1? So IA1 will be equals to, so actually IA0 is supposed to be going outwards from the zero sequence. This is incorrect. IA0 is supposed to be going outwards, right? And this is my IA2. So IA1 will be equals to 1 divided by 0. Like j will be there anyways. Okay, 0.248 plus 0.194 parallel with 0.55. So this will be equals to into 0.55 divided by 0.55 plus 0.194. So 0.143 plus 0.248, then inverse of this, it comes out to 2.55 minus j 2.554 pu. Right? What is your IA0? So IA0 will be equals to IA1 minus sign will be there. Why minus sign will be there? Have been explained in today's lecture only. Okay, then multiplied by the opposite reactance j 0. Basically it will be 0.194 divided by 0.194 plus 0.55. Okay, so into 0.194 divided by 0.194 plus 0.55. Okay, so it comes out to be 0.666 pu, but of course my fault current in per unit is 3 times I naught, right? It's a zero sequence component, so 3 times this, it comes out to be 2 pu. So your fault current will come out to be 2 pu. This will be your answer. That's it. Okay, you're done. So they have just asked what is the fault current fed, right? Nothing, no voltage rating has been given, so I have to answer in per unit. That will be 2 per unit. Okay, that is the fault current. Let us solve this next question. So the positive negative zero sequence impedance of generator Z1 is Z1, Z2, Z0. Okay, so for the line to line fault with fault impedance ZF, right? The fault current, line to line fault is happening, right? The fault current IF1 is K into IF, where IF is the fault current with a zero fault impedance. So if I have zero, like if I have fault impedance, right? I know in a line to line fault, I have this voltage EG. then I have this positive sequence, and then I have the fault impedance ZF, and then I have the negative sequence, right, Z2. And my IA1. So IA1 is basically the fault current in this case. If you remember, no, IA1 is not the fault current actually. My fault current, if you remember, it was minus J into root 3 IA1. So basically your fault current is proportional to IA1 only. So I will just compare the IA1, right? I will just compare the magnitude of IA1. Okay. So if fault dependence is there, what is IA1? IA1 is equals to EG upon Z1 plus ZF plus Z2. They are telling me, so this will be equals to my IF1. This will be proportional to IF1. If ZF is not there, so then what will happen? If ZF is 0, if ZF is 0, then my IA my IA1 my IA1 will be EG divided by Z1 plus Z2, right? That will be proportional to my IF, that is given to me, IF, right, when zero fault impedance. So the relation between ZF and K they are asking. So I know what will be IF1 by IF. So IF1 by IF, from here I can find out it is K. IF1 by IF is simply K, right? That is equals to my K. And here in this equation, what is it equals to? It is equals to IF1 is this one, right? That is EG upon Z1 plus ZF plus Z2 into IF2 is EG, IF is EG upon Z1 plus Z2. Okay, so this will get cancelled. Right? So they are just asking me the relation between K and ZF, right? So relation between K and ZF. So ZF is equals to what? So I have to just eliminate ZF from here. So Z1 plus ZF. Okay, again this is freaking out. We're almost at the end. Z2 will be equals to Z1 plus Z2 divided by K. So ZF will be equals to Z1 into 1 by K minus 1, or ZF will be equals to Z1 plus Z2 into 1 by K minus 1. So yeah, this will be equals to Z1 plus Z2 into K minus 1, sorry, 1 minus K divided by K. So ZF is equals to 1 minus K divided by K, 1 minus K divided by K into Z1 plus Z2. So that will be option A. So in this case, option A will be the correct answer for this question. Okay, that is 68. Now 69. Let's solve the 69. So 69, we have a 100 MVA 18 kilovolt turbo generator, has the following per unit reactance. Direct axis synchronous reactance is given, negative, positive, all these are given. X0 is given. Okay. The generator's neutral is grounded to a this current limiting reactor. It is a reactor, right? Your ohmic value is given. It is a reactor. It is not a resistance. It is a reactor. Okay. Now what they are telling me is, before connecting the generator to the power system, the terminal voltage is manually adjusted to 16 kilovolt. At that instant, a double line to ground fault occurs at the terminal VNC. The initial symmetrical RMS current flowing to ground and the initial symmetrical RMS current in line B. So luckily here the synchronous reactance and the positive and the negative, all of them are equal. Okay, if they were not equal, then I would have only chosen xd double dash. I would not have chosen these two, right? So xd double dash is the most important one, because here they are asking me the initial RMS symmetrical current that is flowing to ground and initial RMS current that is in line B. So if there is double line to ground fault happening, right, between line B and C, so I have three lines here, and there is double line to ground fault happening between line B and C, right? So this is my IB current, this will be my IC current. Okay, and this will be my fault current, right? So they are asking me this IB current and this fault current that is flowing to ground. Okay, so that will be hectic. So let me draw the circuit, right? So let me, for a double line to ground, it is just they're telling me the fault is happening on the terminals of the alternator. So I will have the positive sequence impedance, remember subtransient reactance. Okay, then I will have the negative sequence reactance, and then I will have the positive zero sequence reactance. Here, as initially they are telling me that the before it is not connected to the power system, right? So my generator current was 0. So pre-fault was no load. So if it is no load, whatever is the generator voltage, it will be same. It will be 1 angle 0. But they have told me it is not 1 angle 0. They have reduced the voltage to 16 kilovolt. So it will not be 1 angle 0, right? Because actually it is rated for 18 kilovolt, but they have reduced to 16 kilovolt. So it will be 16 divided by 18 angle 0. Okay, what is 16 divided by 18? It is 0 0.89. 0 0.89 angle 0. Okay, now I know my reactance is J 0.2. These are J 0.2, and the zero sequence reactance is J 0.05. Okay, so this will be my IA naught current, this will be my IA2 current, and this will be my IA1 current. Okay, so first of all I have to find out the fault current. So if I have to find out the fault current will be what? Fault current will be so I have to find out IA naught. So first of all I have to find out IA1. IA1 will be 0.989 divided by J 0.2 plus 0.2 in parallel with 0.05. So it will be 0.2 into 0.05 divided by 0.25 plus 0.2 into 0.89, 3.7, 84 minus 90. Okay, what will be my IA0? It will be minus of IA1 into 0.2 divided by 0.25. Okay, so minus 3.7084 angle minus 90 into 0.2 divided by 0.25. So it is 0.8. So 0.8 into 3.7084. So it almost comes out to be 2.97 angle plus 90. Okay, so one more mistake I had made. I ignored this line, right? We completely जाने दो इसको भाई. We ignored this line. It is grounded through a 0.162 reactor. So there will be a reactor as well, right? I forgot to add that. There will be a reactor that is 3xn, right? Because like 0 seconds, so it will be 3xn. So what will be xn in per unit? So xn in per unit have they given to me. So I know it is 100 MVA and it is 18 kilovolt. So with this, like, we are hoping that expecting we have to use this base, because generator per unit impedance is also given according to this base. So I will convert in this base only. So this will be 0.162 into 100 divided by 18 whole square. So this will be 100 divided by 18 whole square into 0.162, so 0.05. It also comes out to be 0.05, but as it is 3 times, so this will be J 0.15. So this will actually become J 0.2, interestingly. So this will actually become 0.89 divided by 0.3. It actually comes out to be 2.97. So this will be 2.97 divided by 2, because it's like, this is how much, this is 0.2, this is also 0.2, right? So this will be 2.97 divided by 2. So it comes out to be 1.483. Okay, 1.483 pu. Okay, 1.483 pu. So this is my IA naught, right? What will be my fault current? It will be 3 times this. So IF will be 3 IA naught. So IA naught is this 1.43, 3 times 1.483 into 90. So 3 into this, it comes out to be 4.45 angle 90, and magnitude of IA will be 4.45 into S base, that is 100 MVA, upon V root 3 into V base, that is 18 kilovolt. This will be kiloamperes. So this will be into 100 divided by 18 divided by root 3, comes out to be 14.273 kiloamperes. Okay, so that is the magnitude of the fault current for the question. Now this is the first part of the answer. Second part, they are asking me what is IB. So for IB, I need IA0 plus alpha square IA1 plus alpha into IA2. So IA1 I already know, IA0 I know, I need IA2, right? So what will be IA2? IA2 also will be same. IA2 also will be same, right? Because it will be equally divided. So IA2 also will be same. So I can say my IA0 and IA2 are same, equal. So this equation can be rewritten as alpha square into IA1 plus what else I know? I also know this, right? IA naught is actually minus IA1 divided by 2. So which is equals to minus IA1 divided by 2. So I can replace this, right? So this will be IA1 plus 1 plus alpha into minus IA1 divided by 2. IA0 is minus IA1 divided by 2. Okay, can this be beneficial to me? So this will be, if I take common IA1, so what do I know? What is 1 plus alpha? I know this formula, right? 1 plus alpha square, this property is equals to 0. So 1 plus alpha will be equals to minus of alpha square. So I can replace this with minus of alpha square, right? And minus minus will become plus of alpha square. So this will be alpha square plus, so this will be minus of alpha square divided by 2. So this will become plus of alpha square. So this will be 3 by 2 I1, 3 by 2 alpha square into IA1. Okay, 3 by 2 alpha square into IA1. Okay, you have understood this point. So they have just asked me the initial in the line B. So line B, again, if I just calculate the magnitude, right? So this is the line B current, right, in per unit. So line B current magnitude will be, because alpha square magnitude is 1, so 3 by 2 into magnitude of IA1, so which is actually 2 times IA0, right? Which is actually 2 times IA0, or I can directly write here as well what is magnitude of IA1, that is 2.75, right? So it will be 2.75 in PU. So 3 by 2 into 2.97, not 75, sorry, 2.97 in PU. Okay, 2.97 in PU, and I want this in actual value. So this will be 3 by 2 into 2.97 into S base upon V base. V base is 18. This will be kiloamperes. So 3 divided by 2 into 2.97 into 100 divided by root 3 divided by 18. So this will be equals to 14.2. Okay, it almost comes out to be same. Is it? How it is? It comes out to be same. It comes out to be same only. Yeah. Okay. It comes out to be same. That's interesting. So this comes out to be 14.29 kiloampere. So basically the line current in phase B also will be same. Okay, line current in phase B also will be same. In phase C also you will see magnitude will be same, but phase difference is there, right? There is phase difference. Okay, keep that in mind. So let's now solve the next question. So a solidly grounded alternator with sequence impedance, this solidly grounded, right? So its neutral is solidly grounded. Sequence impedance are given, is connected to a transformer having a series impedance. The transformer is star with secondary neutral solidly grounded. Primary neutral they are not discussing. They have not told me about the primary neutral, right? They have not told me about the primary neutral. A double line to ground fault occurs at the transformer secondary terminals B and C. Calculate the per unit voltage of the healthy phase. Okay. So they are telling me to calculate the per unit voltage of the healthy phase if a double line to ground fault occurs. If a double line to ground fault occurs, and they have just told me that the secondary of the transformer is connected to a neutral, but they have not discussed anything about the primary, right? Primary they have not discussed. That means primary of transformer is not grounded. Okay, primary of transformer is not grounded, right? So if primary of transformer is not grounded, then what will happen? Then I can say, right, what can I say? What can I say? What will be the zero sequence diagram? Zero sequence diagram will be here. The primary is not grounded, right? So this will be open circuit. Then I will have the X0, and before this I will have the zero sequence impedance of the generator, that is 0.2, and the zero sequence of the transformer is also that 0.2. After this, do I have anything connected? No. Secondary side fault is happening, right? So this is my zero sequence network, right? This is my zero sequence network, okay? And I know this side is grounded. This side is ground. So what is my XTH 0? It is infinity. So zero sequence is actually not connected, right? So for the double line to ground fault, zero sequence is not connected. So only positive sequence is there. In positive sequence, what will be there? Your XG1. In positive sequence, what else will be there? So this is your zero sequence network. Then I have my positive sequence network. So in positive sequence network, what things will be there? So I will have my EA, right? The voltage, it is operating in rated. So assumption is it is operating in no load. So this will be 1 angle 0. I will have the positive sequence reactance, that is J 0.3. J 0.3. And then I will finally have the transformer reactance, right? This will be there, right? Transformer reactance for positive sequence will be J 0.2. That will be same, right? Transformer series impedance, this will be there. And ultimately this will be my equivalent network. So I don't have to convert this into VTH and XTH. This is already done, right? And what about my negative sequence network? Negative sequence network. So negative sequence network, just the voltage source will not be there. Okay. So so negative sequence, it is J 0.2. J 0.2. And obviously transformer will be there, so it will be J 0.4. So now I will combine the circuits, right? I will combine the circuits, okay? So this will be here, right? This will be J 0.5. This will be 1 angle 0. Then I will have the negative sequence reactance, that is J 0.4. And then finally I will have the zero sequence. So fault current will be 0, but still there will be some phase currents over here, right? That will be very high, okay? That will be very high. So there is no, so this is infinity, right? So now what are they asking? They are asking me for a double line to ground fault happening at the secondary terminals phase B and C, calculate the per unit voltage of the healthy phase A. What is the voltage of the phase A, right? What will be the voltage of the phase A? So for that I need to find out VA0, I need to find out VA1 and VA2 and VA1. I know all of them will be in parallel, so I just need to find out VA1 basically. So VA2 I can directly find out, right? So VA2 will be what? VA2 is just voltage division, right? Because here the current is 0. So it is just voltage division. So it will be 1 angle 0 into 0.4 upon 0.9. Okay, that is what my VA1 is equals to, right? So VA1 will be 0.4 by 9 into 1, that is 0.444 angle 0, right? This is what my VA1 is equals to. And of course, what is, like, all of them are same. So VA1, VA0, all of them are equal because they are in parallel. And my VA is what they have asked me, the potential for VA. VA will be VA0 plus VA1 plus VA2. So it is basically 3 VA1 whatever. So I have to multiply 3 here. So it will come out to be 1.34 per unit. Okay, 1.34 per unit. So in per per unit is given only, no base values are given, so it will be 1.34 per unit. This will be the answer for this question. Let's now move on to the last one, then finally you can go, छुट्टी हो गया आपका, ठीक है. Last one we will solve. So a 50 hertz, this is given, these are the values. Neutral is grounded through a 0.5 reactance, okay. 0.5 reactance, it is grounded, okay. Prior to the fault, the generator voltage is 12 kilovolt. This 0.5 reactance, obviously I have to choose these base. Why this base? Because the per unit values are also according to these base only. So the reactance xn will be 0.5 into S base, that is 15, divided by V base whole square, that is 13.2 whole square. So this will be 0.5 into 15 divided by 13.2 whole square. So this comes out to be 0.43 pu, okay. This is what my xn is equals to, and they're telling me the RMS ground current during RMS ground current. Ground current basically means, ground means basically it is the fault current. They're asking me the fault current, right? Ground current is the fault current during double line to ground fault occurring in phase V and C. Okay, it's fairly straightforward. It's not like it is something difficult. Okay, so it's not like it is difficult. Ground current will be basically the fault current only. Here just one simple thing is there, ground current. Maybe you guys will have doubt. So what do I mean by say ground current? So ground current basically means the fault current only. The current that is going to ground, that is the fault current. So if I draw the circuit, right, I can, without drawing the circuit, I can directly do it, right? So it is operating in no load, but my voltage of the generator is actually not 1 angle 0. It will be 12 by its own base, that is 13.2, right? So 12 divided by 13.2, that is 0.91 angle 0. Okay, that is what my voltage of the generator is. I can do this without drawing the circuit, right? Can I do this without drawing the circuit? So I know what will be my IA1. IA1 will be Vg upon x1, J will be there, x1 plus, there is nothing else, right? x1 plus x2 in parallel with x0 plus 3xn, right? Because there is a neutral reactance connected, right? Without, I will not draw the circuit for the last one. I will not draw the circuit. So what is x0 plus 3xn? So 3xn, right? 0.04304 into 3. This will be 3xn will be this plus 0 sequence component 0.08. So this comes out to be 0.209. x2 is 0.2 only, so it is almost same. Okay, again they will be divided equally. x1 is also 0.2. So this will be roughly into 0.2 divided by 0.409, 0.1 plus 0.2 into 0.91. So this IA1 comes out to be minus of J 3.0106. Okay. So this will be, so what will be my IA0? IA0 will be again minus of IA1, and it is almost equal, right? You can see like this is 0.02 and 0.010. It will be almost equal, but still, if you still want to do without drawing the circuit, I will do, right? Without drawing the circuit, you will draw the circuit, right? You will draw the circuit and solve. So this will be into 0.2 divided by 0.409. So this comes out to be minus will become plus, so plus 1.4722 per unit. Okay, this is what my IA0 is, but of course I am not interested in IA0, I am interested in the fault current. So what is the fault current? Fault current will be the ground current, that is IG this will be 3 magnitude will be 3 into magnitude of I naught. So multiplied by 3, this will be 4.4167, right, in per unit, but I want to write in kiloamperes. So in kiloamperes this will be 4.4167 into the S base is 15 and V base will be root 3 into 13.2, right. So this value will be equals to, so into 15 divided by 13.2 divided by root 3, so this comes out to be 2.898 kiloampere. Okay, this will be the answer, 2.898 kiloampere. Okay, this will be the answer for this question. And with this we are done with fault analysis. So if you enjoyed this whole series, right, of fault, like we have covered every single thing, I have not left anything, right, I have literally not left anything. Okay, like you might have a doubt here as well, that how, sir, this is like how my like XPU is equals to this X actual into S base divided by V line whole square. So X actual is a single phase reactance, right? So S base is what? S base is 3 phase MVA. So what is V line? It will be root 3 times 3 VPS. So this will be 3 VPS whole square. So if I divide 3 phase MVA by 3, it will be single phase MVA. Now I hope it is clear, right? Now it becomes what? It becomes single phase MVA upon VPS whole square, right? This makes sense. Why this makes sense? Because I know like the what is the if I say what is my Z base, Z will be basically magnitude of Z will be equals to what? It will be V by I, right? V base upon I phase. And how can I write my I phase in terms of MVA? So I phase will be equals to for a single phase load, it will be S single phase MVA divided by V phase. So this you will replace here, and you will get your Z base to be this, right? So if you, even if you have doubt, I might feel like some student might have this doubt. So still, like last lecture में भी सब कुछ clear करवा रहा हूँ, ठीक है? So still this is like you'll get the correct result. So this whatever we are writing, whatever we are using is correct. So I have tried to clear every single thing conceptually, fundamentally, so that your concepts are sharp. So now any questions come from fault analysis, you will be able to crack it, because we have solved almost 71 questions, and those 71 questions were not cakewalk. Those were actually very good questions which I solved, right? So those are actually very good questions. So if you did enjoy, please do comment below. Please comment on the first video. That will really help us out. Really help us out. Like if you do the appreciation, like other students can get to know the quality of teaching that we're doing, right? Please, that's just a request from my end. Okay. So yeah, I will see you in the next video. Until then, happy learning.